where the topological states live on the edges. Now, instead of implementing this Hamiltonian on a system with open boundary conditions, if we implement on a periodic boundary condition, we will find that it is similar to this trivial state where there are no topological phases. So in periodic boundary condition, irrespective of the value of m, in the trivial regime where the absolute value of m is greater than 2, the Chern number is 0, whereas when the system is topological, the Chern number is non-zero. As you can see, when the value of m is between -2 and 0, it is known as the m phase, because if we plot the energy eigenvalues, the band inversion occurs at the m point in the Brillouin zone, whereas for m between 0 and 2, the band inversion occurs at the gamma point in the Brillouin zone. And in this region, which are shown in red and blue, the system becomes topological. Now let us discuss the effects of dislocation in this system. To create a dislocation center, we remove a line of atoms which are shown in green here, and then we stitch the atoms which are adjacent to the lines to the line which we remove. So now, if an electron with a certain momentum k encircles this dislocation center, it will pick up a phase factor which is denoted as phi here. So if the system has zero momentum, which occurs for the band inversion point in the gamma phase, this phase will be 0, whereas in the m phase, this phase will be pi. So in the gamma phase, if the system encircles this dislocation center, since it will not acquire any phase, it will not be able to see the effect of the dislocation. Whereas in the m phase, we expect it to see the effects of the dislocation. Now, in our system, we create two dislocation centers here and here, just so that we can also join the top edge and the bottom edge, so that we can employ periodic boundary conditions in both directions. In case we had only one dislocation center, then we would not be able to employ periodic boundary conditions in both the directions. Now, if we implement the Hamiltonian of the BHZ model in this system with periodic boundary condition and two dislocation centers, we will see that the spectrum is usually gapped, but there are two states which live at zero energy. And if we plot the probability density of these states, we will find that they are living on the dislocation centers. However, if we do the same thing in the gamma phase, then we will not be able to see any dislocation modes, because as we discussed previously, in the gamma phase, the electrons do not see the dislocation center. Now let us turn on some non-Hermitian terms in this Hamiltonian. So the Hamiltonian itself was Hermitian. The red terms which are shown here are non-Hermitian because of the factor of square root of -1. Now, for this Hamiltonian, it can be shown that the effective hopping amplitude towards, let's say, the right direction and the left direction are different. And as a result, if we plot the probability density of the states, we would find that all the states go to one edge of the system. This is known as the non-Hermitian skin effect. And this happens for all the states irrespective of the value of m. So now, irrespective of whether the system is trivial insulator or a topological insulator, all the states will live at one of the edges. So for a Hermitian system, we found that the topological states will live at the edges, whereas the trivial states will live in the bulk. And this is known as the bulk boundary correspondence. And this bulk boundary correspondence is broken as we turn on the non-Hermitian terms. So, so we would like to post the question, how do we experimentally find whether a system is topological when it is non-Hermitian? Because if we just try to measure where the electron is by which is the same as finding the probability density of the electron, we will see that it goes to one of the edges irrespective of whether the system is trivial or topological. Now, previously we found that for a Hermitian system, if we have dislocation centers, then the topological modes get pinned at the dislocation center. So we would like to see what happens for a non-Hermitian system. Here, I have diagonalized the Hamiltonian for a periodic and an open system with two dislocation centers. And since the Hamiltonian is non-Hermitian, now the energy eigenvalues have become complex. Now you can see there are some special modes which I have shown in red, which are separated from the other energy modes. And if we find the probability density corresponding to these modes, we will see that they are still located at the dislocation centers. So we found that although most of the states go to one of the edges of the system, there are some special states which in the topological regime live in the dislocation center, and this can be used as a way to experimentally verify whether a non-Hermitian system is topological. We can do the same thing for the gamma phase by switching the sign of M. In the previous slide, M was -1, and by switching the sign of M, we can go to the gamma phase, and here we see that those special modes which were present here are not there anymore. As we discussed previously, in the gamma phase, the electrons cannot see the effects of dislocation, and here the dislocation modes are absent. All the eigenstates, if we plot their probability densities, we will see that they accumulate at one of the edges of the system under periodic boundary condition, which is just the skin effect. And if we do the same thing under open boundary condition, so if we diagonalize the system under open boundary condition, it will accumulate at one of the edges. And if we do the same thing for periodic boundary condition, there will be no edges, and there the electrons will be dispersed throughout the bulk of the system, but they will not accumulate at the dislocation centers. Now, we want to pose the question, suppose we keep increasing the non-Hermitian parameter, will we still get these dislocation modes? First, let us diagonalize the system without any dislocation. So as we keep increasing the dislocation at the non-Hermitian parameter, we find that the energy eigenvalues are spread in the complex plane like wings of a butterfly, and they come closer, they join at the origin of the complex plane, and the wings mix together. Now suppose we implement the Hamiltonian with a lattice with dislocation centers. We will find that initially there were these dislocation modes, but as we keep increasing the non-Hermitian parameters, the wings come close, they join, and after that the dislocation modes vanish. If we plot the probability density of any of these states, they will all show the skin effect. So we found that as long as we don't have any zero energy eigenvalue of the system hosts dislocation modes, but as the wings come closer and join at zero energy, the dislocation modes vanish. So we have this Hamiltonian, which is just a 2 cross 2 matrix. We can analytically find its eigenvalues, and then we can try to find when it will have zero energy eigenvalue. So given a value of m, we can find the values of the non-Hermitian parameters where it will have zero energy eigenvalue. From this, we can find where the phase transition will happen so that we will not have any dislocation points, any dislocation modes anymore. And after doing this calculation, we found that for Hx and Hy, we have a phase diagram which is shaped like a diamond, whereas for Hz, the phase diagram looks like an ellipse. Now we did some calculation. We really cannot say it is a phase diagram unless we show that it has some topological invariant. So consider a regular system, let's say a magnet, which once we heat it beyond its Curie point, it becomes a paramagnet. And there is an order parameter of the system, which is the magnetic moment, which is non-zero in the ferromagnetic phase. But after heating beyond the Curie point, in the paramagnetic state, the order parameter is zero. Similarly, in topological systems, there are no order parameters, but there are these topological invariants. For the Hermitian case of the BHZ model, we found that there was this Chern number which was non-zero in the topological regime. So we can naively take the same formula and plug in the non-Hermitian Hamiltonian. Then we can try to find what will be the Chern number. And we can do all these integrals numerically. We find that the shapes we found analytically using a different method within that region, the Chern number is -1 here, which is which is traditionally called the M phase for the Hermitian case. And here we find the dislocation modes, whereas when the Chern number is +1, which is the gamma phase, there the system remains topological, but we do not anymore find the dislocation modes because the electrons do not pick up any phase factor after encircling the dislocation point. And outside this region, the Chern number is zero. So here we found, here we backed up our claim with numerical methods that the system really has a Chern number in this regime. So it is really a phase. And as we cross this region by increasing the non-Hermitian parameters h, there the Chern number becomes 0 from -1. So the system undergoes a phase transition and it cannot host dislocation modes anymore. A similar phase diagram was obtained by some people in this paper in a different context, and we found it once again in for these dislocation modes. Now, so far, when we were talking about the values of the non-Hermitian parameter, which will cause the dislocation modes to vanish, and we calculated the phase diagram for these parameters, we were talking about periodic boundary condition. If we do the same thing under open boundary condition, we will find that when the value of the non-Hermitian parameter is less than the value which we obtained previously, before that, the dislocation modes eventually melt and they become these edge states, which is just due to the skin effect. So this happens in open boundary conditions because here the electrons can tunnel from this point to the points in the edges. This is just a finite size effect. If we keep increasing the size of the system, the electron cannot easily jump from here to the edge of the system, and there in thermodynamic limit, when the size of the system becomes infinite, the results obtained from the open boundary condition and the previous result which we analytically obtained under periodic boundary condition, they become identical. So whatever I told you so far has been summarized in this slide. Even if you forget all I said after a long time, I would want you to remember just this single thing, that when there is no dislocation in the system, the eigenstates of a non-Hermitian Hamiltonian usually get accumulated at one of the edges, and there is no way to determine experimentally whether the system is a trivial insulator or a topological state. Whereas if we introduce dislocation centers, then the topological states will get pinned at the dislocation centers. These are the dislocation modes, whereas the trivial states will show the non-Hermitian skin effect. However, there are some exceptions. For example, here in the gamma phase, it is a topological phase. Although since the electrons cannot feel the presence of the dislocation center, despite being a topological phase, it does not host any dislocation modes. And so far, everything I told you about are theoretical work. So I took the Hamiltonian, I implemented it in a lattice, and I diagonalized it numerically. However, these things can probably be verified experimentally. So in photonic lattices and also in metamaterials, people have observed the effects of dislocation in Hermitian systems, and people have also implemented non-Hermitian Hamiltonians. However, as far as I know, so far there has not been any work on non-Hermitian Hamiltonians in lattices with dislocations. So if someone does that, one would be able to experimentally verify the results we found theoretically. So that's it. Questions?
Thank you for your speech, Urjishmanda. Okay, there's somebody speaking.
Also, here is the link to the paper. If you want to know about it in more detail, you can read it. Also, you can send me an email.
Okay, I guess there's a question in the comment section of Teams. So it reads like, why can't the dislocation center be at the middle? Then also we will have periodicity, and in that case we can work with only one dislocation center, right?
Okay. Let me show you a figure of the lattice. Can you see my screen?
Yeah. Yes.
So to create this dislocation center, we have to remove one line of atoms, and in case it is at the middle of the system, we have to choose one direction where we remove the line of atoms, like here, or we can do it along this side. So if we put it in the middle and we remove one line of atoms here, so let's say here these atoms are removed, but here they are not removed. In that case, this point and this point will not be equivalent, so we will not be able to use periodic boundary conditions.
So like suppose we have say the normal lattice, and like we don't remove the atoms at the edge, we just remove the atoms at the center. Then also the edge.
So are you suggesting we remove one atom from the center?
Yeah. I mean, not one atom. I mean, maybe a line of atoms.
Then we okay, then in case we teach atoms in one side of that, then maybe we will be able to find a dislocation center that way. Yeah, and if we then diagonalize the Hamiltonian, we can do something like this. Yeah.
Okay. So, like, is there any advantage of like choosing this kind of like edge dislocation kind of thing? I mean, dislocation at the edge.
So I am working with a two-dimensional system, so I think I am not sure what all kind of dislocations can be found in two dimension, but I think probably this is the only dislocation that can be implemented. For screw dislocations, we need three dimensions.
Okay.
Okay, so there's another question.
Yeah.
It's by Ivan Dotto. So it's written that how experimentally is it possible to dislocate one chain from a lattice? Is it possible in real material or only in cold atomic setup or others? So this is one part. Then the next part reads that is the BHZ model you're talking is time reversal symmetry. What about the non-Hermitian term you are adding? Does this preserve the symmetry?
Okay.
I guess Ivanda, you can actually like talk and explain if that's not a problem.
Yeah, am I audible?
Yeah, you are audible.
Yeah, I am. And the model you are talking, is this time reversal symmetric or not? BZ model?
I'm not sure. We have to figure it out.
Because in general, the BZ model proposed as a four-band Hamiltonian. But you are talking about the spinless system.
Yeah, so this is also sometimes known as the half BHZ model. So you can take two copies of BHZ model and you can then stack them on top of each other so that the whole system becomes time reversal symmetric.
Okay, so when you are adding some non-Hermitian terms, so have you considered or protected any kind of symmetry in your mind or nothing, just added something?
No, we just added it. We didn't consider whether it preserves the time reversal symmetry or not.
Okay. And next,
I cannot answer you right now. We have to check it out by we have to put the time reversal operator and see whether the Hamiltonian remains invariant.
Yeah, and the second question is how we can experimentally dislocate one chain for experimental in material.
Okay, so in real crystals, so these dislocations can happen automatically. But suppose you take a something like photonic lattice, so you remove certain points and somehow you have to engineer the couplings in the system so that after removing the point, the electrons from both sides of the point can jump from one to the other point. I don't know how they do it experimentally, but they might have discussed it in detail in the references I posted here. So I will share my slides.
No. Okay, thank you. A nice talk.
Yeah, I have shared the link to my slide.
Yeah, I guess we are done with the questions. Thank you so much, Ojishwanda. I think if there are others, they can reach you via mail or other media. So thank you, Ojishwanda, for coming here. I mean, this is a very small scale conference. So somebody like you coming here has been a great honor for us. So thanks a lot for that. I guess many will be benefited by your inspiring talk. So thanks a lot.
Yeah, you are welcome.
Yeah. Okay. So we'll move on to our next speaker. Uh, our next speaker is again an alumnus from RKM Narendrapur. Uh, okay. An alumnus from RKM Narendrapur. He's just 1 year senior to us, and I mean, yeah, I'll just tell you a little story. Like this was probably 2020 when we came across the news that that same guy from our senior batch had got an AIR 2 in both IIT Jam and JEST. So, so that's the thing. Like from before, we used to hear tales, and after such a long time, we'll be getting to hear his talk. So it's a huge honor for us to host Mr. Rupak Mujumdar. He is presently a PhD student at TIFR Mumbai. He works in the field of astroparticle phenomenology, and the topic of the talk seems really interesting, and that is how to see the baby universe. Rupakda, please, you can speak.
Yeah, thanks. Let me share the slides. I am audible, right?
Yeah, you're audible.
Uh, is the screen shared? I'm not able to understand.
No, your screen can't be seen right now.
How to share the screen?
There's an option like you're doing in Teams. There's an option share at the top, so you just select that. Could you see that? I mean, just at the left of that leave button.
Okay.
So you click on share, and then probably there are two there are two options, screen and window. So you go on for whatever's suitable, whatever suits you.
Yeah. Connects. I'm not able. I'm not able to find it in the that leave option, that red mark, and before that we said that there is show participant and then chat and then raise hand, right? And where is the share option?
You may use Control plus Shift plus E to share. Control plus Shift plus E.
Control plus Shift plus E. It still didn't work. Control Shift.
There is a square and up arrow in between this.
Yeah, then it comes close share tray. Yeah, and then what to do?
Then you should just select the window you want to share.
Sorry?
There are two options. Click the open. There will be one of another option is just select the font here.
Just a minute. Sorry.
Fine. Take it.
Yeah.
There is some problem. Just wait for 2 minutes. I will fix the problem.
Rupavik, did you try those shortcuts which Shambhavu suggested? Easy there. Yeah, yeah, your screen is visible now. Absolutely. But I guess you're muted. I mean, you can't be heard.
Yeah, am I audible now?
Yeah, you're audible.
Yeah, actually, from my MacBook, those options were not visible. Like they were not showing those options of share screen.
Okay, okay, I understand. It's okay. Yeah, don't worry.
Sorry.
Mhm.
Yes. Just a minute. Yeah. Sorry guys for this inconvenience. So hello everyone. I am Rupak and I am doing integrated PhD in theoretical physics at TIFR Mumbai. So today I am going to talk about how we could be able to see our universe in her early days. But keeping in mind that most of our audience are just out of grad school, undergrad, so I will be going to keep the mathematical details out of our story as much as possible. Yeah. So our story starts with a simple question. So how can we see our universe? Now the answer is simple: light. Light bounces back from object, and we can see through it. So for that uh, we have put up our arrays of telescope covering all spectrum of light just to scan every inch of the night sky. But the problem is light stops coming from before recombination when universe was 3,883,80,000 years old. So what it means is that we know that the farther the light comes, it tells us about the old that that old time of the universe. But the problem is so if the light coming from the farthest will tell us the farthest in time of the universe, but there is a point after which the light doesn't come to us. And so why is that? So the question is uh, why that thing exists. So let's understand that. So the thing is due to something called Thomson scattering. So what happens is that when universe was too hot, so at that point what happens is that the photons completely gets photons are energetic and they just get scattered from the electrons, and as a result what happens is that the mean free path of the photon gets very much reduced and those photons cannot come to us. And it's basically a similar thing what is happening inside the sun nowadays. So as a result, those photons cannot come to us. But when the universe was sufficiently cooled enough so that these hydrogen atoms were formed, and then when these hydrogen atom were in a very highly excited state, and then they cooled down and by emitting photons, and from that point the photons started free streaming, and those are the first point from which we can get the light to us, right? And so that point we also call CMB and photon decoupling, and that means, and this CMB or cosmic microwave background is the light which we get from all around us. Yes. So so the point being then, to see beyond that point light, we cannot use light. So then the question would be, what would be the medium through which we can see the universe beyond that point? So the answer is gravitational wave. So now if we look at the history of our universe, we get a picture like this, which is very famous picture. And if this being the, as you can clearly see, this being the Big Bang, and this being the recombination, which I am shown in the slide. And then clearly light is not the way to probe this time period of the universe, which is in between these two. Now, like the photon decouples at recombination and creates a CMB or cosmic microwave background, similarly neutrino decouples at a point which has been shown, which is roughly around 1 second after the Big Bang. And similarly, similar principle, and they create something called cosmic neutrino background. So, so from the point of CNB and CMB, that means 1 second after Big Bang to the recombination time, or the 3,80,000 year after Big Bang, this time period can be probed using neutrino also. But before this 1 second time period, when that means when the neutrino gets decoupled, there is no way to probe the universe or to see the universe. So, and at least no conventional way, and that answer would be the gravitational wave, which would help us to see in this time period. That means from Big Bang to this neutrino decoupling time 1 second, and actually in general through the all the time of the universe. So now the question is then how we can use gravity to see those time periods of the universe. So we know that when the universe was hotter and all the forces were unified. Nowadays we have 4 fundamental forces, but when we go back in the history of the universe is much hotter and the forces were unified. Now as the universe cooled down, these forces got separated from each other, and the process was phase transition, and our universe has encountered such 2 phase transitions, which is called electroweak epoch and quark epoch, and which are shown in the slide, and these were roughly around at 10 picosecond and 20 microsecond time. Now at electroweak epoch, strong force got decoupled from electric force, and at quark epoch, weak interaction separates from electromagnetic force. So basically after the quark epoch, the forces we know today start into existence, the 4 different forces. Now the theory is all these phase transition, that means each phase transitions where the forces are getting decoupled from each other, if these phase transition are first order phase transition, then it could be a potential source of gravitational wave. So, and if these phase transitions could create something like gravitational waves, then we have arrays of now current and future gravitational wave detectors, which in principle could detect these gravitational waves. So then let's ask the question, how this phase transition can create a gravitational wave. So now one thing to note here is that like the CMB, which comes from isotropically from the all direction of from Earth, if we see, similarly if these phase transitions would create gravitational wave, this would be also isotropic, and this will come uniformly from all direction towards Earth. And that is one main difference of this gravitational wave from the gravitational wave which we get from the other sources, say by black hole binary mergers and etc. Because those gravitational waves, those are creating from a particular point, and that means those gravitational wave has a directionality. But here, as these gravitational waves will be isotropic in all direction. So this is one thing. So now let us dive into how this phase transition could create a gravitational wave. So for this we need to bring a little bit of PhD. So let's dive into that. So now quantum mechanics had 2 burning problems, which is that how to treat position. So we know in quantum mechanics, positions were operators and time was a parameter. but relativity tells that position and time are basically same thing. So then the question comes that how to treat position and time in a same footing. And the second question which comes is that we have electron and it has charge and mass. But whenever in the corner of the universe I pick a electron, its charge and mass would be exactly same. And which is why? Why is that? So these two were the one of the starting points or which QFT wanted to answer. And the answer becomes that each of the fundamental particles we have, these are basically a field which is extended towards the whole space of the universe. And peak in this field will roughly give us the position of a particle, and thus this can be solved that as electrons are basically coming from the same field, so that's why they carry the same properties, same charge and mass. So for illustration, let's say these wavy like surface, I am representing the electron field, and let's say so similarly mu1 will have some kind of a field. There are all the particles will some field, some have spinless, some will have spin, and etc. etc. And as a result, what will our universe be? Our universe is basically nothing but made up of particles and fundamental particles, and each particles will have their corresponding field, which is extended throughout the universe. So basically our universe would be basically nothing but a superposition of all these fields. So we can, in a diagrammatic way, we can represent by this that all these fields and it's something and universe that constitutes basically our universe. And now these fields will have interaction between themselves, basically, which will say that there is interaction between two particles. That means basically there is a potential energy between these two fields. So here for diagram for illustration purpose, I have shown, like, let's say these two fields have U1 interaction, these two fields have U2 interaction, and there is a U3 interaction, something like that. Now let us plot this potential as the temperature of the universe decreases. So the idea is that as the universe was decreasing its temperature, the interaction between these fields or between these two fundamental particles were changed, and as a result, these potentials were also changed, and potentials were also changed. So how this potential was changed? So idea is that, so let's say universe was this graph, as this all the pictures are going, it is in the order of decreasing temperature. Okay, and so at the initial, the first graph is showing when universe was very high temperature, and we are seeing that the potential has a single minimum, which is at phi equals to 0. So of course this potential is in the previous graph the potential is between the field, so the potential will be a function of phi, which is the field, and so I am plotting here with respect to phi. So it has a minima at phi equals to 0, and that means it has a ground state which will be around this point, around phi equals to 0 point, and then as the temperature decreasing, there is a curve which is coming or reappearing in the potential, and after some point this minima will become similar to the phi equals to 0, and we can see when the temperature was low enough, we are getting a completely different minima. That means the minima has shifted to a non-zero value, which can be seen from the last picture, where minimum is a non-zero value. So what it means that what we are saying that as the temperature of the universe got decreased, the minima of the potential or the ground state of the potential got shifted. Now let us see that what is the implication of this. So the implication is that when the potential, so let's say the left is I am plotting the potential, and the right I am saying what is the value of the field in all over the universe. So this box is saying us the universe in XY plane. I am considering a 2D universe, and the color is saying the value of the field. And so when the potential was universe is very high, so potential had a minima at 0. So basically all the universe had a value phi 0. Now, as the as the potential started gaining a new non-zero minima, so then the field being at that non-zero value becomes energetically favorable. So as a result, what happens is that in this C of phi equals to 0, there are random regions where this phi equals to non-zero value or the new minima pops up. Okay, and as this new minima is energetically favorable, so this region grows because it tries to envelop the whole space into the new minima. So we can see that there is a little bubble. So inside the region there is the new minima, and the outside is the old minima, which is getting squeezed away, and this new minima is expanding because this is energetically favorable. And in the process, so these we can call some bubbles, and these bubbles will expand and then collide and merge, and ultimately finally this all of the universe will acquire a new value for the field. Now so now in this process, as these bubbles are colliding, this is the origin of the gravitational waves, so which is shown here in the curly arrow. So right, yes, so right, so let's think about it, what is happening here. So here, let's see, we are plotting in the first the xy of the universe. Basically, we are plotting the value of the field in the xy plane, and later we are taking a particular cross section or particular direction of this universe and plotting the value of the field in that direction. So initially, all the universe was the potential has only single minima, so all the universe was at phi equals to 0. So if I go across some line, the potential will give this phi equals to 0 line. And then as the bubble started appearing, so let's say there is a bubble appeared, and so if I go across this red line and I see how the value of the field is varying, I would see, of course, that outside of this bubble, the field value is 0, and inside the bubble, a field has a non-zero value, which is roughly equal to the new minima which is going to appear. Right. Now, as the time grows, these bubbles gets bigger. So that means that in this red along this red line, this non-zero value also spreads in the x direction, and this 0 value gets squeezed away, and by that time there is a second bubble also appeared, so that means there is a second maxima. And finally, when all the universe is being filled with the new value of the field, so there's a non-zero value. So now so these are basically rough sketches, but if we actually plot this, we can see that in the first diagram we can see this bubble surface. So as this bubble is expanding, and that is shown in here, and that these lines are at the same bubble. So that means these bubbles are having a boundary where these non-zero value and zero value are meeting at each other, and this boundary bubbles expanding and this boundary is moving, and so this boundary becomes steeper and steeper as the time goes on. And the second plot gives us that so it says that, let's say there are two bubbles which are created at -5 and +5, and so thus this blue region was the value of the old field, and red is the value of the new field. And as these two bubbles were expanded, and then when they started merging or collapsing with each other, then these kind of oscillations started happening, which will create the gravitational wave. So now the point is, so this is all the story. So how do we calculate the gravitational wave? So so what we do is that basically we start from a Lagrangian. So I will just go this part very quickly. So what is happening that for the field we have a Lagrangian, and from that we want to get that how much what is the probability that this field is tunneling from the old minima to the new minima, and then we try to solve this, and then from this from this we try to get, there are three parameters we try to get. The parameters are alpha, beta and k, which I am defining in the next page. And so depending upon what model or what Lagrangian I have taken or what potential I have taken, these parameters alpha, beta and this k will be different. Right. So now let us talk about now. So I can get this Lagrangian. Now what is the spectrum of the gravitational wave that I am getting? So these are the standard expressions of gravitational wave which can be produced. So they are basically gravitational wave tensors, and if I put all of these, and so details I am ignoring, and if we put all these expressions and try to get what is the spectrum of the gravitational wave, and so in that case what we have to do is that we have to consider that multiple bubbles are creating and they are colliding with each other. So we have to numerically simulate it, and then the result we will get, if we fit the curve with the produced spectrum, we would get some results like this. So now there are basically three ways this energy can be produced from these bubble collisions, and so three ways, which are scalar field contribution, sound wave contribution, and magneto-hydrodynamic turbulence contribution. So they have these different formulas, but the main important thing what I want to note is that all these formulas are dependent on, there is a beta parameter, there is an alpha parameter, there is a k parameter, and where this alpha, beta and k are defined in this upper part of the slide. So if I have a model or Lagrangian, from that I can get this alpha, beta, k parameter, and if I have the alpha, beta, k parameter, I will get the spectrum using these formulas. And using these formulas and spectrum, I can determine what is the maxima of the spectrum, or at which point this graph, this intensity versus frequency graph is peaking. For example, here the graph I have shown, here it is peaking at omega is to 0.01 hertz. So yes, so that means that each model will have a signature spectrum. So that is the main important thing I want to focus on, that if I take a different model, I will get a different spectrum, or the maxima at the frequency at which the maximum is appearing will get shifted. Right. So then the point is happening is that, so if this is the case, what advantage we are getting is then in astro-particle physics, or because there are many models, and often this whole high energy region, which we cannot probe nowadays by our particle accelerators, because our accelerators are not that high energetic so that they can probe these models, but we have a range of models, but we don't know which model would be true or not. But here we are saying, if the models will give a different alpha, beta, gamma, k value, and this alpha, beta, k value will give us a different spectrum or different maxima. So if we can detect the gravitational wave and this kind of gravitational wave background, and we can get the spectrum of the gravitational wave background, and if we can get the maxima at which point the maximum of the gravitational wave background is obtaining, from that we can back guess that which of the models we can keep and which of the models we can throw out on this. So that is the main takeaway what I want to talk, why I want to tell through this, that there is a zoo of models, Now, the model interaction will give us a Lagrangian, will give us alpha beta k parameter, and which will give us a gravitational wave spectrum. Now, this observation or non-observation of this gravitational wave will give us the validity of the model interaction. So this will give us a probe to know what is happening there. And third is that this gravitational wave probe is, there's a basically extremely high energy scale, which is very challenging to probe by laboratory accelerators. And so now whatever I am saying, but the point is that so what is its feasibility by detecting the gravitational wave itself? So in this case, which what I want to say is that, so currently we have LIGO, which is ongoing its work, and from since 2015, and it has detected 90 detections and gravitational wave, and its frequency range is around 30 hertz to 7 kilohertz. But this frequency range of these gravitational wave backgrounds are from these phase transitions are generally from 10 to the power minus 2 hertz to 100 hertz, 10 hertz. So there is a LISA, which is upcoming, so and it is going to operate on 10.1 millihertz to 1 hertz. So it has a very good opportunity to very good possibility to detect some gravitational waves from some of the models, and thus by give us a probe to look into this matter. Yeah. So that's what I want to talk about. These are the references, and thank you.
Thank you so much, Rupakda. I guess there's a question in this chat section of Teams. That is, Urjishmanda writes that what is the order parameter in the particular phase transition where the different fundamental forces separate?
What is the order parameter in the phase transitions?
When the different fundamental forces separate.
Yeah. So I think that would be different for different forces, right? But wait, just a minute. Yeah. But the main thing is this: the value of the field is changing, and that I think can be the order parameter in this case. Yeah.
Urjishmanda, if you want, you can turn off your mic and turn on your mic and speak, maybe.
Okay, I have another question. So you said that this phase transition is first order. Now, around a first order phase transition, the first order derivatives of the free energy become discontinuous. For example, the density becomes discontinuous around a first order phase transition between a solid and a liquid. So is there any simple physical interpretation of that thing in this particular phase transition?
Yeah, actually, so the thing is that here we are saying that this, these bubbles are forming and they are colliding each other. So this is basically very similar to how water boils. So when the water boils, that's also a similar thing, right? When this latent heat goes and the temperature goes above it, so there is randomly there is a little pockets of water which transforms to vapor, and then it rises up or it expands. So it's very similar dynamics, and actually we can have this kind of phenomenological calculations, which is very similar in these two regions. Yeah, and another thing I want to say is that I completely forgot what I was going to say. Yeah, sorry. Yeah, carry on. Yeah, I forgot.
Okay, so Rupakda, are you done?
Yeah, I am done. Yeah.
Okay. Thank you so much, Rupakda, for this amazing talk. I guess this will inspire many more people who are into cosmology and stuff. So thanks a lot. I hope you are doing well. We are really proud to have you as a senior. So you have always inspired us. So good luck for your career. for your research.
Thank you. Good luck to you also.
Thank you so much.
Yeah.
Okay, so we'll move on to our next speaker. And the next speaker is also a person who is an alumnus from RKM Narendrapur. Um, he's currently a PhD student at NISER. We welcome Bapaditya Mondol. He is working in the field of high energy physics. And the topic of his talk shall be QGP, the state of a few microseconds old universe after Big Bang. So I guess that will be a continuation from the previous talk. Papada, you can speak now.
Thank you. Can you hear me?
Yes, you are audible.
Okay. Let me share my screen. Okay, can you see my screen? First slide.
Yes, it can be seen clear.
Okay, then second slide.
Yeah. Absolutely.
Oh, okay. And can you see my cursor?
Yeah.
Okay, thank you. Okay. Okay, let's begin. Let's begin with some history of our known universe. Okay, before that, let me draw your attention to something else. Okay, we all currently sitting on a chair, right, in front of a laptop or in front of a cell phone. So please focus on the plastic water bottle that kept in front of you. Okay. Now, if you zoom into that plastic bottle, what you see is nothing but the polyvinyl chloride, right? PVC. Okay. Now, if you further zoom into that, what you see carbon molecule or carbon atom. A similar kind of figure that you can see on the screen also. This red and the blue circles are the nucleus around the electron cloud. Okay. Now, if you remove the outer electron portion of the atom, what you get? You get the nucleus, which contain proton and neutron. You further zoom into that nucleus, what you get? You get proton that contains 3 quarks and neutron that also contains 3 quarks. There are also gluon that binds the quarks that you can see in the. You can see that the white colored spring like structure. These are gluons. So these are the fundamental basic building block of matter that you want to study. Let's focus on the 4 questions written here on the screen in the white marker. Can you see 1, 2, 3, 4? Okay. So throughout my talk, I will focus on the first 2 questions. Question 1, what are we made up of? Question number 2, what is the basic building block of everything? And question number 3 and 4, where does mass come from and why the spin of the proton is exactly 1/2. So this question number 3 and 4 that will be discussed very briefly later. Okay. Now moving on. Okay. To answer the first 2 questions that I have discussed in my first slide, in the previous slide, we have to go back in time. Back in time means 13.7 billion years ago to the origin of the universe to understand what happened just exactly after the Big Bang. Okay, so let's look at the evolution of the universe. You can see at the right side of my slide. So this is, can you see, this is increase in time. You can see this is the time section, the T start from 0 from Big Bang, and then it increases and it also decreasing in time. You see here the temperature is 10 to the power 32, then temperature 10 to the power 28 and so on, decreasing in temperature. Please focus on the microsecond old universe. That means please focus on that particular section. Can you see my cursor? This is 10 to the power minus 5 second. I mean, I'm asking you to focus on that particular region where the temperature is, you can see, of the order of 10 to the power 12 Kelvin. Here you can see here the quarks and the gluons are free, right? They are in a state of plasma that we call quark-gluon plasma. Okay, we want to study the properties of this state, but the irony is that in nature, we cannot find quark-gluon plasma. So our goal, which is written here in the white, in the yellow box, that our goal is to first create a similar state of matter in laboratory and then study its property. Okay, our goal is clear. Create a similar state of matter in laboratory and then study its property. Why? Because we want to study the basic building block of matter that we made up of. Okay. Let's discuss how to create QGP in laboratory. Remember, quarks and gluons are always inside the proton. So to create quark-gluon plasma, we have to take somehow quarks and gluons out of the proton's barrier, right? Now, the million-dollar question is how to do that? How to extract quarks and gluons out of proton? Okay, so please focus on the right side figure. Please focus on that figure. Here you can see a black nucleus surrounded by electron. Now my question is how to free the electron from the nucleus? And the answer should be, it's very simple. You take the electrons away from the nucleus using magnetic field or other processes so that the distance r, the distance between electron and nucleus is very high. That means the U written here minus Ke Q1 Q2. You can see this expression U. So this U would be very small because R is very large. That is how we free the electron from nucleus. It is very simple, right? You increase the distance between the nucleus and the electron, and so that your U becomes 0, and that is how we free the electron from nucleus. Good. But that is not the case for the quarks. As you can see, for the quarks inside the proton, the potential term, which is written here at the left side, you can see V equal minus K1 by R, just like the previous term, plus some additional term K2 times R, where R is the distance between two quarks. Okay, so look, here if you increase the distance, which is R, between two quarks, yes, the first term tending to 0, that is fine. But the second term is not, because it is linearly dependent on R. Remember, in the previous case, you increase just R and the potential tending to 0 for the case of nucleus and electron, right? You just increase R, then the potential tending to 0, and you get free electron. But here in QCD, you increase R, but the potential also increase, right? So we cannot free the quarks. We cannot put the potential exactly 0 at large R. That is a problem. So a similar example that you can see here in the picture at the middle of my slide, that you are stretching a rubber band. Okay. Now more force you put on the to stretch the band, the stronger they become, right? So then the question is, if that is, then the question is how to free the quarks, right? And the answer is yes. Physicists found that if you heat the proton at a temperature of the order of 10 to the power 12 K, then the proton melts and it creates quark-gluon plasma that you want. Remember, the temperature 10 to the power 12 K is the temperature few microsecond old universe that I have already discussed few slides ago. Okay, that means the moral of the story is we need somehow the temperature of the order of 10 to the power 12 K. That is the moral of the story. We need that temperature to create QGP, right? Now our next goal is how to get that much of temperature, 10 to the power 12 K temperature. That is our next goal. because unless you create that much of temperature 10 to the power 12 K, you could not able to create QGP, right? But this is a huge temperature. Can you imagine 10 to the power 12 K? It is about many thousand times hotter than the sun's core. Okay, so this is a huge temperature. Now another problem is that even if you somehow manage to create 10 to the power 12 K temperature, you cannot put ordinary matter on that. I mean, like you put for the case of Bunsen burner. Remember, in the chemistry laboratory, we put some material on the Bunsen burner and tested its property. But here, the temperature is too high, 10 to the power 12 K. So you cannot put just, you just bring some material and put on that high temperature, right? Because at that high temperature, matter melts and also change their state also, right? So what is the solution? How to get QGP? The solution is you put enough energy in a tiny volume. That means your energy density is very large. You got my point. Energy density is E by V. So you put enough energy in a tiny volume. Your V is very small. That means your energy density is large. Now, from Stephen's law, that is written in the white box, can you see EB equal sigma T to the power 4? You can see it, I think. Okay. So if you put enough energy in a tiny volume, your energy density is very large. Now, from Stephen's Boltzmann condition, you can show that energy density is proportional to temperature, T to the power 4. That means if you increase energy density, the temperature also increase. So the idea is put enough energy in a very, very small volume so that your energy density is very high. Remember, your energy density is very high, and we know that energy density proportional to temperature, and that's how we get temperature of the order of 10 to the power 12 K. Okay. Now, what we do, we take 2 gold ion. Gold ion means a gold nucleus that contain 197 nucleon. So we take 2 such gold ion running opposite to each other, and at a very high speed of the order of 0.99995 C, that much of speed, and they collide. The energy density of the collision region is so high that it creates the suitable environment or the suitable temperature to create QGP. Now this process is called little bang. We learned previously the Big Bang. It is the little bang. We are creating the Big Bang like situation in a small scale. Okay. For example, look at the figure at the upper right side. Okay. So you can see this figure I'm talking about, the figure inside the red rectangle or square. So you can see the overlap region. This is the collision region, which is of the order of few Fermi, because we know the radius of a nucleus is of the order of Fermi. So the overlap region, this overlap region should be of the order of Fermi, and we know 1 Fermi equal 10 to the power minus 15 meter. Okay, that means if you calculate the energy density in that region, you see U equal E by V. So your V, volume, the collision region, volume of the collision region is very small. So your energy density is very high, that produce QGP. Okay, that is how we produce QGP in experiment. Below, at the middle of the of my slide, you can see this figure. this is a pictorial presentation of the creation of quark-gluon plasma in laboratory. This is 1, 2, 3, and 4. Picture 1 says the two ion beam, they are about to collide, and then the collision happens. Then figure 3 and 4, you can see the quark-gluon plasma that you want, it is created. Okay. That is how we create quark-gluon plasma in laboratory. Okay. Remember, for the last 1 or 2 slides, I have used the word energy density is very high. I have not used energy is high. I'm repeating. I told energy density is high, but not the energy high. Look the lower section of my slide, the section below the black line. So you can see the energy of the collision between the two gold ion is not high. You can calculate the energy of the collision between the gold atom. It is 197 multiplied by 200 GeV. 200 GeV is the energy of the each ion, and 197, what is the number? It is the total number of nucleon inside gold atom. So if you calculate, if you got the result that it is about 6 microjoule. Okay, so this 197 number is the nucleon inside AU nucleus. Okay, so the energy between the collision of the two gold ion is about 6 microjoule. Now, to get a comparison how small or large this energy is, I have calculated the energy of mid-air collision between two normal mosquitoes, and it comes out, the two mosquitoes colliding. Then I have multiplied 2 times half mass of a mosquitoes and their velocity. The mass is roughly 2.5 milligram, and the velocity is roughly 2.5 kilometer per hour. That's something. So if you calculate the mid-air collision between two mosquitoes, and you found the energy of that collision, you found it is 1.2 microjoule. That means the energy between the collision of two gold ion is not large. It is just about 5 times the energy of the mid-air collision between two mosquitoes. What we do, what physicists do, they pump that much of energy, 6 microjoule of energy, in a very, very tiny volume of the order of Fermi cube, so that energy density becomes very large. Remember, energy density becomes very large because your volume is very low, very small, and the temperature related to energy density, U proportional to T to the power 4, and you get the temperature of the order of 10 to the power 12 K for that small system, and that create the QGP. Okay, so the point is energy density is very large because the denominator, the volume V, is very small because the region is of the order of Fermi. You know what is 1 Fermi? Okay, I'm just giving you some hand waving argument. What is 1 Fermi? Yeah, mathematically it is 10 to the power minus 15 meter. But if you want to visualize 1 Fermi equal, you take one human hair, okay, one normal human hair, and measure the diameter of the human hair and divide it by 10 to the power 10. What you got is 1 Fermi. Can you imagine how small 1 Fermi is? Okay, let's move on. So currently 2 facilities are ongoing that put the energy of 6 microjoule in a very, very tiny volume to create QGP. One is RIC at the left side of your screen. RIC is relativistic heavy ion collider that I am working on, and another is LHC, Large Hadron Collider. RIC uses AU plus AU or gold-gold collision to produce QGP, and LHC use lead-lead, PB plus PB to produce QGP. Okay. Okay, so a few information about, I would like to give you a few information about this collider. First is the magnet. Uh, for a circular path, we need magnetic field, because we have read in 12th standard that you can see this expression QVB equal mv square by r, where r is the radius of that path, v is the velocity, q is the charge, and b is the magnetic field. That means here also in collider, to move the beam or to move the gold ion in a circular path, we need magnetic field, and the normal magnetic field would not work here. What we use superconducting magnets, and for this we use superconducting wire, and that is because lot of heat produced there to produce these superconducting magnets. So we use liquid helium to cool that wire. Okay. Now the next thing that I want to tell you, that why we use gold ion to produce QGP. So remember, when choosing atom, two things to remember. One, the number of nucleon should be higher. What is the number of nucleon inside AU? It is 197. The more number of nucleon, so it is more favorable to produce QGP. So one thing to remember is number of nucleon should be higher, and another, density of the nucleus should also be higher. Ultimate goal is to increase the higher collision probability. Okay, that's how we choose gold. And the money, if you talk about money, how money it cost to produce to establish such project like LHC or RIG, it is about $4.75 billion. Okay. Okay. So that another thing. Okay, let's talk about a new thing. Not new thing. Another thing that you need to know. It is the black hole controversy. What was that? Okay, I'll explain. Before that, I want to read out a quotation of Albert Einstein. You can see on the bottom of my slide. So it is, two things are infinite, the universe and the human stupidity. And I am not sure about the universe. Okay. Let's go to the black hole controversy. Before the RHIC, relativistic hadron collider, began to operation in 2000, somewhere unnecessarily concerned that it would produce black holes that would threaten the Earth. Their claim was simple, that we know after Big Bang, along with matter and antimatter, black holes were also created. They still exist in our universe. So as relativistic hadron collider or LHC creates a similar situation like Big Bang to create QGP, which is called the Little Bang or Little Big Bang, here also, along with matter and antimatter, some black hole will be produced in the lab. And that black hole eat everything around us. But later, scientists proved that there is no such evidence or no such chance for the creation of little black hole. Even if some black hole get created, it would be very small in size and die out by Hawking radiation. Okay. So far, we have discussed how to create QGP in laboratory. Now we will talk about the properties of QGP. Okay, so let's talk about the viscosity of QGP. What is viscosity? It is the resistance to flow. For example, I can say honey is more viscous than water, right? The mathematical expression for viscosity, F equal eta A U by Y, where this mu or eta is the viscosity of the fluid. And one of the most viscous liquid is the pitch. You know what is pitch? Which is used to construct a road, right? Now focus on this figure, on the extreme right upper portion of this figure. So it is an experiment done by Professor Thomas in Australia back in 1927 to measure the viscosity of the pitch. Okay, what he did, he just put some pitch into that funnel and counted number of drops at the bottom. And you know, from 1927 to 2016 or 17, 2020, from 1927 to 2016, I think, almost 90 years, only 9 drops have been found so far. That makes the pitch one of the most viscous liquid ever found. Okay, so let's talk about the other extreme limit. What is the less viscous fluid? Pitch is the most viscous. Now talk about what is the less viscous fluid. The viscosity can be 0 or it has some upper bound. Let's discuss it. You can see the lower this figure here. The Maxwell derived that the viscosity, eta equal 1/3 NPL. I think you know the expression for dilute gas. Viscosity eta equal 1/3 NPL, where N is the density, P is the average momentum of the nucleus, and L is the mean free path. Okay, and now from Heisenberg uncertainty principle in quantum mechanics, we know P times L always greater or equal H cross. Okay, and we also know that the entropy is proportional to Kb times N. Kb is the Boltzmann constant. So if you do a little bit of calculation, you found that this eta by S will greater or equal than H cross by Kb. That means viscosity cannot be 0. Eta by S should always greater than H cross by Kb. That is from quantum mechanics. Now from string theoretical point of view, I have written that KSS bound. This is from string theoretical point of view. This eta by S should always greater or equal H cross by 4 pi Kb, or if you put H cross or K equal 1, then eta by S always greater or equal 1 by 4 pi. Okay, so QGP produced in laboratory has eta by S very close to 1 by 4 pi. That means QGP is the less viscous fluid, that is called the most perfect fluid. You can see in the graph below that the water viscosity is higher than helium, and helium viscosity is higher than quark-gluon plasma. Quark-gluon plasma's viscosity is very, very low. It is the minimum. So it is called the perfect fluid. Okay. Let's discuss another properties of QGP, the angular momentum and the magnetic field. As discussed earlier, two ions coming opposite to each other collide. Let's say this is the collision region. We can see this is, let's say this is the collision region. Okay, this overlap region is the collision region. This is ion A, this is ion B. Ion A is moving in that direction, ion B is moving in that direction. Okay, so in this region, ion A put a force along this direction, right? Because it is moving along this direction, so it put a force along this direction. Similarly, ion B put a force along that direction, in the left direction, right? So the system, the collision region, the overlap region, the system get a huge torque, right? So it start to rotate, and its angular momentum becomes very large, of the order of 10 to the power 7. That leads QGP the most vortical fluid. You know what is the definition of vorticity? It is the measure of the rotation of a fluid, and you'll be surprised to know that for QGP, the vorticity is of the order of 10 to the power 21 per second. Okay. And this QGP is the most vortical fluid ever found, the quark-gluon plasma. Remember, this huge vorticity comes from the torque imparted by the two ions moving opposite to each other. Okay. Let's discuss about the magnetic field. We all know that when a charged particle moves, it creates magnetic field. Now look at the figure, this one, the below the black line, this one. So the two nucleus are about to collide, you can see. Look at the region inside the dotted parallel line, you can see. Look at the region inside this dotted parallel region. That means only this region, just focus on that region. So this is the region that take part in the collision. And the region above the dotted line, I mean this portion and this below this portion above the dotted line, they don't participate in the collision. The nucleons, I mean the protons and the neutrons that don't participate in the collision are called spectators. This is their definition. This highly moving spectator proton creates to the power 15 Tesla, huge magnetic field. So the storyline is that the QGP produced in laboratory is the most vertical fluid, and it has a huge magnetic field due to the spectator proton. Okay. So let's talk about the phase diagram of QGP. When I say the phase diagram, that means more than one phase should be there, like, right? As I have already discussed, after Big Bang, a QGP-like state is produced. After some time, when it cools down further, thousands of hundreds of subatomic particles get produced. You can see this is Big Bang. After Big Bang, QGP is produced here. And when it cools down, it produces thousand numbers of hadrons called subatomic particles, baryon, meson, and all those things. Okay. That means a phase transition occurs from QGP to the subatomic particle state. Look, if I call this is a phase 1, this is QGP. This phase 1 cools down and create phase 2. This is the subatomic particles or hadrons. Before going to the phase diagram of the QGP, let's focus on the phase diagram of water vapor system. You can see the left figure of the red marker, red line. Focus on this particular figure. So this is a phase diagram of water vapor system. We all know on x-axis the temperature, on y-axis it is the pressure. So this this diagram is fully understood, and it is the in the textbook, and you know the vapor cools down to water, and there is a critical point. You can see there is a critical point. Okay, so these things are well understood, right? Now focus on the right side diagram. I mean this QCD diagram. So this is called the QCD phase diagram. On x-axis this is mu b, the baryonic chemical potential. It is number of baryon minus number of antibaryon. On y-axis is the temperature. You see here that the two state, one is QGP here, the QGP, and another is hadron gas, the baryon and the meson. Here QGP cools down and convert into hadron particle. Now the question is, where is the critical point? Like the water vapor system, we know where is the critical point. Now here the question is, for QCD system, where is the critical point? Exactly which T and mu b gives me the critical point. So this is what we are finding. If we find it, then like water vapor phase diagram, this QCD phase diagram would be also in the textbook. Okay. So now to find this, we know that we cannot measure the QGP directly. So what we use the subatomic particle produced after collision. We use basically the net proton moments, their cumulants, to find the critical point. If you ask me why we use moments, because this moments depends on the susceptibility of the system, and susceptibility depends on correlation length. And we know at the critical point correlation length diverges. So from here you can see the moments can be a good tool to understand where is the QGP critical point. Now look at the diagram here. You can see on x-axis it is the collision center collision energy. On y-axis it is the net proton moments, and you see there is a lot of marker inside this figure. Please focus only on the red circle. Okay, you only focus on the red circles, and you see if QGP is there, and if you found the QGP critical point, then this red point shows a non-monotonic behavior, and you see that above 50 GeV on x-axis, above 50, there is a flat dependency, but below 30 or 40 GeV, there are some non-monotonic dependence. So it is some good news that yes, there are some, there is a critical point, but what exactly the critical point, where exactly the critical point, we don't know till now. So we will do further to find it. Now, this is my last slide. There is another facility called electron ion collider that would start running probably from 2035. It is dedicated to find the properties of the QGP, but it is dedicated to find the properties, not the QGP, but the individual quark and gluon. Okay. It would address how the property of QGP emerges from the property of its constituent quarks and gluons. Because, you know, the property of QGP cannot be same as the property of quarks and gluon, individual quarks and gluons. For example, take the case of water, H2O. Hydrogen and oxygen helps to catch fire, but their combination H2O helps to extinguish fire, right? So that means we have to find what is the bridge between the QGP and its constituent called quarks and gluons. Okay, so that's all, and thank you.
Thank you so much, Bapada, for your extremely lucid speech. So, we have one question from the comment section. Is by Ritik. Ritik, can you speak it out?
Thank you.
Yeah, go on.
So my question was, you have presented a slide where you have talked about the gold atoms colliding.
Yeah.
Right?
Yes.
So my question was, that velocity was like 0.995 c. So
yes.
how we can attain that velocity in our laboratory?
Oh,
if you can briefly explain this, it would help.
Yeah, it's a very good question and also very difficult to answer. Okay, can you see my slide?
Yeah, it's showing the colliders.
Yes. Okay. Please focus on that, on the left upper figure. You see the rake star. This, can you see it?
Yes.
Okay. So what physicists do? They first take the gold and remove it electron portion. So now you have gold ion. Okay. So what? Can you see the red color written here? Linux.
Yes.
Can you see? Yeah. This is called the linear accelerator. So what it first do? It takes the gold ion and it accelerates linearly. Okay. So there are two types of acceleration. We can accelerate in circularly and linearly, right? So first it takes the gold ion and accelerate linearly, then eject it in another booster. You can see, write it here, booster, it a very little bit of size, the booster. Okay. Then it ejected to that section and it then boosts its velocity few more, and it then eject the gold ion to another short. It is called AGS. I don't know what is the full form. It then boosts its velocity bit more, and then finally it is ejected in this long collider, 2.5 meter, or I don't know what is the radius. That region. So this is a huge process to attain that velocity. So that's how we reach at that velocity. Okay, there are many processes, 3 or 4 steps to attain that velocity.
Thank you.
Okay. Okay.
Okay. Yeah. Thank you so much.
Excuse me. Actually, I also have one question, but I was unable to send it in the chat.
Yes.
So you said that this QGP is a perfect liquid. So like it has the properties of a Newtonian liquid or a non-Newtonian.
I don't know what is Newtonian liquid or non-Newtonian liquid. When I say the QGP is perfect fluid, the definition of perfect fluid is the fluid whose viscosity is as low as possible. Okay, and it is found that the viscosity of QGP is minimum. No other fluid cannot exceed its range. It is the minimum. It is the base. Okay, that is why we called it perfect fluid. And to know its dynamics that we called about Newtonian or whatever, we cannot use Newtonian dynamics. We have to use relativistic hydrodynamics, because you see all these are relativistic, like that I have already told you that the velocity is 0.999 c. So to understand its dynamics, what is the fluid's dynamics, we have to use relativistic hydrodynamics. Okay.
Thank
Hello?
you.
Yeah. Okay.
Thank you.
Okay.
Okay, I guess the questions are over. Does anybody have any other question?
Sorry for interruption. I have a simple. What could be the implication of finding out this critical point of a QGP? Like, is it, will it associate some sort of, some associated problems? Will it solve or?
Yes. Okay. Can you see my slides?
Yeah.
Yeah. Look, my cursor. This is the critical point that we are focusing on. Okay.
Okay.
So theoretically, it is proposed that the solid black line, you can see my cursor starting from here to the black dot.
Okay.
This line is the first order phase transition. That means the quark-gluon plasma that make a transition along this line, it is called first order phase transition up to that critical point. And if you cross the critical point, you can see the black dotted line. So in that region, the transaction are called crossover transition or ionization. And another thing that you see, if you manage to find the critical point, you see below critical point it is the hadron gas, above critical point it is the quark-gluon plasma, left side of the critical point it is the crossover transition, right side of the critical point it is the first order transition. So it is very, very important to find what exactly the critical point is. You got my point?
Okay. Yeah. Thank you.
Yeah, that's all. Thank you. Any other thing or?
Okay, I don't think there's anything else. Is there anything else by anybody? Any question? Any more questions? Your talk probably generated a lot of curiosity, So there have been so many questions. That speaks volumes about how well you delivered the talk. So yeah, thank you so much, Papada. It was a pleasure to have you here, and we as juniors, feel very proud to have hosted you. So good luck to you in your future endeavor. I hope you bring about laurels for our institute. So thank you again for coming here.
Yeah.
So we'll move on to our next speaker. So our next speaker will be one of our most talented classmates we had at Narendrapur. So this morning has been almost completely from Narendrapur. So he is presently doing his M.Sc at IIT Kanpur. He is working on quantum transport theory, and the topic today shall be on the quantum kinetic theory of. Okay, there's one thing. Before that's a few speakers weren't able to speak today. Okay, so that led to a shifting in the schedule. So please bear with that, and this is to the audience. So yeah, let me start again. So we welcome Shayan Sarkar, one of our most talented classmates at Narendrapur. He is presently an M.Sc student at IIT Kanpur. He's working on the field of quantum transport theory, and the topic of his talk today shall be quantum kinetic theory of spin currents. Sharon, are you there?
Okay, am I audible?
Yeah, you're audible. Yeah, and your screen is visible.
Okay. So my topic is quantum kinetic theory of spin currents. So first of all, I want to motivate you all about the study of the spin currents. So what is that? They found their application mainly in the spintronic devices, which are far more superior than the usual electronic devices we use up to today. Like they have low power usage, and also in these devices we can overcome the velocity limit of the electrons. So that is actually advantageous. And also we can use the 2 degrees of freedom for the spin to carry more information in the quantum computation and quantum information. So that's actually very much so we can say that the spintronic devices are very much advantageous to us, and so we can for the study of the spintronic devices we need to know about the spin currents also. Another thing that is important is the nonlinear regime of the spin currents. Actually, what happens that in some of the systems, it is found that the linear response of the spin currents is pretty low or becomes zero in some instances, depending on the symmetry of the system. Like in some systems, it happens that if in a system we have a time reversal symmetry and the inversion symmetry both present. On that case, the Berry curvature for the system becomes 0, and on that case, the spin Hall conductivity for the or any Hall response like the anomalous Hall conductivity become 0 in that case. But it may be possible that in the nonlinear regime it does not become 0, and on that case we have to consider the nonlinear contributions. So it is also important to study the nonlinear regime of the spin currents also. But in this talk I will not be very much going into the nonlinear regime of the nonlinear response of the currents. I will be simply discussing about the linear responses like the linear anomalous Hall conductivity and the spin Hall conductivity. So that these two are actually the thing I will be discussing more about, this anomalous charge Hall conductivity and the anomalous spin Hall conductivity. So first of all, I want to say that the results I will be deriving here are already have been derived in a different process. My process is actually it is actually a new process. The results are same, but the thing is that my process is somewhat different, and I will be satisfying those results by using this different formalism. So it is the density matrix formalism, and what will be varying in this case is our density matrix. What happens if we take a system, and for that system we actually find the density matrix. This density matrix will be evolving with time because of the time dependent perturbation we give to the system. Like if we have some material, on that material if we apply a AC current, what will happen? What is happening that if we take the frequency of the AC current to be very much small, we can say that it is somehow time dependent perturbation to the system, right? So what happens? We take an unperturbed system and whose Hamiltonian is H0, and we apply electric field perturbation to the system, and so that there is a current flow to the system, and we will just measure that current. Okay. Now there are many processes to calculate this current and corresponding conductivities. But in this process, what we will do, we will find rho for that specific system, which will be evolving with time, and we'll take a trace with this rho with the definite quantity or the current to find the average values. So what we do, we take this quantum kinetic equation, where we just introduce this perturbation in the right hand side, that is EET by h cut dk rho kt, and here we find this H0 in the commutator, which is the unperturbed Hamiltonian of the system, and this tau is the relaxation time. So what we do, this is actually a very complex equation and cannot be treated as a usual way. We cannot find the row as a whole. So what we do, we just divide this row in different powers of different powers of E. E is actually the electric field. Okay, so means I take row as row 0 plus row 1 plus row 2 dot dot dot, where row to the power n is proportional to En, and put this into this equation. And when we do that, we just separate each of the coefficients for e to the power n, like e to the power 0, e to the power 1, e to the power 2. We just separate out those coefficients and take them to be 0. And each of those equations will actually give me this row 0, row 1, row 2, and so on. What is these things? These are actually the different orders of the density matrix, and will be helpful to attain different orders of current there. Like if I want to find the second order charge current or second order spin current, we will be using row 1, we will be using row 2. And if I just want to find the linear response, we will be using row 1. And in the same way, the higher order we use this row, we will find the higher order of currents, or higher order of currents actually. And from that we can find eliminating the E, we can find the conductivity. So the question is how we can use this row to find these currents. The simple thing is that if we have a system, and in that system we want to find some quantity, what we do, we take a trace of the corresponding operator with the row matrix, and like if we want to find the quantity average.
One question. Sorry.
Hello. What?
Yeah, one question means is this row 1, row 2, these are less than the row 0, or your series is convergent?
Yes,
something like.
Yes. Actually, higher the order you go, the contribution will become very much small in the value. Even that in the
electric field, that means the electric field is small.
Yes, if you are treating it as a perturbative term, so you have to keep it very small. Actually, here even on the more than the amplitude, the frequency of the electric field is more important. You can I can give you the implication in the some later slides.
Okay, go ahead.
Okay. So the thing is that I want to find the charge current and spin currents here. So how can you just do this? We will be like if we want to find the nth order charge current or nth order spin current, we will be using this formula, that is the average of Q is equal to average of trace Q row. If we want to find the charge current operator, we have to replace this Q as the charge current operator. And if we want to find the spin current, we have to replace this Q with the spin current operator. Like what is the charge current operator? It is very basic. That is, it is a multiplication of the current charge, that is minus E, and the velocity operator. And for the spin, it is somewhat different. It will be found in a commutator form, that is 1/2 into VA S nu and A plus S nu VA. Will be replace those operators in this formula, that is trace within the trace, to find this currents. And we'll be using this rho n with respect to our choice, that what order we want to find the currents. Like for the nth order, we will be using rho n here. So that's the main idea for getting these currents. Another thing that is important, that if we just see the indexes here, for the charge current I have one index, and for the spin current I have two index. So what is that? What is this difference? In the charge current, we are just calculating the flow of the attribute charge, and for the spin current we are calculating the flow of the spins. So just what is happening in the operator, we will be for the spin currents, we will just replace this minus E with the spin. and spin have a specific direction, spin may be aligned along the z direction, x direction, or y direction. So based on that, we will have two indexes like j for the spin current, where a will give the direction of the flow of the electron, and s nu will give the direction of the alignment of the spin of the electron. Like if we so it will have a two index here. So now I will just introduce how we can how this anomalous Hall conductivity is coming. It is this anomalous Hall effect is actually very much similar to the Hall effect, but the thing is that here we don't need any magnetic field, like so it's actually coming from the spin orbit coupling present in the Hamiltonian or in the disordered potential we are giving. Here we are using here we are finding the intrinsic anomalous Hall conductivity. So basically our spin orbit coupling will be present in the Hamiltonian directly, and the disordered potential will not have any spin orbit coupling term. So in that case, what we will do first, we first have to find the spin Hall current, and after finding the spin Hall current, we will just eliminate the E part and we will get the conductivity, just like we do in the linear cases. For that, we first have to find the velocity, as we have seen in the before slide, where we have used VA. This velocity operator is present in both the cases. So first of all, we have to find the velocity operator. So for that, I will be taking a two-band system, where the lower band is given as have an index m, and the upper band have an index p. On that case, if we want to find the velocity operator, how we can just do that? The velocity operator we know is given by del h del k. Del h del p, and this operator we will be taking the average in both sides of p and m eigenstate, and after taking the average value by taking the eigenstates on the both sides, we'll get this VMPA, this matrix element. This matrix element will have two parts. The first one is actually the very simple part we use in the linear case. Not linear case. We found actually giving doing the derivative of the eigen energies with respect to the momentum operator, that is h cut k, and it is actually this first part, that is this VM0A MP, is actually the diagonal matrix. If we diagonal matrix element, like if this m not is equal to p, then it will be 0. And this second part is very much important. It is the interband velocity term, and it is the interband velocity term, and it remain finite for m not is equal to p. This interband velocity term is very much important because it is the main reason why we are getting this Hall responses in the system. So and it is and by using this using only this part, we can arrive at the result for the anomalous Hall conductivity or anomalous Hall current we can measure. So what we will do, in the first in the before slide, I have given this formula, if we want to find the average of Q, we will be taking a summation of MP, QMP, rho MP. That is actually the trace formula of the trace. If we just see, if you see very carefully, so we will be replacing this QMP with the only this part, this interband part. This will be enough to give us the Hall response of the system. Hall response means we are giving electric field in a direction and finding the charge in some perpendicular direction, right? So why, and that's why we are using this interband term to give us this result, because this thing is R is actually the non-abelian Berry curvature. And and when we take the commutator of two Berry curvature with Berry curvature with different indexes like RMPA and RPMA, we will get the Berry curvature in our system, Berry curvature in the system. So, and that is actually that's actually have a two index, that's x and y, and they will they will actually give the Hall response for the system. Okay. So what we'll do for getting the value of this, for getting the expression for this charge Hall current, we'll be just replacing QMP with this I omega RMPA, and putting the value of rho MP1 we have derived from the quantum kinetic equation I have given before. We'll arrive at a point where we will find the spin Hall conductivity, the anomalous Hall conductivity as this. This sigma n is actually the sigma n is actually is the band resolved conductivity, that is for a single band we are finding. No, if we want to find it for the mth band or pth band, we will just replace this n and n with the m and p. And it's actually a satisfying result, and you can find it in any reference you use actually. This is the spin Hall conductivity. We will just do the same thing we have done before. Just the operator will be as the operator is different. We just replace this VA with I omega RMPA, and we will use this in this formula and we'll use this rho 1 as we are seeing at the linear Hall response. So so we will get this charge Hall current having this expression. And in this case, I have to say that if we just take the relaxation time tends to infinity, like if there is almost no collision in the system, and also the frequency of the electric field we are giving is actually very slow, we can arrive at this expression. If these conditions are not satisfied, we will not get this simple expression for the Berry curvature. It will not come, because as you know, this Berry curvature is actually a commutator of this RMPS. And if we just don't simplify our expressions with this tau tends to infinity and the small frequency limit, we cannot find out this expression for the spin Hall conductivity. So that's actually actually very mathematical. But the thing is that these expressions are satisfying with the results coming from the known theories. Okay, means my process is somehow different, but the thing is that it is giving satisfactory results. So what we do next, we will take a simple example here. Okay, so this is actually the Hamiltonian for the system we are taking. It is a 2D material, and this material is actually the monolayer MOS2. Here we can find the spin orbit coupling term. You can find this there is a SZ, this is a spin operator, and sigma z. These are the spatial operators here. The sigma x, sigma y, sigma z are actually the Pauli matrices here. If we just see this Hamiltonian, we can say that we can just show that this Hamiltonian will have the eigenstates having the spatial part and the spin part separately, and the spin part will be actually proportional, actually the eigenstate of the SZ operator. SZ means the spin operator, the spin Z operator, and this spin Z operator will have the eigenstates what this spin up operator or spin down operator that having their eigenvalues as h cut plus h cut by 2 or minus h cut by 2. These tau terms are actually given to the value for the system, corresponding to the value for the system. The +1 or -1, they can have their values like this, and the rest of the terms are not important for the concept actually. What we do for this system, we actually find if we want to find the spin Hall conductivity, what we have to do. In the beforehand we have find that expression for the spin Hall conductivity. For the derivation of that, we need three terms, that is Fm, omega m mu a, and S nu. as the system has as the system I have taken has a eigenstate which is the eigenstate of SZ operator. So it will have some value like h cut by 2 or minus h cut by 2 depending on the spin direction. Like if it is along the plus z direction, it will have a value of m bar plus h cut by 2, and if it is in the minus if it is in the spin down state, it will give us the minus h cut by 2 value. Okay, this omega m BA, this Bailey curvature can be directly derived from this Hamiltonian. Okay, this is actually a very tedious job to do this, but okay, we can find that from this Hamiltonian directly, and we can see that if we have a spin up electron, we can have SZ as plus h cut by 2, and if we have spin down electron, we have minus h cut by 2. So H0 is different for spin up and spin down electrons. So this and as we are finding this omega from this H0 directly, so our omega will be different if we have spin up electron and spin down electron. It will be actually the spin down electron, and this FMs are actually the Fermi Dirac distribution. No, sorry, the Fermi density distribution for the mth band. So as we are finding the spin hole conductivity for the conduction band, we'll just use this replace this index of m with the c, and for the spin up electron and the spin current, which is for the spin up electrons, will be this first part, that is by E by 2 into Fc omega c plus 1 omega c spin up yx, and for the electrons which have their which are in the spin down state, we'll have the conductivity like this. The second part, E by 2 into Fc omega c spin up yx, and we just take minus. This minus term is actually coming from the minus h cut by 2 we have given when we put this here. Actually, we are finding the conductivity for the spins directed along the z direction, and as they have two states, that is the spin up state and spin down state, we just take these two values for spin up and spin down, and as the spin down has minus h cut by 2 value, we will get the second term to be like this. This will be actually spin down. It will not be spin up. It will be spin down. And after that, putting the values for the omega and Fc, we will get this type of expression, which is actually satisfying the result. We have taken when I have studied those things, I have followed some papers, and there was this result was given on that paper, and this is actually the satisfying. So this is the simple summary we have done up to now. We have taken an unperturbed system. We give a weak electric field perturbation. We use the quantum kinetic equation to give us the density matrix for the evolving density matrix for the system, and from that we will use the formalism to find out the value for the expression of the anomalous charge hole conductivity and the anomalous spin hole conductivity. The excitation about this thing is that it is nothing but a different formalism used for getting the same expressions we have derived up to now from the known theories. So the thing is that I know it is not very interesting to get these mathematical terms here and there, but the thing is that they are giving us a satisfactory result, and that can be used for the nonlinear regime. And so the future scope is that we can use the same as our formalism is somehow giving us the satisfactory result. We can use it for the nonlinear regime of the spin currents also, and we can find from there, we can predict new formulas or new phenomena from there and new currents from there. That's all. And these are some references I have used for my used when I have studied these things. And thank you. I will take questions now.
Okay, so do you have any questions? I don't think there is any. So people will get back to you if they have. So thank you, Shayon. Thanks a lot for your talk. It's been a great pleasure, like to hear from you after a long time. So
Thank you.
yeah. So good luck for your whatever you'll be doing. Good luck for your career, for your research. And I guess that's it. Take care.
Thank you.
Okay. So we'll move on to our next and final talk for the intermission period. So we welcome. Okay, this is another classmate of ours, probably one of the most studious classmates we had, or the most. I don't know. So we welcome Nilachal Chakraborty. He is currently doing his M.Sc from IIT Gandhinagar, and he is working in the field of quantum optics and open quantum systems. And he'll be delivering a talk on periodically driven open quantum system. Nilachal, please come in.
Hello, am I audible?
Yes,
Hello?
you are audible. Yes, you're audible.
Okay. Yes. I will share my screen.
Yeah, sure.
Is the screen visible?
Yes, absolutely. Please go on.
Yeah. Okay. 1 minute. Is it in full screen mode? Hello?
Yes, absolutely. Yes, absolutely.
Okay.
Yeah.
Thank you, Alekho, for giving a introduction, and thank you
Always my pleasure.
Thank you all our batchmates for arranging this talk. So I will today I will deliver a talk about periodically driven open quantum systems. So open quantum systems are very much studied in quantum optics and field of quantum information. So I will talk about today what will happen when we drive a open system periodically with a periodic drive. So mostly I will deliver, or I will talk about the formalism. So let's begin. So I am a M.Sc student at IIT Gandhinagar, and I am doing my project in quantum optics, and this is supervised by Dr. Prasanna Venkatesh. So what is the plan of my talk? First to talk about the motivation for this project, then the basics of Floquet dynamics, means the periodically driven system dynamics, and then to talk about the quantum many-body rate equation for a non-interacting gas, and some of the works I am doing in open Floquet system, and then to summarize my work and what are the future scope. So let's begin. What's the motivation for this project? So recently it was found that a periodically driven ultra cold atomic system, what is in a 1D optical lattice, that can be described by the very known tight binding model, and this is attached to a bath that is made up of a 3D Bose-Einstein condenser that shows a driven dissipative non-equilibrium BEC steady state. So what is a non-equilibrium steady state? So in an equilibrium steady state, the transition rates between the states depend only on the temperature, but in non-equilibrium steady state, more parameters come in the transition rate. So our research problem is, we would like to consider a similar system with a drive-hand dissipative system, but with a quasi-periodic lattice AH model. That is a very known model for a quasi-periodic lattice, and to demonstrate a possible non-equilibrium Mott insulator phase to superfluid condensed phase transition when we tune the quasi-periodic potential. So that's my research problem. So I will now talk about some basics of the Floquet dynamics. So if we start with a Hamiltonian HT that is periodic, like HT is HT plus capital T, where T is the time period of the Hamiltonian, then simply from the Fourier series we can write the HT as this: m equal to -infinity to infinity hm e power im omega t, where hm are the Fourier modes, and that can be written as like hm equal to 1/2 pi -infinity to infinity ht e power minus m omega t dt.
And if psi is the eigenkette of the full Hamiltonian HT, then the simple equation can be written as like this: I HT ddt of psi t equal to HT psi t. So now what we will do, we will define a periodic unitary operator UFT such that if when it operates over a state psi ft, it gives a full state psi t. And psi ft can be written like that, UF dagger t into psi t. So now, as we know from the time dependent Hamiltonian HT, that between two time t1 and t2, the unitary operator can be written as like this: tau times exponential minus I t2 to t1 integral ht dt. For a time periodic Hamiltonian, this u t1 t2 will remain invariant under the transformation when t1 t2 is changed to some t1 plus n times capital T and t2 plus n times capital T. So using the basic properties of the unitary operator, that u t naught plus nt comma t naught, that can be written as, sorry for the mistake, it will be u t naught plus t comma t naught whole power n. So now what can we define? We can define a unitary operator within a period, that is from if we start with start a system from t1 and evolve it to t2, and there is an initial gauge t naught, and the system is up to t naught plus nt, we will define a unitary operator that is u t naught plus t comma t naught, that can be written as exponential minus hf t naught t. That hf t naught hf, that is depending upon the initial gauge t naught, that is the Floquet gauge, that is the Floquet Hamiltonian, and that depends on the hf, that the initial gauge t naught. So now this formalism, what we are doing, we are writing the total unitary operator between t1 to t2 using the Floquet Hamiltonian HF. That can be u t2 comma t1 can be written as u t2 comma t naught plus nt, and within the stroboscopic period it can be written like that: exponentiation of this minus IHF this into u t naught comma t1. So why we are writing this? Because this HF is giving us the evolution that is the stroboscopic time between the periods, and that u are the that we know between the times. So now we will define a micromotion operator. So that micromotion, if we define a micromotion operator p t2 comma t naught like this: u t2 comma t naught into exponentiation of I HF t2 minus t naught, then we can write the micromotion using this micromotion operator. We can write the full u t2 comma t naught like this: p t2 comma t naught into exponentiation this and p dagger t1 comma t naught. And now what will we do? So after defining this micromotion operator that gives us the stroboscopic evolution between the periods, we will define a key operator k. Okay, so k, if is defined like this: p t2 comma t naught is exponentiation I k that depends on initial gauge t naught into t2. So now if we have a time dependent Hamiltonian HT, so we can construct a Floquet gauge, Floquet Hamiltonian HF that depends upon the initial gauge t naught like this: HF t naught equal to p dagger t2 comma t naught ht2 p t2 comma t naught minus I times this. So this is something like a frame change, and we can do the inverse transformation or the inverse engineering also, that we have a HT that is dependent on time and we have to construct the HF. Now what will we do? We will define a key operator k that is depending upon time t, and we will construct a HF that will totally independent of the time. What we construct earlier, that HF, that is a Floquet Hamiltonian that depend initially on the time gauge t naught, but now we will constructing a HF that is totally independent of time, that and we can write HF like e power I k t naught into HF t naught, that is HF t naught is depending on the Floquet gauge t naught into e power minus I k t, where the key operator is defined like this: that p t comma t naught, that is the micromotion operator we have defined earlier, that is p t comma t naught is exponentiation I k depending upon t naught into t, and that can be written as like exponentiation minus I k t into e power I k t naught. Okay, so we have defined the Floquet Hamiltonian first. that we have a ht that is dependent upon the time. We have constructed a hf t naught that depends upon the initial gauge t naught. Then we construct a hf using a key operator that is that does not depends upon t. So that's our construction. So the Floquet Hamiltonians and the key operators that we have defined that sometimes cannot be written like in a closed form. So to write in a closed form, we have to use some expansion. That expansion are called Magnus expansion and inverse frequency expansion. Why inverse frequency? Because we are using the inverse of the frequency to as a expansion parameter. So the terms, first few terms of this expansion I have written, that terms are simply like the Dyson series. Okay, so first term hf naught, that can be written as like the one that simply the time average of the ht, and that is 1 by t integration of t naught to t naught plus t ht dt, that is h naught, where h naught is the that we have that the first Fourier mode where we have written the ht as the summation over hm e power im omega t, and that the next thing is the hf1, that is this integral that is a double integral with a commutation between ht1 and ht2, and in terms of Fourier mode that can be written as like this 1 by l hl commutation of hl h minus l and e power this, where this hl and h minus l are the Fourier modes of the ht. And we can also expand the kf, that the key operator, that is by definition that kf 0th term is 0 and kf 1th term can be written like this in terms of Fourier mode, that is 1 by h cut psi summation over l hl e power I psi t minus this by l. So and also we can write the effective term or the that does not depends upon t in this expansion, where the first term of the hf effective 0 is h0 like the previous one, and effective 1 in terms of Fourier mode can be written like this 1 by h cut psi summation over l equal to 1 to psi commutation between hl and h minus l, and the k effective term, the 0th term is 0 by definition, and 1th order term is 1 by I h cut psi summation over l e power il psi t by l hl. So after discussing some basics of the Floquet system, I will discuss the quantum many-body rate equation. So to talk about the Lindbergh-Master equation in the interaction picture, so you can find in any non-equilibrium statistical mechanics or quantum optics book that how to write the Master equation. There you will find that you have to do some approximation that are called the Born approximation and the Markov approximation and the full rotating wave approximation to write the Master equation, and after this you can change it to a interaction frame that can be written like del rho del t, where rho is the density matrix of the operator with the I minus I commutation between a h and rho, and a dissipation operator d in rho d, that is a function of rho. And in interaction picture you can write the Lindbergh-Master equation in that form, where ddt of rho is dissipation operator of as a function of rho, that can be written as like summation over rj rij into some lij rho t lij dagger minus half of this anti-commutation between rho and lij dagger lij, where lij are the outer product between I and j, and rij denotes the transition rate from eigenstate j to eigenstate I. And these we have assumed that tau s is less tau r, where tau s is the evolution time scale in system, and tau r is the correlation function decay time in reservoir case. And if you take the trace of this equation, then the probability rate equation can be written as like pi dot t is equals to summation over j rij pjt minus rji pit, where pi is the just the diagonal element of the row matrix, that summation this is the matrix element, and we will denote our Bath Hamiltonian, that is in open system what we do, that there is a system, there is a bath, and there is some interaction between the system and bath. that we does not consider in closed system, that interaction. So that's why we will consider first the system Hamiltonian, then the bath Hamiltonian, and there will be some interaction Hamiltonian between the system and bath. So we are assuming the bath Hamiltonian as some collection of the harmonic oscillator that can be written as summation over alpha h cut omega alpha b alpha dagger b alpha. And the system bath Hamiltonian operator can be written as in that form, that some operator v and summation over c alpha b alpha dagger b alpha. Okay, so b alpha and b alpha dagger are the creation and annihilation operator, and the v operator in the system bath interaction Hamiltonian is the coupling operator. Okay. So the rates Rij, what I have written earlier in the Lindbergh-Master equation in interaction picture, that rates can be written as like Rgi summation over minus infinity to infinity Rgi m, where Rgi m can be written in like the using the Floquet-Bon-Markov approximation, like the golden rule, using the golden rule, where Rgi m is 2 pi by h cut Vji m square, where Vji m what we have written in Fermi golden rule also, these are the matrix element times the density of state, where this G is dependent upon the change in energy epsilon j minus epsilon I minus m h cut omega. So this m h cut omega is coming due to the drive that is given to the system, that due to the drive m number of quantas are absorbing, so that's why m h cut omega comes. Okay, and Vji m now in our simple case, that Vji m is the simple matrix element, but this time we have to integrate over this, that 1 by t integral over 0 to t e power I m omega t, that's the matrix element gt. V is the coupling operator, it dt, and that ge, that's the bath correlation function, and that can be written as something like je by e power b minus 1. That je are the spectral density function, and that is some summation over alpha c alpha square, that depends upon delta e minus h cut omega alpha minus delta e plus, sorry, it will be plus h cut omega alpha. And okay, and another important thing, that's the total flow of energy flux from system to bath. That quantity is important, that is qt, that is here it will be summation over I, j and m, and that is the energy difference into the rate at which the transition occurring into the probability. Okay, so that is the epsilon j minus epsilon I minus m h cut omega into the Rgi m is the rate, and PID is the probability at which this transition are happening. So this Lij, that's are the jump operators in many body version, that can be written as ai dagger aj. And if we write the many body version of the Pauli-Master equation that we have written in the single particle form previously, then it can be written as like Pn dot t, that is summation over Ij. This will come, that thing inside the third bracket that was there, Rij Pn Jit minus Rgi Pnt into 1 plus sigma nj into ni. So this sigma, this is due to, if sigma equal to 0, then the single particle form will come, and this sigma is for Bose case, this will be Bose enhancement, or for fermion case, this will be fermionic exclusion. So Pn is that n rho dagger n, and the total energy flux for a periodic drive for a many body system, that can be written as like this now, summation over m, summation over Ij. That is the similar thing, that the energy difference epsilon I minus epsilon j minus m h cut omega into Rgi m, that is the rate at which the transition are happening, into that thing are the coming due to the many body version, that expectation of ni as a function of t plus sigma time expectation ni ij as a function of t. So now what the Hamiltonian we are using as a model. So we are using the known tight binding chain with the drive given at a particular site m. So that is ht, the is some minus j is the tunneling parameter, summation over L equal to 1 to m, Cl dagger Cl plus 1 plus its harmonic conjugate, this is the tight binding chain, plus gamma omega j cos omega t Cm dagger Cm. So this gamma omega is the strength of the period, strength of the drive, and Cm dagger Cm, that are the on-site annihilation and creation operator, and the system is coupled to a heat bath where the coupling operator is given like that. V dagger is gamma times C1 dagger C1. That is the bath is joining to the system at the site 1, and the single particle eigenstate for this Hamiltonian is the I where I runs from 0 to m-1 that are delocalized. Okay, and the eigenstates are described by the wave function, that is the overlap between L state and I state, that is proportional to sin KIL, and the energy eigenvalues are the EI is equals to minus 2j times cos KIL. So to solve the problem or to solve this model, we will mainly use three kind of solution. That is, one is Monte Carlo simulation, second one is mean field theory, and the third one is augmented mean field theory. So in mean field theory, what we will do, just to write the expectation in terms of its mean value, that is the rate equation, time evolution of the mean occupation, ddt of ni bar t, that is actually that is trace of ni into rho t, and since rho is only dependent on t, so ddt will be upon rho. And if we do some calculation, then it can be written as in this form: rij into nj bar t plus sigma times ni nj t, and rji ni bar t plus sigma times ni nj as a function of t. And within mean field approximation, we will approximate this expectation of ni nj as a function of t, like ni bar t into nj bar t. And then it will simply comes down into that form, ddt of ni bar t, that is equals to rij nj bar t into 1 plus sigma times ni bar t minus rji ni bar t into 1 plus sigma times nj bar t. And what we will do in augmented mean field theory, actually I have not written here. Augmented mean field theory, we have considered the write the ni is equals to ni bar plus some some terms like epsilon, and that's it, that's the fluctuation, and we will get the linear equation for this, like the mean field one, and for the fluctuation also. That's the thing. Now, after knowing the basics of the Floquet system, and also to how to write the rate equation, quantum many-body rate equation using the Lindbergh-Master form in an open system, we will come to our problem. That is a system where the system is modeled by a tight binding chain, where that is H0 system Hamiltonian, that can be written as summation over j, I runs from 1 to m plus 1, ai plus 1 dagger ai plus ai dagger, that is harmonic conjugate, that can be in diagonalized in that form, summation over k epsilon k bk dagger bk, where epsilon k are the quasi energy modes, j is the tunneling parameter, and m is the number of sites, and bk dagger is the overlap between psi k and I, with a summation over I ai dagger. And the modes are like this: summation overlap between I and psi k, that can be written as with a normalization factor into sin ki, and eigen energy epsilon k are the minus 2j times cos k, where wave vector k is this n pi by a times this, where n runs from 1 to m. And this system is given a periodic drive at a site L, where HDT is in a simple form like this: a times 1 plus cos omega t, L dagger L. And now comes to the Bath Hamiltonian. That Bath Hamiltonian is something written like summation over q EBQ, that beta q times beta q. I will not discuss much about the Bath and system Bath interaction in this talk, because I have not done the open version till now. And the Pauli-Master equation for this system can be written as like Pn dot t is summation over alpha beta 1 plus n beta times n alpha into that thing that we have done previously. I have talked about this, how to write the Pauli-Master equation for that. And the thing that's the important are the transition rate. The transition rates are written like this: 2 pi gamma square by h cut summation over k summation over ij vi alpha beta k star into vj alpha beta into this wij and that depends upon the energy difference, where V, I, alpha, beta, that's are the matrix elements of the coupling operator, and the states are now the Floquet states, that's are U alpha depending upon T. And coupling operator, we are taking the coupling operator as a number operator, and this number operator in a single particle form can be written as like the outer product of I and I. So that's why that is U alpha T, the number operator is outer product I and with I. So that is the inner product of U alpha T with I, and again I with U beta T, and integral over 0 to T e power I k omega T dt. With a 1 by T, that's the matrix element. So we have to write the transition rates because these are the important. So to write the matrix element, the major thing is to write the Floquet modes U alpha T and U beta T, and we have to use the concepts that we study in our basics Floquet dynamics. So that's I am now doing. The equation of motion for the mean occupation number is also this ddt of n alpha bar t, that is summation over r. That's I have discussed earlier how to write this. So the thing important is to write the Floquet modes U alpha t. So how to write that? We have to U alpha t is some U f dash t operating over the U alpha tilde. So what is this U alpha tilde? U alpha tilde is the eigenstates of HF that I have told earlier, that we have a HT that is depending upon T. We have to construct a HF T naught that is dependent on the initial gauge T naught, and from this we can construct a HF that does not depend upon T. So the eigenstates of HF are the U alpha tilde. So first we have to write HF using the Magnus expansion, what we have told earlier, and now we have to multiply it with the UF dash T, that is an operator, with this U alpha tilde to get the Floquet modes U alpha T, and we have to just put in the rate equation, that the matrix element and the rate equation to find the rates. Because why the rates are important? Because if we know the rates R alpha beta, and if we put it in the equation of motion for the mean occupation number, we will get to know how n alpha t will vary with t. So that's I am doing now. First, that I have this calculation is not correct, but I have done previously, because I think that HDT can simply written like that cos omega t can be written like this, and we can simply know what are the different HL, but this is not the case. The thing is, now I am doing that. We have talked about the Magnus expansion, but this Magnus expansion has a convergence condition. This convergence condition has to be satisfied by the Hamiltonian of the system to write the Magnus form. If it is not, then we have to go a rotational frame using a transformation, and then we have to do the Magnus expansion. So that thing I am doing, that calculation I am doing now, and since I have not completed the calculation, so I have not put it in my slide. So in summary, I have talked about the basics of the Floquet dynamics. Then I have write the many body rate equation and how to write the transition rate using the Fermi-Golden rule. And then I am trying to reproduce the results for a tight binding model with a periodic drive. So some of the future works I want to do is to reproduce the result properly for the tight binding model, and to see the variation of the mean occupation numbers with different parameters, how n alpha t is varying with t or k, and can we see the Bose-Einstein condensation in this picture also. And then my next aim is to change the tight binding Hamiltonian with the AH model Hamiltonian in a quasi-periodic lattice, and to see the eigenstates are localized or delocalized, and to see also the quantum phase transition from a Mott insulator state to superfluid transition. So that's all. Thank you. Is there any question? Hello.
Thank you so much, Nilachal. I don't
Hmm.
think there are questions. Just let me check the YouTube chat. Nope, I don't think there are any questions. There are any? Is there any question? No, I don't think there is. So
Okay.
the speakers can get back to you, not the speakers, like the audience can get back to you, I guess, after once we are done with these things.
Hmm.
So thank you, Neelajal. Again, it's been
Hmm.
great hearing you after such a long time. You have put in a lot of hard work. Thank you so much. Looking forward
Hmm.
to more such interactions in the future. Okay,
Thank you.
so
Thank you.
yeah. Okay. So this is a notification to the audience that we'll take a break now. We'll take a break now, and we'll come back at 2:30 p.m. in the afternoon. Okay. So we'll have more interesting speakers in the second half. So I hope that you'll enjoy the next talks as well. We take a break right now. You can leave. Please come back at 2:30 p.m. Same link. Bye for now. Yeah, just I need to check. I'm audible, right? Can someone please confirm?
Yes, I can hear you.
Okay, okay. We'll start our meeting in a few minutes, okay?
Sure.
2:30, I guess. Okay. Hello and welcome back to Young Physicists Meet 2022. We are really glad to have you all after the break. Um, Now is the last part of a 2 day online conference that we are having. And I must say that your overwhelming appearance and the response has really been, great news for us. And it shall be very encouraging for all the viewers of this show who are wishing to pursue research in the future. The next person on our list is yet another RK Narendrapur alumnus. His name is Rothindranath Das. He's presently a PhD student at Julius Maximilians University at Würzburg, Germany. He works in the field of quantum chaos, and today he'll be delivering a talk on the complexity of detecting quantum chaos. Rothinda, the stage is yours.
Thank you very much. Let me share the screen. Please let me know if you can see the screen.
Sure.
Okay. So, hello everyone. Thank you very much for inviting me to.
Yes, sir. Are you sure?
Yes, I'm showing the screen. Can you see it? No?
I don't think it's visible, is it?
Okay.
I don't think it's visible.
Cannot see presentation.
Yeah, your presentation isn't visible.
Wait, then I have no idea why. Sorry. Okay. I'm sharing, but so what can you see? You can see nothing?
We can see you.
We can see you. Yeah, you and.
Okay, yeah. Then let me just disconnect and connect again. Sorry.
Sure.
Okay. Is it visible now?
Yes, a screen is come. It came and went away, I guess.
I don't know what's the problem.
Are you having a network issue on your end?
No, there is no network issue, but I think there is some problem with the screen sharing.
Your screen came back again and went away. That's the problem. It just came back right now and went away again. It's happening the same. It's the same happening. Like it's coming. A black screen is appearing and going back.
I have no idea what's happening. Okay, then let me quickly join from a different device altogether. Sorry.
Yes. You take your time. No issues.
Can you see it?
I'm sorry to say, Rutin, I just where it happened the same again. It appeared and went back. Like it's okay. I mean, if you are having problems, you might try doing it later on. I don't know.
I think that should be something. If the next speaker is available, then you can go with him.
We are looking for some new speakers who might be ready right now. So I request our viewers to like wait for some time.
Can you see the screen now?
Yes, finally. Can you see?
We can see it.
Okay. Sorry for the delay.
It's okay. Thank
Okay.
you.
Okay. Thank you very much for inviting me to this conference, and it's my pleasure to give you this talk. And it will be a brief overview of what the current community is doing on quantum chaos, and I'll be talking about two specific things in general, like OTOC, out of time ordered correlations, and the complexity. But I will mention at some points when there are some other interesting things in this, but that cannot be covered in this talk, that I'll mention at certain points. Okay, so the contents will start with the motivation, why quantum chaos, why anyone cares about it at all. And then there is this thing that to understand this, we'll need some basic understanding of the system. There comes integrability and what is beyond that. Then I'll talk a little about the OTOC, two-point correlation functions. And then I will talk about some relevant timescales that are important in the system. Finally, I'll go to the complexity, and then I'll say if this is enough, and then I'll have some other advertisements. Okay, so let's begin the talk, as I'm already kind of lagging a little. So classical chaos is kind of well understood. It has many descriptions in the sense that there are many probes to study it. But the main idea here is to study if the system is sensitive to the initial conditions. And the few other things that I mentioned are something that are termed as topologically transitive and dense periodic orbits. So the things that are read in this presentation, I will not talk about them, but they're interesting. I am just mentioning these things. If anyone wants to have a look at them, one can just Google it or ask me a question or talk about it later. But these are just for completion of this topic, but this will also not be relevant for this talk. So I'll not go on explaining them, the things that are in red. So in classical chaos, nonlinearity plays a big role because as you see that sensitivity to the initial condition is important, and this happens very often when your system evolves under an equation that is nonlinear. So this kind of nonlinearity is important, but in quantum mechanics, we know that the systems evolve with the Schrodinger equation, and Schrodinger equation is linear. So with that thing in mind, there is no exact classical analog of chaos in quantum mechanics. So in that sense, there is no scope or hope in that sense that if we want to say that I know there is classical chaos, I want to find the exact analog in quantum mechanics, we may never find. But then why we are interested in quantum chaos at all? Because there are some characteristics of quantum systems that behave like chaotic systems that kind of gives the idea that there is some kind of chaos in the system, but that is not exactly what you would get in a classical system. So that is why quantum chaos is by definition inherently different from classical chaos. And there are some signs that kind of tells us that this is a thing. So the signs that are there are like two-point correlation functions, out of time ordered correlations, complexity, spectral form factor, level spacing statistics, and etc. I will not talk about the last two things, but these two things are itself very interesting. I mean, all of them are very interesting, but these two things are being used in very different contexts, but if I would include them, this talk would be very long. So, but if anyone is interested in this topic, they also may go and look forward, study these things. Okay, now let's start with the basic ingredients that I want to cover. And the basic ingredients that I want to start from is like integrability and beyond. So what do I mean by integrability? As I have already told you that being governed by linear equations, there is no exact non-linearity or class. Oh, so I also wanted to mention this one thing, that I said that non-linearity plays a big role, but that is very specific for finite dimensional systems. So there is also some proofs that say that if your system is finite dimensional, then non-linearity is kind of essential for having a chaotic dynamics. If your system is infinite dimensional, then even if it is integrable, then still it can have some chaos. Then it can, if your system is infinite dimensional and it is linear, if non-linearity is not there, then there can be still some chaos. But for finite dimensional systems, the non-linearity is very important. Okay, moving forward. So as we do not have that non-linearity in this thing, we'd like to have something that is kind of similar. And that is where integrability and non-integrability comes in. What is integrability? According to this definition of Liouville and Arnold, like if the number of constants of motion are equal to the number of degrees of freedom, then it is said to be integrable. This thing is there, which is important in some other context, that the vector field also have to remain regular over the whole phase space. But the main condition is this, that the number of constants of motion are equal to the number of degrees of freedom. So here are two examples. One is like the circle billiard. So the circle billiard is like this is a boundary condition is just a circle. So the whole a particle is there and it is bounded by a circle, and here it is a cardioid billiard. So it is like a particle that is bounded by a cardioid boundary condition. So what is the main difference between these two? If we look at the circle, we know that if a particle is moving inside, it is a closed system, so energy is conserved, and so is the angular momentum. So there are two conserved quantities. And as it is in 2 dimensions, so you have like 2 degrees of freedom. So there are 2 degrees of freedom, and then you have 2 constants of motion. So here it is an integrable system. But if you look at this cardioid billiard, then you see that here energy is conserved, but there is no another thing that is conserved, like angular momentum or something else, or momentum. So as here you are still in 2D, you have 2 degrees of freedom, but only one thing is conserved. So here it is not integrable. And here you can see that the trajectory is a bit more quote unquote chaotic. Then how do I relate chaos with the trajectory in the classical picture at least? In the classical picture, we say that the distance between 2 nearby trajectories increases linearly with time for integrable system. Suppose this is an integrable system, this is an integrable system, and here if we look at 2 nearby trajectories, the difference between them kind of grow linearly with time. But if you look at this system, if you have 2 trajectories that differ by very little perturbation at the initial point, after some evolution, they will be hugely different. Some trajectory will go in this direction, some trajectory will go in that other direction. And this is for this case. For non-integrable systems, the separation between neighboring trajectories go exponentially. So this is one feature that will be somehow very interesting in the quantum mechanical case to see if there is any analog of this. But then in the classical picture, there is this thing that the non-integrable systems have positive Kolmogorov-Sinai entropy. And the Kolmogorov-Sinai entropy is mainly studied in the context of classical chaos. And this kind of tells you if your system is chaotic, non-chaotic. This is one thing that one may look at, but it will not be relevant for the later discussion. And apart from the 2 cases that I have just told, like integrable and non-integrable, there are also some other examples that we call pseudo-integrable or quasi-integrable systems. These systems are very interesting in its own right, but I'll not talk about them here now. Okay, and just one thing, probably I would have said this in the beginning already, but I was just in a bit hurry, because if you have any questions, just feel free to stop me at any point. I'll be very happy to take them. Okay, and moving forward, I start talking about OTOC, the out of time ordered correlations. So why these things are interesting? Because here I just said that in classical picture, the chaos and non-chaos are somehow related to how much at later time two nearby trajectories differ, if the separation becomes linear or exponential. And that thing is kind of captured here in this picture. How? That if you calculate this commutation relation to the power squared and take a thermal average, then you will see that it behaves like this. Here I have used the cyclicity property of the trace. Here there are two, because 2 is multiplied, two parts that are time ordered and two parts that are not time ordered. These not time ordered parts kind of tell you about the dynamics of the system in a non-trivial way. If you look at this, just the not time ordered part, this thing is supposed to behave like exponential of 2 lambda t, where this lambda is called Lyapunov exponent. So what happens is that in general, this quantity tells you that how much two trajectories separate at later time, given that there is some separation already at the initial time. If you look at this, so this part is a part of this. If you look at this is delta x at t is equals to t1 by delta x at t is equals to t0. So there is a separation at time t is equals to 0, and this kind of tells you what the separation will be at time t is equals to t1. If this thing grows like this, which means that if this thing has exponential growth, that should, being motivated from the classical picture, tell you that there is something chaotic about the system, that the trajectories kind of diverge exponentially. If the trajectories are nearby, because this is delta x, so that the initial separation is very small, but it grows exponentially. So that means that there you should find a positive real number that we call the Lyapunov exponent for this. That should tell you how fast the trajectories are kind of diverging from each other. And then, so it is the usual definition, and you can generalize the definition as the thermal average of commutation to the power nth power, and that will give you exponential of n times lambda t. What it actually does is like it enhances the behavior, because if you plot this thing, you will see a growth with the power 2 lambda, but if you plot this thing, if you take the higher powers, you will see more and more. The separation will become more clear. It will be easier to detect if there is a positive real number lambda present in the system. And then there is the other aspect of this. So this thing grows. This thing grows because the separation increases with time. And then there is the complete opposite picture, the 2-point correlation. This we call the 2-point correlation, which is like also the thermal average here. This thing should decay exponentially for non-integrable system. If my system is non-integrable, it should decay as exponential of minus lambda t. It is the same lambda, the Lyapunov exponent, and it should drop suddenly. Very sharp drop. The quicker the correlation decays, the more chaotic it is. Is it a true statement? We will see in a while, but this is one initial point to start with. So just let me recap a while. So what we have seen that in classical picture, the divergence of two trajectories are an indicator of whether there is chaos present in the system or not. Then we have defined something analogous for the quantum mechanical system using the commutators and their higher powers. And we see that if it grows exponentially, we might think that, okay, the trajectories are diverging. It might signal chaos. And along with this thing, if the 2-point correlation decays exponentially with the same prefactor, with the same exponent, then we might say that, okay, it might be chaos. And for integrable system, this thing will be oscillatory. That means that for integrable system, the 2-point correlation will not decay, but oscillate. Okay. And then there is this ambiguity that is there, and that is why there was this initial picture that whenever we see fast scrambling, we kind of think that is it quantum chaos, and there is the complexity of finding quantum chaos that is here. If we have a potential like this, a W-shaped or Mexican hat potential, if we have a potential like this, then what happens that there is an unstable saddle point here. This point is an unstable saddle point. So it is like if a particle starts from a little on this side or a little on this side, the trajectories will be quite different. But mind it that it is in a one-dimensional system, and it is a bound system. So the total energy is conserved. So according to this definition of integrability, the number of constant of motion is equal to the number of degrees of freedom. Both are 1. The energy is conserved and the degrees of freedom is 1. So this is an integrable system. But because of this presence of unstable saddle point, we still find exponential growth of out of time ordered correlations. Then there is another thing that if my potential contains terms like this, that x to the power 2n, like for x square, it is an exception, but apart from x square, any other higher term like x to the power 4, x to the power 6, x to the power 8, for any higher term, it is a bounded system. So the energy is conserved. It is in one dimension, but we still find exponential growth of OTOC. So this is kind of puzzling, that these systems are integrable, but they have a chaos-like behavior or a kind of chaotic behavior. And that is a point where we kind of distinguish between fast scrambling and chaos. These two things are not same. So whenever my system is kind of having an exponential growth of OTOC or a sudden decay of the two-point correlation, that tells me that the trajectories are kind of diverging very quickly. My wave function is spreading very quickly. So the word scrambling is connected to the how fast the wave function or wave packet spreads over the whole system. So the exponential growth tells me that in my system there is some fast scrambling, but it is not always the case that it is chaotic, because I can always kind of calculate what the system will behave like in future, because it is an integrable system. So this is why OTOC is not always a good probe in that sense, but there also has been some recent proposal where they put some lower bound on the value of Lyapunov exponent to distinguish between this kind of scenarios where you have the saddle dominated scrambling or the higher order correlations, and then the case of where the system is actually chaotic. But still this thing is still not settled. One needs to study this more to understand. But from this thing, what we kind of gain are like in these kind of systems where you have the fast scrambling, where you expect some kind of chaos, there are three important timescales that we should take into consideration. One timescale is like where the OTOC becomes significant. We call that a scrambling time. Then there is this time when the exponential decay has already happened, or the timescale of the exponential decay. This happens much faster than this. So dissipation timescale is a smaller or a shorter timescale than the scrambling time. And then there is another kind of timescale where the OTOC kind of saturates. The OTOC saturates because the spreading has been completed. The wave packet has kind of explored the whole Hilbert space, and then it is kind of saturating the OTOC. And in this kind of scenario, we call this timescale an Ehrenfest timescale. But sometimes the scrambling timescale and the Ehrenfest timescales are equivalent for some systems, and it is not equivalent for some other systems. But usually there are three important timescales that are present in a system. Now we kind of move on to the next part of this talk, that is complexity and its allies. So here I also did not want to be very specific, because what we call complexity are kind of, it is a package. It is a package of many things. These are the initial complexities that one started with, the state complexity and the operator complexity. I'll just say what they are. But then there is this modern version of complexity that we call Krylov complexity. One is like operator Krylov complexity, and the other one is the state Krylov complexity, which we call spread complexity. So coming to the first definition, what is a state complexity? It is like starting from an initial state, let's say psi r, or reference state psi r, using some unitary gates ui, you want to find the shortest path to reach the final state psi f. So you minimize over the paths or the combination of the gates using which you can reach this final state starting from a reference state. Then there is the other part of this that we call operator complexity. Here you do not talk about the states, but you just say that we have some unitary operators ui, and I just want to create a more complex unitary operator u using these combinations of ui and what is the minimal configuration that kind of mimics u. So you can see that these two things are related, but not completely equivalent, because in this picture you really do not know what the initial and final state is. You are just given an operator and then you are supposed to find the optimal combination of UIs to get the actual operator. And then there is this operator Krylov complexity and the state Krylov complexity. I will talk about operator Krylov complexity a little later because it is a bit non-trivial, and I think that somehow it is more helpful for new people to get this insight because it has some new ideas. So in the operator Krylov complexity, the idea is that we go to the Heisenberg picture where the operator is evolving, and this is how the operator evolves, and it kind of spread over the operator basis. What I mean by operator basis, I'll be clear in a while, but this is the initial idea that how much the time evolved operator is spreaded over the operator basis that we call Krylov basis for operators. And the state Krylov complexity is again the state version of this. Here we are in the Schrodinger picture. Our state psi is evolving and it is spreaded over the Krylov basis for states. But these are just two kind of complementary pictures of each other. I will talk about this part because this part I feel is somehow more trivial when we kind of understand this part. Okay. So whenever I now mention KC, it is like Krylov complexity, but it is Krylov complexity for operators in general. And okay, I don't know why this, oh no, why this part is cut here. I have no idea. But okay, this equation I believe is a familiar equation here, how that operator evolves. It kind of commutes with the Hamiltonian and there is the explicit time derivative of the operator. And if the operator is not explicitly time dependent, that part anyway doesn't matter. So here what you are left with. But here what we see that we can write this part like this, where the ONs can be written as this. I mean, the O0 is like just the O itself. O1 will be the first commutation with H and O2 will be this nested commutators. This comes from Baker-Campbell-Hausdorff because there is this form that e to the power A times B times e to the power minus A. If you have a form like that, then it can be always written as nested commutators. And that is what we are doing here. These ONs are the nested commutators. But now this is literally the most important part, that we build a basis out of these nested commutators. How do we do that? So first of all, to build the basis, we kind of use this notation of Liouvillean superoperator that we call L. Why superoperator? It has nothing to do with supersymmetry, but it is called a superoperator because it acts on operators. So the curly L, the Liouvillean, acts on operators, and that's why it is a superoperator. So if we have like a commutation of H and O, we may call this that L is operating on O1s. If we have a nested operator, nested commutator of O 2 times, then we call it L square and so on with L to the power n. So this thing in terms can be simplified with this form where L is the Liouvillean superoperator. Why is this helpful? Because now you see that this picture looks like anyway like the Schrodinger picture, quote unquote, where you feel like somehow this operator is being time evolved by this Liouvillean superoperator. In the state picture, it would be evolved by e to the power minus IHT. So just after we do these steps, from this now on, the state picture and the operator picture kind of becomes equivalent, where in the operator picture we have this Liouvillean superoperator, where in the state picture we just have the Hamiltonian. But for this state picture we have this non-trivial task of writing these nested commutators at the Liouvillean superoperator, which we do not have to do in the state because we are already given this form. But okay, now after we write this, we have a form like this. So here what I really do is that I start behaving with these operators as if they are states. This is the time evolved one, this is the without time evolved one. And now here is again a non-triviality of the operator space. If it were the state space, then you already know how to take the inner product in the state space, and this would be well understood. But what I mean by operator inner product, one really has to define that. So this is a general form. I mean, I cannot say the general form if I am considering the thermal inner products also, but this is a reasonably general form of taking the inner products, where it depends on kind of two things, where g of lambda is like the weightage function, and then it also depends on beta. Beta is like inverse of the temperature, so it is like a thermal inner product in some sense. And then one can take very different approaches to this. One can define their inner product with g of lambda like this. This is called Whiteman inner product. Then one can define a inner product at infinite temperature, where you make like beta goes to 0. Then it becomes this very simple form, and so on and so on. But this is a general way of defining operator inner products. And now as we define the inner product, now we can again proceed with our initial way. We come back to this picture. We have these different bases. So now we start treating these vectors as bases. So what are my bases here? My bases here are like the O, L operating on O, L square operating on O. And let me just say, if it were the state picture, it would be just the state psi, then H operating on psi, then H squared, I mean, where H is the Hamiltonian, H squared operating on psi, and so on. So now with these different vectors, I just do Gram-Schmidt orthogonalization and make a orthonormal basis. So here I start with, take the initial vector, I orthonormalize, I mean, I just normalize it, I get the initial state. Then I proceed with, so then I operate with the L1, I kind of again normalize it and go on and keep subtracting its inner product with the previous ones, as we do in the Gram-Schmidt process. But this algorithm here is called Lang's algorithm, because also we are doing it in a weird kind of space that is like the space of operators. So this is the Lang's algorithm for obtaining a complete set of orthonormal vectors. Okay, and then it is just nothing, but it is just a nice visualization of the Liouvillean in this operator basis that we have just built. For Liouvillean like this, if we build basis like this, where these B's are the inner products, then in this basis it looks like this. And why is this interesting? Because here we have built a space with the Krylov vectors as the basis. So in this space, it looks like these are the nearest neighbor hopping parameters. So it is like a spin chain kind of model in the Krylov space, but that is a side comment. One may be interested to study that thing specifically, but for this part, it is not that important. But what is important is that there is operator growth hypothesis that kind of tells me how these BNs should behave for a complex system, in the sense that for a chaotic system. But I'll just go to that before let me just make two last comments. One is that if I have these systems where O's are the operators, then the dimension of the thing will be proportional to like this square. And here with some technicalities, one can prove that the Krylov space that we have, so this is the linear span before orthonormalizing everything. And after we orthonormalize with some calculations, one can show that the Krylov space dimension is bounded by d square minus d plus 1, where this d is the dimension of the initial operator that was in. Okay. Fine. So now we have this picture where ONs are the basis that we have built. We can write our time-evolved operator as in this form, with this thing being the coefficients. And as these are the coefficients, we might expect them to behave like probabilities, because these are just the coefficients and they should be constant, the sum of all of them. And then from this relation, one can calculate a time evolution equation of how these coefficients may change with time. And by solving them, one may see how this operator OT is spreaded over the basis. So this kind of tells you, so if the phi n has all non-trivial terms for all the n's, that means that the OT has support on all of the operators. And that tells that this O really is spreaded over the whole Hilbert space. And on the other side, if psi t has all these non-trivial terms, that tells me that it is spreaded over the whole Hilbert space. So this is what I mean by spreaded over the Krylov space. And from here, one can define the Krylov.
Excuse me, Rothinda. I'm sorry to interrupt you, but we might be running short on time. So could you please wrap this up within 5 to 7 minutes?
Yes, I have that in mind. So it will be within 5 minutes.
Okay, thank you so much.
Sure. So from here, one can define the Krylov complexity like this. One can also define what we call Krylov entropy that has this form, but it is like a Shannon entropy, but in the Krylov space. So this is something one can study to say about the quantum chaos. And this kind of wraps up this part also, that for maximally chaotic system, this complexity behaves as exponentially. For finite size, for systems with finite size, this kind of saturates, that supports the eigenstate thermalization hypothesis. And then this is the third thing is the conjecture that was there, that if S is my system size, then the BNs are these BNs. They are kind of proportional to the system size and they grow with the system size. And this was the universal operator growth hypothesis that was there for chaotic system. One should find a behavior like this, and that has been later confirmed in some models like some XXG spin chain model, where they find that the complexity initially grows and then saturates. It is from a paper, this paper. And these are for chaotic system. This has been shown to be a good measure. And there is also a special thing about this, that usually what happens after one system has thermalized, it is very hard to study chaos after thermalization. But this complexity even grows linearly even after thermalization, and then it saturates much later. So this complexity is very special because it has growth even after the system has thermalized. This is one key property that kind of distinguishes this thing from other measures. And this is just one thing to study it in the holographic picture. So why should we care about this? And then one can say that there has been some recent proposal about the geometric aspects of the Krylov complexity. One can study Krylov complexity in the CFT and spin chain models, and then one can do complexity in holography that we call holographic butterflies, in the sense that the other classical chaotic systems are called butterfly effects in that sense. So this is the volume picture or the bulk picture, where the Krylov complexity has kind of been conjectured as being the volume of this system. But this is for, I think, a SL2R manifold, and this is from this paper. This is also not ours. This is some other paper. But this volume conjecture is there, and this needs more understanding and more study on this is due. But my current research, I just summarized in this one sentence because that would be a bit too much if I went on with this. That is, we study Krylov complexity for non-Hermitian or dissipative systems, because with the non-Hermitian systems, one can have complex eigenvalues, and the complex eigenvalues kind of tells you that I do not have a unitary time evolution. In the case when we do not have a unitary time evolution, how to build the Krylov basis, it's itself very challenging. And further, what we find more, so this is a work with Arana Bhattacharya, IISc, me, and Bidut Dev, who is at IIT Kanpur at this moment, I believe. Here, what we do is like we take the non-Hermitian part of the Hamiltonian as perturbation. Here what we see is that the total probability kind of decays with time. If it were a Hermitian system, the total probability would stay constant. But here the decay of the probability is there, and this is because of the non-hermeticity being present in the thing. And here you can see that the tau is the perturbation parameter. The stronger the perturbation or the larger the perturbation parameter is, the quickly it decays. And the interesting part is we perturb it to a non-chaotic or integrable system. But we still see that there is an initial growth and then there is a saturation. This shouldn't be the case, in the sense that this saturation shows that the system is somehow chaotic. There is initial growth and then there is this saturation. But what we find that even non-Hermitian perturbations can mimic the effect of chaotic systems. So dissipation is also in some sense scrambling, because my information kind of scrambles out of the system. And in this way, this kind of mimics the chaotic behavior. This should be a paper by next 1 month or 2 months, I believe. And okay, I'm kind of done with my story with complexity. This is some advertisement, as my kind of guide asked me to do it, because my main field of work is not quantum chaos. My main field of work is quantum holography and quantum information measures in holographic theories. So this is one recent paper that has been out from my group, including myself. If you are interested in ADS-CFT holography or hyperbolic geometries, maybe SON spin chain from the condensed matter background, or maybe graphs, as we had a very nice talk yesterday on graphs, on negatively curved space, the hyperbolic space. One may go and have a look at this paper. And thank you. That kind of ends the talk from my part.
Thank you. I mean, it was really informative. I don't see any questions around here, but then I guess the people will get around you if they have doubts or something to ask.
Sure. If you
thank you.
Or queries or any need for the reference, you are very welcome to contact.
We see a hand, Siddharth Jain. Please speak, Siddharth Jain.
Hello.
Yes.
I have a question in where you mentioned OTOC.
Okay.
So when you were defining OTOC, like yes, this slide. So in the second point, you have shown that's XTP0, XTP0, and then you have mentioned the usual definition this in the next line. So, like, can you give a bit of physical motivation, like why the orders have changed in the usual definition and this second point definition?
Okay, sure. I understand your question. So I think the main idea is that if you calculate this commutation squared, then what you find is that there will be 4 terms. And the 4 terms are these 4 terms. So there are 4 terms. And 2 terms of them will be time ordered. These are time ordered parts. And 2 terms of them will not be time ordered. These are the non-time ordered parts. If you calculate them numerically, you will see that the time ordered parts kind of give you a trivial result. It really doesn't tell you the it really doesn't help you to distinguish between a chaotic and a non-chaotic system. But if you look at this non-time ordered part, this is what really plays the non-trivial role. This kind of decays over time, and this kind of gives you the non-trivial information about the presence of chaos or scrambling that is there in the system. So in the first part, I have mentioned only the last part because this is really where the main information is hidden. But usually it is easier to calculate because of some technical reasons. This is just easier to calculate. You can define some terms and then it becomes really easier to calculate, and people usually define it this way. And then there is also this thing that if you really want to go higher power, like to the power n, then you really would like to go as the commutation to the power n, where you will find a mixture of some parts that are time ordered and some parts that are non-time ordered. But the non-time ordered parts are really the thing that carry the information, if that helps your question.
Okay.
That's why I highlighted the second part. Yeah, sure.
Okay. And one more thing, like, uh, is this some sort of measuring how the canonical commutation relation of X and P, like, does that change in a chaotic or non-integrable system?
Yes. So in that sense, if you write this term as del x at 0, so P is del x, I mean minus I ka del x. But if you write this the P as del x at 0, and then calculate this thing that x at t times del x at 0, the commutation of that, you will find this thing. You will find that it is so the del xt that is, sorry, the xt that is there will be in the numerator, and in the denominator there will be that del xt at 0. You will find a term like this if you just write in that fashion and calculate. And this tells you that, looking at this expression, it makes it very clear that it is how the separation at time t1 is affected by the separation at time t is equals to t0. Right. So
yes,
mapping from these to these is really helpful, and that can be done by writing P as del x at 0. Then you can see that this is the real thing that I want to look at. And if this thing grows exponentially, that tells me that I have some chaos or at least fast scrambling present in my system. If this thing is linear, then that tells me that it, or periodic, then it tells me that it is an integrable system that has no fast scrambling or chaos in that. But yeah.
Okay. Thank you.
Thank you very much for your questions. Yeah.
Thanks a lot, Rothinda, for this amazing everything. I mean, the question also, I guess, sparked curiosity. So we are really, proud to have you as one of our seniors. Best of luck for your future.
Sure. Thank you very much. Thank you very much for organizing this. I'm really.
Yeah, we are very grateful to have you here. Okay, so we'll move on to our next speaker. Her name is Shulabna Bhattacharya. She is presently a PhD student at TI for Mumbai. She works in the field of theoretical astroparticle physics. And today, she'll be delivering a talk on the compact stars and mergers as a probe of particle dark matter. Shulabna, if you can speak. Ms. Shulabna, are you there? We saw her some time back. What happened? Request our audience to wait for some time.
I think there might be an internet issue. Please ask Sunshine to reach her out.
Yeah, it might be a problem. Oh, Shulabna is here. Okay.
Yeah. Actually, I am new to Microsoft Teams, so that's the problem.
Yeah, basically COVID introduced us to this platform. So
can you see my screen?
Yeah, we can see your screen. Please go on.
Can you see this?
Yeah, we can see your slides.
Yes.
My slides you can see?
Absolutely.
Yeah. Okay, fine. Then should I start?
Please go on.
Yeah. So hello everyone, thanks for having me. So I'll be talking about compact object and mergers as a probe of particle dark matter. First, I want to tell that I am also new to this field, and I have tried to keep the talk very simple and informative. So anytime if you have any questions, just feel free to interrupt me and ask. And as I am new to this field, if you have any comments or any suggestions, so you can just interrupt me and then tell. So I'm starting. So this work has been done in collaboration with my senior Anupam Rai and my advisor Professor Vasudev Dasgupta. So at first, why we are bothered with dark matter? Because 26.8% of our universe, the constituent of our universe, is made up of dark matter. 68.3 is the dark energy. We just don't know what it is, but we are trying to probe what dark matter is using some special candidates. What we see around us is just the 5% of our constituent of the universe. So depending upon the ranges from ultralight dark matter to massive dark matters, the range is like the ultralight dark matter starts from 10 to the power minus 20 EV order, and it goes to the 10 to the power 57 EV order, where the 10 to the power 57 are the thing which are known as primordial black holes and the massive astrophysical objects. So these are the candidates of dark matter that people are interested in, and each of these fields are very broad and yet to be explored a lot. So today in my talk, I'll be emphasizing about the weakly interacting massive particle. Now, there are 3 detection techniques of dark matters. So the first detection is direct detection, where we assume that dark matter will have a non-zero scattering cross-section with the standard model particles. And a dark matter particle comes to the detector, hits a standard model particle, and they recoil, and we measure the recoil, the momentum transfer, and we measure the recoil energy, and from that we try to search the dark matter. Here I have written a sigma chi n interaction term, which is like later on I'll be talking about. It is the interaction with the neutron. The dark matter particle is hitting the neutrons, and then they will be recoil. This is the direct detection technique that people use. Like there are underground detectors, and as the dark matter particles are very weakly interacting, so they come from the galactic halo and they enter through our Earth and they detect in the Earth detector. Now, as we don't see any detection, we can put a bound on the dark matter particle mass and their interaction strength, but we cannot say like this is the dark matter particle, that if there is a detection then we would have got a point. But as we have not seen any dark matter yet, so far we can do is like we just put constraint that okay, this region cannot be allowed. So the other one is indirect detection. Indirect detection tells about the dark matter will have self interactions, and a dark matter particle will interact with itself, and then they will give a standard model particle, and you will try to look for that standard model particle, and then you will try to say whether what is the mass of the dark matter and what is the cross section with its own So and the another is collider search. Collider search is basically the supersymmetric models that I was talking about in the candidates of dark matter. In the here the standard model particles are they are energized, and then they are collided, and we try to search what is the decay channels, and there are some energy loss and which we cannot answer, and that energy loss can be answered by the standard model particles decaying to dark matters. So in this talk, we will be talking about direct detection experiments where there will be a non-zero interaction with the standard model particle of the dark matter particle. So we will be talking about the dark matter capture by the neutron star. I'll talk about why neutron star is important, but here the dark matter capture by the neutron star. So you can see these red balls are the stellar nuclei of mass Mn. Mn is basically the neutron mass, because neutron star is degenerate with neutrons. And a dark matter particle of mass m chi is coming from the galactic halo with a velocity of u. So it's coming from far away, and when it's reaching the surface of the neutron star, the stellar object, the velocity of it's become u square plus v escape square whole to the power half, that you can see that I have written. Somehow the pointer is not working, so I cannot point. So that's a problem. Anyway, so then the dark matter particles are getting to interact with the neutrons, and as they are interacting with the neutrons, they are losing energies, and as they are losing energies, there will be a time when their final velocity will be smaller than the escape velocity of the stellar object, and then the dark matter particle will be captured inside the object. As you can see, this blue balls are the dark matter balls, so they are getting accumulated inside the star, as after the collision they cannot have the sufficient energy to escape from the neutron star. So now, why neutron stars? So neutron stars are compact object. Compact object means they are very dense. Their radius is about 2 to 10 kilometers, and their mass is about from 1 to 2.4 solar mass. So they are very highly dense objects, and the density range is given here. So you will be finding a huge number of stellar targets. I mean, the number of neutrons, if you calculate the number of neutrons in a neutron star, it will be of the order of 10 to the power 57. And due to the high lifetime of the neutron stars, that is 10 to the power 9 years of the order of, they can probe a high mass WIMPs. In the direct detection experiments that I was talking about, in the underground detector, as you try to search a high mass dark matter particle, anyway, if the dark matter particle is very massive, then its number density falls, because number density is the density divided by the mass. When you are dividing by the mass, the density of the dark matter is constant. We know in the solar neighborhood that the density of the dark matter is 0.4 GeV per cc. So if you are trying to see that if you are trying to probe the highly massive dark matters, their flux is very low. So your underground detector will not have that much dark matter to interact with, and they cannot probe it. But in case of neutron stars, as the stellar targets are huge, I mean, if you want to detect your highly massive dark matter through underground detectors, you will have to build a huge detector, and you will have to take a runtime of a huge period. But so we can see the neutron stars. The neutron stars are basically, they will have a number of stellar targets, and as their lifetimes are also high, so we can capture dark matters inside the neutron stars, and we can see the subsequent effects. Now, due to their low radius and high density, their escape velocity is also very high. It is of the order of 10 to the power 15 kilometer per second. So the galactic dark matter particle, which have an initial velocity of 200 to 300 kilometer per second, will easily get captured inside the dark matter particle, say after single scattering itself. So after the dark matter gets captured, what physics we try to see? First of all, we try to see for self-annihilating dark matter, for the case when the dark matter particle is interacting with itself and giving other particles, other standard model particles. So the captured dark matter particles can annihilate and can produce heating in the neutron star. If you are producing new particles, then it will produce some heating, some exotic heating in the neutron star. And as you know, neutron star is a cold object. Studying the luminosity measurement and anything, you can see a new direction to probe the dark matter. Probably JWST can be one of those probes. And for non-annihilating dark matter, for the thing I'll be talking about, it is concerned about the non-annihilating dark matter. So the captured dark matter particles lead to a micro black hole formation at the core, and that black hole eats up the host star. Existence of all stars can probe the dark matter parameter space. So if you are seeing a neutron star in the sky, then you can tell, okay, so I can see the neutron star, so it is not being transmuted. I mean, it has not formed a black hole due to the capture of dark matter particles. So as it has not formed any black hole, so we can say that this mass of the dark matter particles and this cross section that with which it can interact with the neutrons can be probed, that this will be disallowed. If it would have been allowed, then we would not have seen the neutron star in the sky. So from the existence of these nearby pulsars that I have mentioned, people have already put constraints on the dark matter parameter space. So after this dark matter is captured, many more collisions can occur, and it helps the dark matter particle to come near rest. And the dark matter sinks to the core of the star within a thermalization radius given by this. And as you can see here, m chi is the dark matter particle mass. So the massive particle dark matter you choose, it gathers towards the core. This RTH, R thermalization radius, is the radius from the center of the star, from the center of the neutron star. So as you are increasing your dark matter particle mass, it will accumulate towards the core. More the massive dark matter is get accumulated towards the core. This process is quick compared to the stellar lifetime and dark matter capture time itself. And if the dark matter density at the core becomes greater than the baryonic density means the standard model particles that you can see. I mean, all the things you can see, you can measure at the baryonic things. All that we cannot is the dark matter. So if somehow the dark matter density becomes greater than the baryonic density at that core within the thermalized sphere of the dark matter, then it starts self-gravitating. So it starts to self-gravitate and it starts to collapse. Now, if the mass captured, I mean the dark matter mass captured somehow becomes greater than the mass needed to self-gravitate, and the mass captured also at the same time becomes the mass needed to collapse. Self-gravitation is the starting of the black hole formation, and collapse is the formation of the black hole when the black hole eats up the neutron star. So anyway, when the mass captured becomes greater than the mass needed to self-gravitate, and at the same time when the mass captured becomes greater than the mass needed to collapse, then a black hole is formed. And that black hole, we name it as a transmuted black hole, because the neutron star, the host stellar object, getting transmuted to a black hole. So finally, when the black hole forms, there are two timescales involved. One timescale is the time required to capture enough dark matter particles to achieve the black hole formation criteria. Like there is the neutron star that there is throughout its edges, it's accumulating the dark matter particles. It's a time scale, and when this dark matter particle density at the core becomes greater than the baryonic density, then it starts to self-gravitate. This is the first time scale. The second time scale is this self-gravitation, that dark matter sphere, when the dark matter sphere started self-gravitating, I mean when the dark matter sphere has formed a tiny black hole inside the core of the host stellar object, then it starts accreting the mass from the host object, and through the accretion it eats up the total host star, and this is a time required to capture the whole host star, then it becomes a pure black hole. So now the mass of the seed black hole that is formed inside the core of the stellar object is of the order of, it scales 1 by m chi to the power 3 by 2. So you can see, if you are trying to probe a very high massive dark matter, I mean the dark matter particle is very massive, then the seed black hole is very small. And if the seed black hole is very small, then it will Hawking evaporate. So when it will evaporating, its accretion, its evaporate rate dominates over the accretion. Hence, we don't end up having a black hole. So can you see, like as the neutron stars can probe a highly massive WIMPs, but if it becomes very high, then you cannot probe it, because then the seed black hole is very, the mass of the seed black hole is very low, and it will, the Hawking evaporation will dominate over the accretion. So it will never be able to eat up the host star in the required time scale. Now, why are these black holes interesting? So now we have the LIGO. We all know about it, Laser Interferometer Gravitational Waves Observatory. So we have of the order of 110 events now. Most of them are binary black hole mergers, but we have also seen binary neutron stars mergers as well. So this is an event GW190425. So just for the information, I want to tell like how the nomenclature is done. It's GW is the gravitational wave event, 19 is the year 2019, and it's 0425 is the 25th April of 2019. This event was seen on 25th April of 2019. So here you can see I have marked that the component masses are 1.12 to 2.52 solar mass. And they say the possibility that one or both binary components of the system are black holes cannot be ruled out. Though astrophysics says that we cannot have black holes in the mass range, like it is disfavored, that we cannot have black holes in the mass range of 2.5 to 5 solar mass, but LIGO is seeing black holes which are merging in these mass ranges. So we do not know whether these are black holes or whether these are binary neutron stars, because there is also inconsistency with the known galactic BNS population, because from the TOV equation of state, Tolman, Oppenheimer, Volkov equation of state, you cannot have neutron stars which are massive than 2.4 solar mass. So what are these objects? Whether they are neutron stars or whether they are black hole, we do not know. But LIGO has seen such events. Now there is another event which is GW190814. It's also, the thing is like 14th August 2019 the event was seen. Here also the compact object is of the mass of 2.50 to 2.67 solar mass, and they are claiming either this is the lightest black hole or the heaviest neutron star. However, the combination of mass ratio, component masses, and the inferred merger rate of this event challenges all current models for the formation and mass distribution of compact object binaries. So we are yet confused whether we will tell it is a binary neutron star or it is a binary black hole. So how can we look for these tiny black holes? So as I was telling, astrophysics disfavors the mass window of 2.5 to 5 solar mass for black holes, and TOV equation of states of neutron star can't be larger than 2.4 solar mass. So what are these compact objects that LIGO is seeing? So as we are telling about these transmuted black holes, we can say this can be the transmuted black holes or can be primordial black holes that the LIGO is seeing. Primordial black holes is also an exotic topic, but I cannot cover it over here. And what I can tell, the primordial black hole is the black holes which are formed very early in the universe when there was nothing. There was no nucleosynthesis. So the primordial black holes are made up of non-baryonic matters. So as they are made up of non-baryonic matters, so they are a good candidate of dark matter. People study this primordial black hole in a more extensive way, and these are very interesting. So if you are interested, you can look for that. So the black holes that LIGO are seeing, they are not astrophysical. So can they be primordial or can they be transmuted? Yes, they can be, and that we get from the future advanced detectors called LISA, which is the space antenna, the space-based gravitational wave detectors, Einstein telescope, cosmic explorer, and all. So if we see this kind of black holes, we will not know whether this is a transmuted black hole or primordial black holes. But the thing is, like, their merger rate, if we try to see the merger rate, the number of merger that happens within a volume within a year, because LIGO has a sensitivity, like it scans the sky in a volume, say in a unit of megaparsec cube, and throughout a year, and then it sees some mergers. So the merger rate is basically the number of mergers per gigaparsec cube to the power -3 per year. So it's divided by a volume into time factor. So anyway, like we can distinguish this primordial black hole and transmuted black holes from the merger rate evolutions of these objects, because as I am telling, these primordial black holes are formed in a very early universe. So if you try to probe your early universe, you will see more and more primordial black hole mergers. But these transmuted black holes are from the binary neutron stars. So these transmuted black hole mergers can only happen after there is the star formation. And our star formation history tells that the first star was formed after Z equal to 10. I'm talking about redshift. If you are not familiar with it, it's nothing but the time analogous of cosmology. We call the earlier times with higher redshifts. Like today, the redshift is Z equals to 0. So from the merger rate, we can say whether these black holes are transmuted or the primordials or not. So my recent glimpse, glimpse of my recent work is like, I am telling that we are telling that LIGO has not seen such exotic transmuted black hole mergers. And as LIGO has not seen these mergers, so we can put an exclusion limit on the dark matter on the dark matter parameter space that I have put an arrow on. Just look at that plot. The x-axis is the mass of the dark matter particle. The y-axis is the scattering cross-section with the nucleon. And this shaded region tells that this from current observation, this region is ruled out. We cannot have a dark matter of this mass and this cross section which lies within this pink area, because if we'd have seen this pink area, if we would have seen some dark matter in this pink area, then there will be some transmuted black hole mergers that LIGO should see. But as LIGO has not seen such mergers, there are 0 events, so we can put an exclusion plot and we can say, okay, these parameters are ruled out. Just for the information, this RBNS that you can see, this RBNS is nothing but the binary neutron star merger rate, and it has a huge effect on the transmuted black hole mergers, because these black holes are formed from the neutron stars itself, and this is how these transmuted black holes are separated from the primordial black holes, because the primordial black holes are very old. They were formed in the early universe, and these transmuted black holes that I am talking about, they are after the birth of the neutron star, when the neutron star is capturing the dark matter, and then when it is transmuting to a black hole. So if there are events in future, if there are events by LIGO which tells about these transmuted black holes, then we will get an region where we will say that our dark matter particle and mass and the cross section will fall in this region, and that's why we are getting to see such events. As we have not seen such events, we can now just exclude the parameter space that cannot happen given some recent data. So my final takeaway from this talk is is LIGO a direct detection experiment? So we can say yes, LIGO can be a direct detection experiment, because our underground detectors cannot detect these highly massive dark matter particles that I have shown the range here, 10 to the power 4 to 10 to the power 7 GeV. So we cannot probe this kind of dark matter particles through the underground detectors that we have, because they are very low flux. So there are neutron stars, there are highly dense neutron stars we are capturing dark matter. If they are capturing dark matter, if we are having these exotic black holes which are not in the range that astrophysically motivated black holes are, so we are seeing exotic black holes, and we have to answer what are these black holes, whether they are the neutron stars or whether they are black holes. If they are black holes, then we cannot rule out the chance, then they can be primordial black holes or they can be transmuted black holes. And if they are transmuted black holes, then future detection of these exotic black hole events will give us a concerning detection region in the dark matter parameter space, and then we can tell that this mass and this cross section will be our dark matter particle. So this is all about my talk, and if you have any questions or any comments, you can mail me, you can just drop me an email or catch me.
Okay, so I'm asking the audience, do you have any questions? Anybody? Okay, there's a question. Ritik, please speak.
Firstly, it was a really nice talk. Actually, I have a lot of questions. I cannot tell everything there, so I can reach out sure. But I have a question that you have excluded some parts, or you have put some constant on dark matter. That's from the exclusion plot.
Yeah.
So this is because that LIGO has not detected, because LIGO has the range. It has detected. I mean, it can detect at. It cannot detect the higher redshift region. But LISA is expected to be detected at a more region, 8, I think.
Yeah.
So whether it is possible that constant can be changed, or if
surely. I mean, we have put the constant with the O3, the third observation A plus B data. Now the constant is from third observation O3 A plus B data. Now from 2023, the LIGO will operate in its fourth observing run, and we with a greater volume sensitivity. I mean, it will scan a much greater volume in the sky. So we expect that if there are such exotic events that I was talking about, about, I mean the GW190814 and all, if there are such events, then if there are a detection of these exotic mergers, then this bound will never be, like if we can say there are 1 or 2 transmuted black hole mergers, then there will not be any exclusion plots. Then we will get a region in the parameter space where we will have some mass of the dark matter and some cross section allowed. We will get a closed region, not an exclusion.
Another question is that for the self-annihilating dark matters, so you are saying that when two dark matters annihilate, so new particle can be generated, and so some heat will get generated. So is there any possibility that when the new particles is getting generated, and it can have the escape velocity greater than the bound, so that it can come out and we can detect it?
Yeah. There was recent work on it in arXiv. You can just look for it. Like the people who are working on, like in the neutron star itself, the dark matter particles are interacting with each other, and they are producing some like they're interacting with a long mediated thing, and the long mediator, is the thing just which has like a higher energy. I mean higher mean free path. So it escapes from the neutron star, and you can detect those mediators, and you can say you can put constraints on the dark matter parameter space. Yeah.
Yes. Yeah. Okay. And another question is that I don't know whether white dwarfs can be, because it's a compact object. So is it can be a good form of dark matter?
White dwarf, you can check. I mean, my advisor has works on it. Anupam Rai and Basudev Dasgupta both has papers on the same dark matter capture in white dwarf. But the thing is, like, white dwarf is not that dense that the neutron star is. So you will get I mean a more conservative bound. But yes, white dwarf is also a compact object, and people have studied white dwarf also.
Is there any kind of density bound that beyond? Sorry, is there any density bound that if we are not so much dense, we can't detect the dark matter? Like, I think is there any kind of bound on the compactness so that?
No, it's not like that. It's like you will have to get the stellar target should be very high, that I was showing that for neutron star it was 10 to the power 57, so that your dark matter gets to interact with a lot of particle, and as they're weakly interacting, so you need a lot of particle. Like it's always probabilistic that whether the dark matter particle will interact or not. So you need a very high number of stellar targets, and you need a very dense object, in the sense if you want your dark matter to be captured, then the escape velocity should be very high, so that it cannot escape the star. So this is how it works. There are not such density bounds. We always work with neutron stars or white dwarfs only, because these are the compact objects we have. I mean, astrophysically discovered compact objects. Yeah.
Thanks a lot.
Yeah, thank you.
Okay. So thank you, Shulagnadi. I mean, I guess your talk will inspire a lot of theoretical physicists in astrophysics, interested in astrophysics, as most of the students are actually interested towards astro and cosmos. So thanks a lot. We have been very happy to have you here.
Thank you.
So we're looking forward to more interactions in the future. So,
yeah, sure. If you have any questions or anything, you can drop me an email. Yeah.
Yeah, absolutely.
Thanks for having me.
Okay. Sure. We are pleased. Okay. So now we'll be moving on to our next speaker. It's a little different taste. His name is Ankit Dhaka. He is a student at Institute for Plasma Research, IPR. He works in the field of plasma physics, and today he shall be giving an overview of theoretical, experimental, and computational studies of plasma physics at IPR. Mr. Ankit Dhaka, you can speak now.
Yeah, hi. Thank you, Alake, for a nice introduction. So let me try to share my screen and tell me if you guys can you hear me?
Yeah, we can hear.
Yes, you're audible.
Okay. So let me share my presentation. and see if you can see. Hello? Do you see the screen?
Yes, it's visible.
Is it in the full screen mode?
Well, it's just going on and off. Something is happening. I'm not getting it. Like it went off again. It's on now. It went off now.
Okay, let me just disconnect and then reshare again.
Sure.
Is it visible now?
It's black. It's not visible.
It's blank.
It's black. I mean, your screen is it's visible now.
Yeah, now it's visible. Yeah.
It's now visible.
Okay. Is it in the full screen mode?
It's in the full screen.
Yeah.
Okay. Yeah. So I'll start now. My name is Ankit Dhaka. I work in the fundamental plasma experimental division in IPR. And for those who don't know, IPR stands for Institute of Plasma Research. It's a lab located near Ahmedabad in Gujarat. And we work on the theoretical, experimental, and computational studies of plasma physics, ranging from a very fundamental level to very complex geometry such as tokamak. So I'll start with the definition of. So I'll just tell one thing. So my idea is that you can stop me at any time during the talk and ask any question that might come up. So I'll start with the introduction to plasma. So the plasma is basically a collection of charged particles which show two important phenomena. One is that even though the system is having the charged particle, macroscopically the medium is almost neutral. So what do I mean by that is that if I select an area which is larger than the system, larger than the dimension of electrons and ions, the total charge that I find inside this is almost zero. And another thing is the collective behavior. By collective behavior, I means that if I share a part, if I produce a perturbation in one part of the system, that perturbation is going to be traveled. So that basically arises because of the forces that we see in plasma are electromagnetic nature, and they generally have a long range order. So that is responsible for the collective behavior. And since it is a many body system, many body charge system, the physics is quite complex for this system. So there are a few important properties of the plasma, one being the plasma density. So the plasma density is basically the density of electrons in the medium. And since these electrons are having continuous collisions with the neutrals, with themselves, and they are getting supplied by some energy, so they have a velocity distribution. So just like we see in statistical mechanics, they follow a Maxwellian distribution usually in unperturbed conditions. So they have a finite temperature that we usually say the plasma temperature. And then we have two another quantities, that is the plasma potential and the floating potential. So by plasma potential, I means that if I measure the potential of an charged particle inside the plasma, that is basically the plasma potential. And the floating potential is if I put a probe, suppose I put a wire inside the plasma, what will happen is that the electrons will come toward this probe. Why they will come is that because they have very high mobility, and due to the high mobility, they will start getting collected on this wire. And as compared to the ions, the electrons are very, very light, around 2000 times lighter than the ions. So they'll get collected on the probe, and as a result, the probe will attain a negative potential. So that we call as the floating potential. So these are the few properties by which we can classify the plasma. And moving on, we can find the plasma all around us. Almost 98% matter in the universe is in the plasma state. And in this figure in the right hand side, we see where they occur. The x-axis is the number of charged particle density, that is basically the density of electrons, and on the y-axis we have the temperature. So here we see that the plasma can attain a very high temperature, up to 10⁸ Kelvin in the laboratory experiments, as well as in the intergalactic medium. And we also have very small density plasmas such as flames and the solar aurora. So here I see few pictures. So the first picture is something called a laboratory dusty plasma. So laboratory dusty plasma is a plasma normal ion electron plasma in which I have introduced some few micron sized object. So, or maybe a nano-sized object. So what will happen is that the objects will attain a floating potential, just like I described in the last slide. And the system now has three components. You have electrons, you have ions, then we have the dust particles. And since there is a large difference in masses of these three particles, the time scale with which they interact has also a large variation. So the dust particles, since they are very massive, they have very slow time scales. Then ions, then electrons moves very fast, so they have very fast time scales. So these types of systems are also called as complex plasmas. And then in the next picture, we see a plasma torch. So this is a plasma which is flowing from a tube to outside, and here you see a finger is the plasma is getting touched by a finger. So this plasma torch is also one of the few industrial applications of plasmas that we have developed here in IPR that are used for various skin diseases, treatment of skin diseases and waste disposal. Then the next picture is a solar comet, and then we see a plasma in tokamak, and then the northern lights that we see on the poles, that are basically the charged particle, the solar flares that are getting traveled from sun to earth. And since the magnetic field at the poles is very strong, so these particles bound to magnetic field, and then we see these lights at the poles. So here I briefly describe about IPR. So IPR basically has three institutes. So first one is the Center for Plasma Physics that is located in Assam, Guwahati. And then there is ITER India, which is the domestic agency for a very large international collaboration in the tokamak physics. And then the last one is the Facilitation Center for Industrial Plasma Technologies. So here we use plasma to immediate societal applications, and we do number of studies ranging in these four fields. First is the experimental studies. So we have we have 10 to 12 plasma experiments that are directly linked to the academic purposes. And so here we have a plasma physics, fundamental plasma physics experiment, then plasma diagnostics, and then tokamak and fusion research. And simultaneously, to support the experiments, we have a computational studies division that do the fluid simulation and particle in cell simulation and molecular dynamic simulations to corroborate the results that we observe in the experiments. And that is also supplemented with the theoretical studies, including nonlinear phenomena and laser plasma interactions. And then the last but not least is the plasma application, that is mostly engineering, but there are few students working in plasma pyrolysis system, plasma jet technology, and plasmas for waste disposal system. So I'll move to very basic plasma experiment, that is the dusty plasmas. So while discussing these experiments, I'll also talk about how the plasmas are being produced and what are the studies basically being done on these experimental systems. So till now, if anyone has any questions, they can ask. Okay, so I'll move with the dusty plasma experiments. So basically, dusty plasmas are formed by doing a DC or an RF discharge. I'll tell you what a DC and RF discharge is. So basically, what we do is have an electrode, and we give a power supply to these electrodes. So what will happen is that these electrodes are kept in vacuum, and since we have few stray electrons always present in the medium, those electrons will get accelerated and they'll get some energy, and by that energy they'll strike the neutral atom present in the medium, and those neutral atom will then get ionized, and they'll also lose an electron, and then a plasma will be formed by ionization of the gas. So what will happen is that once the plasma is formed, as I told you, plasma is macroscopically quasi-neutral. So there is no strong electric field present in the medium. But since I have applied a field, my electrodes are at a finite potential. So what will happen is that in the vicinity between the powered electrode and the plasma, there will be a strong electric field generated. So this electric field we call as a sheath electric field, and in this sheath electric field, if I put a particle, dielectric particle, what will happen is that the particle will get negatively charged. And since the particle is getting negatively charged and the gravity is pulling it down, what will happen is that the particle will float in the air, where mg and qe are balanced. So, so one of the beauties of this system is that the particle that we introduced in the systems are of micron size, and it is very easy to see that particle using a normal visible camera. So what we do is that we shine the particles by laser light, and then we collect the scattered light using a high-speed camera. So here what you are observing is that basically you are getting all the kinetic properties of the system directly. So in principle, you can say you are generating a full n-body distribution function from the images. So these are the system. These systems, since you have very fine information, particle level information of the experiment, these are excellent for studying the hydrodynamic theories. Then if you make a flow in the plasma, that you can see in the top image. So if I somehow create a pressure gradient where P1 is greater than P2, so what will happen is that the particles will flow in the medium. So yes. Yes, sir. Yeah. I'll take 1 hour. I'm presenting, so it will take 1 hour. I cannot switch in between. I'm presenting. Yeah. Thank you. Yeah. Hello. Hello.
Yeah.
You can hear me, right?
Yeah.
Okay. So where was I? Yeah. So since you have a very all the kinetic informations of the particles present, these are the excellent system to study the hydrodynamic models, then the solitary structures by making a flow in the system and then exciting a solitary wave. So we see the solitons in dusty plasma, then the interaction of different type of solitons, and another tuning parameter in this experiments is that you can control the charge acquired by the particle. So by controlling the charge, you can control the correlations in lengths and time, and that will allow you to study the phase transition. So you can take the system from liquid to solid state and so on. So the first order phase transitions and the second order phase transitions also can be studied in this system. Then I'll move into next experiment, that is the large volume plasma device. So as I told you, so the plasmas in the intergalactic space are basically boundaryless plasma. So they are very large in size, and there are almost no effects of boundaries. But when we produce a plasma in a lab, what will happen is that I cannot make an infinitely large system. So here is an attempt to make a boundaryless plasma to study atmospheric physics, and I'll briefly tell you about this system. So basically, this is a 1.5 meter diameter linear device that you see in this picture, and these are the two pumping ports. So here we have two diffusion pumps that are labeled as diff stacks, and using these two vacuum pumps, we generate we achieve a very low vacuum, that is 10 power minus 5 millibar, and then the plasma here is produced by thermionic emission. So unlike in the last device where the plasma was formed by ionization ionization using the stray electrons, here the electrons are accelerated by this grid. So on the left hand side here you see that there is a source, we call it a plasma source, and here basically we have a number of tungsten filaments. So just like we used to see in the incandescent bulb. So we have a tungsten filament, and when the tungsten is getting heated up, it emits the electron. Then what we do is we negatively bias this source, and due to that negatively bias, the electrons will get accelerated towards the right hand side. And then there is also the electromagnets present in this geometry that are not shown here, that gives a magnetic field in the axial direction. So the electrons will follow the magnetic field by gyrating around the field lines, and then they come towards the right hand side. And here in this chamber there is something called a electron energy filtering system. So basically it's a magnetic filter that will stop the energetic electrons, and in the target region, I'm labeling it as T, is a very calm plasma. So here there are the studies of magnetohydrodynamic waves. One of them is a Whistler wave, then the turbulence in plasma that is induced by electron temperature gradient, and other plasma transport phenomena are studies. And the plasma in this device is getting, for the diagnosis we are using what is called a Langmuir probe. So Langmuir probe is basically a cylindrical wire that I was showing you in the first slide, and you just put a voltage here and then collect the current, and from the VI characteristic few plasma parameters can be estimated. So that's a whole different theory. And moving on, next is a device which is called as a non-neutral plasma. So the idea is if I keep a gas in a chamber, what will happen is that the neutrals will be present, and somehow if I ionize that gas, the number of electrons will be equal to the number of ions. So in order to produce a non-neutral plasma, what we do is we take a chamber to very, very low pressure. So here we achieve a pressure of 10 power minus 10 millibar, that is 13 order less than the atmospheric pressure. So here the neutrals are basically almost negligible. And then we have again a thermionic emission from the left hand side. Here you see a filament labeled, and from here the electrons are getting injected, and using the same negative biasing technique that I shown you for LVPD. But this time the machine has a toroidal geometry. So basically it's like a medu vada that we see, and there is a magnetic field going on in the toroidal direction, and that will take the electrons from the injector grid to the collector grid. And here we have seen a tremendous amount of confinement in this geometry, and you can refer to this paper by Dr. Lachwani. And currently, the studies are going on to install some fluorescence diagnostics in this system. Okay. Next, I'll talk about the confinement of plasma. So how do we can make a plasma to stay in a particular geometry? So the studies in 50s and earlier also found out that there is a very nice configuration which can be used to study the magnetic confinement. So here what we do is these are the two electromagnets. The green thing that we see are the two electromagnets, and due to the electromagnets, these are the magnetic field lines. So what I have done is that I have pinched the magnetic field line in a linear geometry at the two ends of the cylinder. So if I take a fluid and assume that it's in magnetic field and solves the equation of motion, I can easily find out that there exists a constant of motion, that is the magnetic moment. So what it will do, since it's a constant, what will happen is that when the electrons go in the high field regime, what will happen is that since mu has to be constant, if B increases, the V perpendicular will decrease. So what will happen is that the electron will get reflected from the high field region. So due to this effect, it is known, it's famously known as a magnetic mirror machine, because it is reflecting the particles from the two ends, and this happens because the magnetic field B is varying in Z. So this was the very initial attempt to confine the plasmas, but there lies a problem. The problem is that if you have a very high energetic electron, what will happen is that the field might not be enough to reflect it back. In that case, the energetic particle will escape from the distance very close to the axis of the cylinder. And since you are losing energetic electrons, you are losing a lot of energy. So somebody in Russia thought that what happens if I close the two ends of this device? That means if I close this, make it a circular or a toroidal device and close this. So here you by doing this, you reach to a geometry that is called tokamak, and in Russian it translates as toroidal chamber with magnetic field. So here comes the concept of tokamak to confine the plasma. Why do we are confining the plasma? I'll explain in few slides. So what will happen is that since the linear device has been joined end to end, and now we achieve a toroidal geometry, just like the method I explained. So we get a device that is similar to tokamak. So this is also one of the experiments in our lab that is known as beta, basic experiments in toroidal assembly. And here in the left hand side picture you see a lot of magnets. So these are all square shaped magnet. They are surrounding the toroidal assembly like this. So when current flows in this direction, what will happen that they'll generate a toroidal magnetic field. And due to this toroidal magnetic field, what will happen is that the electron will try to follow these field lines, and as a result, they will be confined in this configuration. And this is an excellent geometry to achieve the confinement. And this machine that I am showing you is producing the plasma same.
Hello.
Hello. It's paused, right? Uh,
There is a
Hello.
problem. Network.
Yeah, probably he faced a problem. I mean, does he know about it? Is everything is paused? Can you maybe text him or something? Contact him somehow.
Okay, I'll
I request our viewers to wait for some time. Shanshan, please try to contact him. I don't know whether we should proceed or not.
okay. Let's wait for 2-3 minutes for him. I mailed him. Probably there is some internet issue or something. I mailed him. Let's see what it is. We'll wait for 2 to 3 minutes. Then we'll.
Okay, we'll wait till 4:20 maybe, and
Yeah.
we'll continue if he doesn't respond. We request our viewers to kindly wait for some time. Our speaker has encountered a technical issue and network issue probably. So we'll be back in some time. Mr. Ronak Chatterjee, I mean, if we ask you to present your talk now, will that be a problem?
No, it's not a problem. I can start right now if you like.
Okay. Then just a minute.
So tell me whenever I have to share my screen, I'll start sharing at that moment.
Yeah, I'll inform you. Okay.
Okay.
Okay, so we are back again. The last speaker probably encountered some network issue and he isn't able to join with us. We aren't able to contact him. So we are moving on to our next speaker. Our next speaker is Ronak Chatterjee from TIFR Mumbai. He works in the field of nano and mesoscopic optics. Today he will be delivering a talk on the basics of quantum cryptography and recent developments in free space quantum cryptography. Mr. Ronak, you can take this.
Yeah, thank you so much for introducing, and thank you so much for having me here. I'll start sharing my screen. Yes. Okay, is my screen visible?
Yeah.
Okay then. Okay, so good afternoon, everyone. I am Ronak Chatterjee. I am a PhD student in Tata Institute of Fundamental Research, working in the nano optics and mesoscopic optics lab. But as you can see, we don't work on nano optics and mesoscopic optics. We are working on something called quantum cryptography, and I'm so much interested to talk about it with you guys. This is a very new and emerging field, and it shows promise in the near decade itself. So I thought that in this moment where new faces are coming around, it's better that we know the basics of this thing so that you can go ahead and explore this upcoming field. So I'll talk about quantum cryptography, which in scientific terms is called quantum key distribution. I'll tell you why that is called. I will talk about the basics of it and also show some recent developments over a few years. So let's start. Okay, let me get my laser pointer on. So the natural question arises, what is cryptography? Well, it's the method of encrypting, transmitting, and decrypting a data. Well, the will to...
Sir?
Yeah.
I mean, are you have you started showing your slides?
Is it not visible?
I mean, your screen is visible. I can see the Teams icons, but then the slides are not visible.
Just a second. Is it visible now?
Yes, it is.
Okay. Sorry, I'm actually new to Teams, so...
It's okay. Don't worry.
Anyways, okay. So yeah, I talked about quantum cryptography and things. So everything's visible, right? Like what is cryptography and all. Okay. So the question is, what is cryptography? The method of encrypting data, transmitting and decrypting data is called cryptography. Well, the will to share secret messages is as old as language itself, when language developed, people are trying to say things secretly to people. And in the modern time right now, this method of encryption and decryption has become a daily part of our life, not only just in our social media and stuff, but also in like economic transmissions and banking stuff. So in any cryptography scheme, someone's mic is echoing back. If it's okay, you can mute. Okay, thank you. So in any cryptography scheme, the major role is played by a thing called a key. A key is nothing but a very big binary number. And that what the key does is that it helps you to encrypt the message. What you do is that you take a plain message, you convert it into binary, and you add the key. Once you add the key, which by its nature is very long and very random, it will create a message that is totally ineligible. It is called a crypto message. Once you transmit that crypto message, you can use the same key. You can subtract that binary number from the crypto message to get back your plain text. Well, the method of cryptography is very old. Like the picture that you see over here right now. Let me get my laser pointer. Picture that you see over right now is a method that was used by the Spartan military. This was a long stick on which you could actually wrap around a paper on which like sequences of things were written.
Hello.
Yes.
I'm really sorry to interrupt once again, but then your slides are probably not changing. I mean, it's still they're stuck in the first page.
Okay, I have allowed the access to. I have allowed access to the teams about this, but it's not.
Yeah, now it's.
Okay, let me do for entire screen. Maybe the entire screen will help. Allow. Is change of slides and things are visible right now?
What is cryptography slide is visible? I mean, you just change one slide so that we can see whether the slides are changing.
Now I am in slideshow mode. Can you see the change in slides?
Yeah, you are in slideshow mode. The first what is script? The changes.
Changing,
the changes are
okay.
visible. Okay. Okay, go
Okay,
on.
I thought maybe I should have shared my entire screen from the beginning, not an application. Sorry about that. Sorry about that.
It's okay. It's okay. Don't worry about it.
Yeah. So as I was talking about this, you can see my laser pointer, right?
Yes, yes.
Yeah. So this instrument was used by the Spartan military, where like these sticks were available with the commanders, and they would wrap around this encrypted message that would be a long strand of random written words. When wrapped around, you would get the message back. Well, one of the most famous, or rather infamous, example of cryptography machine is the German Enigma machine. Well, it is a very innovative concept of cryptography, but it also had a major flaw, which was broken by Alan Turing during the World War II. That also led to the development of the first computer in the world called Colossus. So let us talk about two major encryption methodologies that we use till date. First is called the public key encryption. What we do in that, suppose you make a locker in which you distribute to public openly. Like if you want to send me a message secretly, I give you the locker, you lock your message inside that locker and send it to me. So what does this mathematically mean? Mathematically mean that there is a certain function which are called one-way functions whose computation in one direction is simple, or rather the time scale is linear or polynomial, while the backward computation of this function without certain informations would be exponentially long. Like for example, if I tell you, if I multiply two prime numbers, you would multiply it very easily. But if I want to tell you to factorize a prime number, you would take a lot amount of time. So this is called a one-way function. Multiplying a prime number, but prime factorizing a big number is a one-way function. So a sender would send a locker, which is a one-way function. The one who wants to encrypt his message would put the message into the locker, and then the receiver would have a key for that locker. This key for that locker is that missing link, that missing piece of information, which was not allowing me to compute the backward function properly. One of the major example is the RSA encryption technique. This is a very commonly used technique, or rather it's like advanced successors are used right now. For example, in bank, when you ever do transactions, you see this word called SSL encryption, secure socket links. These are all based on this basic example of RSA algorithm. So schematically, it looks something like this. You have a public key that is distributed to the public. They would use this to scramble data, and the private key is private with the one that is receiving the data. This is called public key encryption. The only flaw in this method is that these are based on this backward, this one-way functions, which for these recent, what do you call? For the recent technologies that we have are like exponential time to compute. But with developing techniques, developing computation methods, and also advancement in quantum computing, this is just like a matter of time before these all are broken and everything can be decrypted. So this is a reference to the RSA method. You can look at it if you want. There is another method called private key encryption. In this, the two parties have the same key, the same random binary string of numbers that you can use to encrypt as well as decrypt. The key is called information theoretic secure. What does this mean? It means that if you have a very long key and it's completely random, there is no correlation among the key, the parts of the key, then if you encrypt your data using such a key, then there is no computer in this world that can decrypt it, like in finite time at least. So this is called information theoretic secure. But as you can understand, the catch is that the key has to be completely private among the two individuals. One of the best example is Burnham one-time pad. You would be like astonished to know that this was developed during the First World War by this person called Burnham. So you have a shared secret key. This secret has to be a complete secret between the sender and the receiver. This is the paper of 1926 of Burnham one-time pad. You can look at it if you want. So how does quantum theory helps us? Well, classical information can always be copied. Let us see an example. Suppose you have a sender Alice and a receiver Bob. Alice encodes her information by putting 0 to a low laser level and a 1 to a high laser level. Suppose you have a pulsed laser which is sending low and high signals. So you call it as 0 and 1 and sending to Bob. Bob is receiving that and tagging it as 0 and 1. But suppose an eavesdropper, conventionally called Eve, wants to copy it. For her, it's very easy. She would just put a beam splitter. Okay, now I'm assuming that people are like privy with these facts called beam splitters and light amplifiers. If not, you can just ask me. I can tell you about them. Is it okay?
Yeah, sure.
Yeah, okay. So suppose an eavesdropper wants to copy the information. For her, it's very easy. She would put a beam splitter, get half of it, and the other half she can amplify and give it back to Bob. So Alice and Bob won't even know that the information has been copied from in between. But suppose we encode the information in a single quantum particle in one of its quantum states. Say, for example, a photon's polarization is a quantum state. Like suppose if I say it's a 0 degree photon, means it's a quantum state at 0 degree, a 90 degree polarization photon is a quantum state 90 degree. If I encode my information in the polarization, then you are producing a qubit. You are encoding information in the quantum state of a single quantum particle. But how does it help? Well, there's a theorem called no cloning theorem. Let us first get to the principle of it. It says that it is impossible to create an identical copy of an arbitrary quantum state unknown a priori. The best is that we see an example of this. Suppose that you are being given a photon, just a photon of particular polarization theta, and you don't know what that theta is. How would you find what that theta is? Well, usually you would say, okay, give me several of these photons, then I would put it through a beam splitter. Then there is sine squared theta probability of hitting detector D1 or cos squared theta probability of hitting detector D2. But as I said, you need multiple photons of same polarization theta, right? To sample over and get the value of theta. But for a single photon of polarization theta, if it passes through a polarizing beam splitter, which actually transmits or reflects based on what polarization it is, you can only say that the photon either hit this detector or this detector, which means you would say that either the photon is 90 degree or 0 degrees, but you cannot say what the photon theta is. So just because you didn't know a priori what the angle of this photon was, the polarization angle of this photon was, you cannot copy it. But best choice is single photons, because first of all, they are experimentally available by lots of techniques. They're the fastest information carrier, of course, and a variety of producible quantum states. Like polarization is the most available and easily you can manipulate photons, polarization states easily. But there are other quantum states of photons, like its optical angular momentum, or like in what time they come. These states of photon can also be used to like encode information into a qubit. So let us get into a little detail of how this theorem works. Like if I will try to establish this logically. Suppose there exists a machine A that can clone. Let us assume that can clone. So starting from initial state 0, if it see a state S, it will go to another state S and it will create a clone of this state S. So A0S becomes ASSS. Now, suppose two basis states exist, the up-down, which is the 0-degree polarization, and left-right, the 90-degree polarization. So any arbitrary state can be written as alpha up-down plus beta left-right. So suppose I send this arbitrary state in which alpha and beta will be unknown to me a priori. I don't know what their values are. If I send it through this machine, I would get a copy of these individual states, right? Like 2 up-ups and 2 down-down, with the machine going to a vertical and a horizontal for each state. Now suppose if I make a machine in which the a vertical and a horizontal states are equal, that is the final state to which the machine A goes is independent of what polarization it is, then you can take the a vector out, and what you are remaining with is a pure state of 2 up and 2 down. This is a pure state. But just because this is a pure state, there should also exist a linear operator that can achieve it from the ground state of the photon, that is the vacuum state. So let us assume that such an operator exists. We can write it as alpha A dagger vertical and a beta A dagger horizontal whole square, because 2 of them are being created. That is the only way you can write it if you want to keep it linear, as well as you want to make 2 of them. But if you use this operator over the ground state, you will find that there are 2 ups and 2 up down and 2 left right created, but also a cross term created. So there is no linear operator that can make you achieve these state. You are always ended up with this cross term. So there is a contradiction. So even if you try to clone an arbitrary state, assuming that a machine A exists that would give you this, there is no linear operator in quantum mechanics that can allow you to do this. Exactly the same derivation in a much more detailed fashion is done in this paper. A single quantum cannot be cloned. You can have a look at it, and like why this theorem became so much important in any quantum applications that follows it. How do we use this to our advantage? Say there is a sender called Alice that sends polarization states randomly in something called 2 mutually unbiased bases. What do you call 2 mutually unbiased bases? Mathematically, it looks like this. Like if you have a basis B1 of dimension D, another basis of the same dimension but of different kind, if you find the inner product of them, you would get 1 by D. Simplest example is if you take a 0-90 degree basis of polarization and 45 degree 135 degree basis of polarization. So think of it like this. Suppose you have a 45 degree polarization light and you want to measure what is this polarization. You can decompose it into 1 by root 2 0 plus 1 by root 2 90 degrees, right? So what does that mean? It means that whenever you are trying to find what is the component of 0 and 90 in a 45 degree polarization photon, you have equal probability, both of them being half, right? So they are mutually unbiased. It means that if you take any basis B2 from any basis B2i from B2 and find the inner with any B1, you will always end up with equal probability or equal probability density, whatever you call it. Why use mutually unbiased basis? So that you cannot do complementary measurements. Like as I said in the beginning, like let us like encode qubits is 0 degree as bit 0, 90 degree as bit 1. That is a complementary measurement. Suppose you are measuring 0 degree, but you don't get 0 degree. And if you know the other qubit is, other state is 90 degree, then you can always do complementary measurements and tag your photons as 0, 1, 0, 1. But if you are in a mutually unbiased basis, say your qubit's 0 degree polarization is 0 and 45 degree polarization is 1, that is the bit value, then you would never know which one is which, because they are in 2 different bases that are mutually unbiased, which means the probability of each of them being in the other basis is equal. So for any d-dimensional basis, there are always d+1 mobs, that is mutually unbiased basis. For example, in polarization, which is a two-dimensional basis, you have three like mobs. One is the standard 0, 90. Other is the diagonal, that is 45 and 135, which is 1 by root 2, 0 and 90. And then there is a circular polarization, that is 0 plus I90 and 0 minus I90. This left circular and right circular. So like you encode information in these mob states, the receiver called Bob would measure randomly in either of these bases. Like you would encode your information in 045, 045 and send to Bob. But Bob, he would also have no a priori information of what basis was chosen by Alice. So what he will also do, he will start randomly measuring the photons in any random basis he gets. Now you would be like wondering, since I cannot copy a quantum state, then how will Bob measure? Well, that is the trick over here, and that is the trick that the people of this people who develop these quantum protocols will be utilizing. Is that yes, it's true that Bob doesn't have an a priori information of what was the initial polarization that Alice said, the sender said. But then again, what Bob is doing is he is measuring it randomly, right? So there is some probability of like correct measurement, and in ideal case that there is a fixed value. So if the measurement is done between only Alice and Bob, you would always get a fixed statistics. You will not go above the statistics. You can go below that if your detectors and all are non-ideal, but you will never go above the statistics. But even eavesdropper comes in between and starts doing the measurement, you would start changing statistics, and that is when like you understand that your channel is being hacked. We will talk about this more as we go into the protocols. So at the end of the communication, the Alice and Bob will now like talk about the basis, like what basis I send in and what basis you chose. Now you will be wondering that if I am like talking about basis, then my key is released, right? No, the key is not released. See, in a 090 basis, Alice could have seen 0 on 90, and in Bob has no idea what was measured, 0 on 90. He wouldn't release it to Alice that what I measured. He would only release what basis that I measured. Did I use standard basis? Did I use diagonal basis? Similarly, Alice would also say, did I use standard basis? Did I use diagonal basis? Using this, they can like talk amongst each other and establish a key that is same between them. We'll talk about it when we get to the protocols. Keep the bits of the bits for which the bases match. After they have matched the bases, they know that the key between Alice and Bob is same. They can share 10% of that key to like match, to like verify if really the key that is shared between Alice and Bob are same. Because you have to verify that. Without that, the one-time pad won't work. So what do you do in a quantum key distribution? In quantum key distribution, the secret key is being sent by single particle quantum states as qubits. So you have two channels of communication. One is the quantum channel, other is the classical channel. In quantum channel, you send the qubits. Bob would measure in random basis. Alice would send in random basis. After that, in classical channel, they would like reconcile among them what basis they used. And when eavesdropper try to like hack in this channel, classical channel she can always have, that's okay. But whenever she hacks into a quantum channel, that is where statistics starts changing. When they are going to like reconcile with each other, they would see that the expected statistics would deviate, and then they would know that then hacking is being initiated in that channel. So no cloning theorem provides a natural defense against key cloning. And due to the inherent random nature in the quantum processes itself, the key generated is completely random. So as I was talking in private key encryption that it has to be completely random, very long, quantum mechanics already takes care a lot of these. So possible intrusion by Eve is also detectable in the system. If you want to read about quantum cryptography, like a very good review article is by this guy, Nicholas Gissin. This is a very big one, but it's a very good one you can try. So let's talk about the first protocol of quantum cryptography, which is called the BB84 protocol, introduced in the year 1984 by Bennett and Bassard, like very intelligent people. They had done. Like, this is one of the most secure QKD protocols. So how does this protocol work? Alice, on her side, would choose among four polarization states. among two bases and four polarization state. One is called the plus basis, another one is called the cross basis. Basically 090 or standard basis, and the cross is 45 135. She would switch among four separate polarization, and she has tagged them as 0 degree to be bit 0, 90 degree to be bit 1, similarly 45 degree to be bit 0, and minus 45 degree to be bit 1. This is how it works. Alice at random will choose any four of this polarization and keep a track of them. Like she would send like this one basis, she has sent this as minus 45, so she keeps it as 1. She has sent this 1, so she keeps it as 1. This is her private key that she is keeping. She would randomly choose among these four polarization states and transport it to Bob. Bob on his side will choose a basis for measurement. Mind it here that it's a basis of measurement, not the exact photon polarization. He either chooses to measure in the plus basis or the cross basis. So whenever he chooses to measure in the plus basis, as you can see that either if it's 0, it will always tag as 0, but if it's 90, it will never be tagged. Similarly, if it's 45 basis, if it's 0, it has a like 50-50 probability of hitting the minus 45 plus 45, but it has a 0 probability wherever it's minus 45. So whenever a correct bit is sent, whenever a correct polarization is sent by Alice and Bob chooses the correct basis of measurement, then their keys match. As you can see, he has sent a diagonal photon, but Bob chooses to measure in a plus basis, right? So this is incompatible. So this is rejected. This is after the transport has been done. But look again here. Alice has sent a diagonal the standard polarization, and Bob has used a standard basis for measurement. So this time things should match, right? Once again, if you're using a cross basis, Bob is using a cross basis, but Alice has sent a standard basis polarization. So this would be incompatible. So whenever there are compatible bases, Bob would know that whatever polarization I'm seeing the correct polarization. Like if Alice chose a plus basis to transmit and Bob chose a plus basis to measure, then whatever polarization, be it bit 0 or be it bit 1, Bob is measuring it correctly. So whenever their bases are matching, they know for sure that their bits are going to match. So whenever their bases match, they're using those parts only to create a secret key. Now think of it like this. Whenever a eavesdropper comes in between over here to hack, what she will do, the best she can do is take a similar kind of setup as Bob is using over here and place it over here. But look at this. When she is intruding into this system, she has an uncertainty. Suppose she chooses a wrong basis, okay, then she has to send something, right? She cannot hold the photon back because Alice and Bob would know that photons are missing. That is a clear-cut indication that our channel hack ho raha hai. But when eavesdropper comes in between and tries to do a similar kind of measurement like Bob, she has to also send photons by guessing so that she remains consistent. She doesn't get exposed due to loss in photons. So inherently, if she is guessing by making choice of wrong basis to send to Bob, she is changing the statistics of the whole measurement system, and this change in statistics of the whole measurement system is going to tell you that your system is being hacked. So let us get into more, as I described to you, how does it work? Like whenever the bases match, you know the polarization is same, and you would say that ठीक है, मेरा key is same. A very simple experimental setup to do this is using a Pocal cell. A Pocal cell is nothing but an electric field controlled polarization switcher. So you have a single photon source and you would use a polarization switcher to switch between four polarizations. While on Bob's side, he has two things. One, a polarization switcher that switches between 0 and minus 45 to choose what basis you're measuring, and a PBS to put to two detectors am I seeing bit 0 or am I seeing bit 1? These two papers, this is the original paper by Bennett and Bassard. They described the BB84 protocol, and this was the first experimental demonstration using this very technique of the BB84 protocol. Although they didn't use 45-135, they actually used left circular and right circular. As I showed you, that is also a feasible basis to use. There is yet another protocol which we in laboratory actually use because it's simpler to execute. It's called the B92 protocol. It was developed by Charles Bennett independently and alone in the year 1992. It uses just two polarization states. This is a very ingenious way, like you don't have to use too many resources, but still you can achieve the same kind of cryptographic scheme. Use only two bases, two polarization states, 0 and 45. You encode your binary 0 to 0 and you encode your binary 1 to 45. It's a little less secure BB84, but let me describe how it works. Suppose you send a 0-degree polarization and Bob chooses to measure in the 0 basis, that is 090 basis. So you are sure that if you're measuring in the 090 basis, you will see a 0. But if he is sending a 45, if Alice is sending a 45 and you choose to measure in the standard 090 basis, there is an equal probability that you can get in the 0-degree line or the 90-degree line. So whenever a 45-degree polarization is being measured in the standard plus basis, you know that a detector that is not supposed to detect will always click. I know you people will be having questions in this part, so I would be leaving this part in questions also, but I'll try to describe it slowly once again. Whenever you have a 45-degree polarization and you are measuring in the plus basis, that is 090 basis, there is an equal probability that 0 and 90 is clicked. So using this, you know that whenever there is an equal probability of both the detectors clicking, then you are seeing a 45-degree photon. But whenever you are sending a 0-degree photon and you are measuring in the cross basis, then similarly 0 will have a 50-50 chance of hitting in the 45 and minus 45 basis. In this way, this complementary measurement will tell you what photon are you seeing. Am I seeing 0? Am I doing 45? This table will help you understand. Suppose Alice is sending binary bit 1. So Alice sends plus 45, but Bob's polarization measurement is minus 45. So it has been rotated and it's going to click in the right position and giving the bit sequence 0, which means it is incorrect. As I said, whenever you measure 45 in the other basis, in the complementary basis, that is 0 and 90, then only you know it is same. For example, in this column, as you can see, Alice has sent a 45-degree polarization and Bob has chosen to measure in the 090 basis. So he's getting the same sequence. So whenever they choose complementary bases to measure, they are getting the same bit. One of the major advantage of this protocol is that, like unlike in BB84 where you have to like exchange bases after quantum communication has been done, in this case you do not have to like explicitly interchange bases. So it's less amount of back and forth information that has to be transmitted among Alice and Bob. Because it's a complementary measurement system, they can always know which basis they are measuring accurately. So this is the paper by Bennett that talks about this protocol. You can look at it. So let's look at some practical requirements of like executing these kinds of protocols. The two protocols that I've described right now, BB84 and B92 protocol, these are called prepare and measure protocols, which means you prepare a quantum state, you send it, and Bob is measuring it. The major requirements, as you would expect, that you need a very good single photon source. Without a single photon source, this doesn't even make sense. Like if you have a multiple photon source or a classical photon source, it is as good as Eve copying it by breaking it into parts. And you also need high quantum efficiency optics. This is a very important part. Why? Because see, every protocol that we've described over here right now is assuming that whatever Alice is sending, Bob is receiving all of it. He is not losing anything. Okay, so the statistics that I was talking about that would determine key above this, if I go below the statistics, then I know my channel is being hacked. This is only applicable when you are at a like you are at an ideal level. But even if you are a non-ideal level, there is a lower threshold below which you cannot go. Below which if you go, then you cannot tell if my channel is being hacked or my channel is so noisy that the statistics don't make any sense. So the high quantum efficiency optics and photon detectors are required to be above that particular threshold in the practical cases, so that you can distinguish between the cases that are you being hacked, or is your photon or is your communication channel is so noisy that statistics are all gone haywire. And precise time tagging and time synchronization instruments for both Alice and Bob. Well, this simple reason is that these are single photons, and photons are everywhere. You have to be very precise in the right tagging the right photons. If you do not tag the right photons, then you don't know if that photon is coming from a noise or is coming from the actual signal photon that the sender has sent you. thus increasing noise. There is another set of protocols, if that time permits, I'll discuss. It's called an entanglement-based protocol, EBs. They have an extra requirement that they would require is a generation of entangled photons, but we'll come to that later. Let's talk a little about single photon sources, one of the major requirements of any cryptographic quantum cryptography protocol to be executed. One of the best ways to do is using a weak coherent pulse. Like even in modern times, like the Chinese people have executed quantum communication from satellite over very long distances. Even the people who came before them, like Zeilinger and all, whom they did like a long distance communication and all, they use this very type of single photon source called a weak coherent pulse. The principle is very simple. Essentially, you mimic a single photon source. It's not actually a single photon source, but you are mimicking a single photon source. How are you doing that? Suppose you take a monochromatic pulsed single mode laser, which means single wavelength. Pulsed means that your photons are being concentrated in very short time intervals. Single mode means it has a single direction, that is, it's being directed. It is monochromatic, single wavelength, polarization you will set later, and pulsed means your photons are constricted within a certain time window, so that you can like set your mean values of photon within certain time window. So if you have studied quantum optics, or if not quantum optics, if you have studied quantum harmonic oscillator and all, you would know that these lasers are all coherent sources. A coherent source in quantum mechanics is always described by a coherent state. Okay, so when you take a laser and try to count the number of photons that arrive within certain time windows, you would find that that photon is distributed as a coherent state, or the photon number is distributed as a Poisson statistics. If you find like what is the number of photon within certain time window in this particular quantum state, that photon number distribution is always Poisson statistics. As you can see over here, then the mean number is defined by alpha. Now, what is our aim? Within that certain time window that I'm talking about for this pulse single mode laser, I'm going to make the probability of seeing more than one photon very small. That is, I'm going to take the mean number of photons n bar less than 1. What will happen if I make my mean number of photon very small? Most of my pulse, the pulse within which the photons are being constricted, those pulse will have no photons at all, because it's a Poisson distribution, right? If you have the mean number very small, the highest probability will be assigned to the zero photon state or vacuum state. So you can see this count is the highest, while the second highest probability is assigned to the photon number 1. So if you make your mean photon number very, very small, like in literature they use 0.1, people can go as low as 0.1, 0.01, whatever. If you make that happen, you can be sure that within the pulse that you're looking for, the photons, they will be always in a single photon state.
Mr.
Yeah.
Chatterjee. So I'm sorry to interrupt you, but I mean, since we are running short of time, can you please wrap it up within 5 to 7 minutes?
5 to 7. Okay, like then I'll talk about these single photon sources only. These are the only main parts that I was going to talk about. Okay. So how then this generation can be achieved? So this generation can be achieved by controlling the pulsing window and the intensity itself. So the pulsing window of this laser is controlled by something called an AOM, or acousto-optic modulator. It's a very simple device that actually creates a grating by sending sound waves through a media that creates a grating. So what happens whenever a laser beam comes, you have the 0th order and the first order, and this first order can be like this first order can be switched based on how we send in a pulse into this device. Like whenever there is a radio pulse incoming in this device, the first order diffraction light is there. Whenever there is not, the light is not present. Like if we send a RF, like this is a square wave modulated over a sinusoidal RF wave. Whenever this RF is present, this first order beam is present, which means that the photon is being transmitted. And whenever it is not, it is only the 0th order. So if you align your whole system to the first order of this system, you know that you have constricted your photon within this part only. So for the incident beam, if you attenuate this incident beam by a very small, like by a large amount, and then you pulsed it based on for how much time you're keeping this window open, you have essentially made a pulsed source in which you have a control over the photon number and the time for which that pulse is open. The pulse programming allows over the time window and the intensity of each pulse. is given by this expression. This is very simple, like power times time, the time window divided by the energy of each photon. So this is an experimental graph. So we have made a 100 microsecond window in which we have attenuated the pulse heavily and chosen the time window to be 100 microseconds. So as you can see that the 0 counts is maximum, then the next count is 1 photon state, then 2 and subsequent were totally missing. So this is how you create a weak coherent. What are the uses of equivalent pulse? Well, equivalent pulse is widely used in free space quantum communication, like surface to surface, like you are at point A and point B, you are sending photons from one part to other. You can also use from satellite to surface. For example, like the Chinese have used, they have executed a BB84 protocol by the same method. They have created a weak coherent pulse right over here. Don't be like intimidated by this picture. They are actually have only one beam path over here, but they have chosen to make so many laser diodes so that they can choose the particular polarization they want to send as required in the BB84 protocol. So all these laser lines are merged into one single line, and they're creating a single weak coherent pulse that is being sent from the satellite to the ground station where a measurement is being done. So weak coherent pulses are practically used for doing quantum communication. This was shown by Liao SK, by the Chinese group that does satellite to ground quantum key distribution in 2017. But weak coherent pulses are really vulnerable to a certain kind of attack called a photon number splitting attack. I'll talk about this a little bit. In photon number splitting attack, what happens is that your laser or your quantum state is not purely a single photon state. It's not just one, but it's a linear superposition of 1, 2, 3, 4, where 2, 3, 4s have like lower and lower probabilities. So whenever you are transmitting in like light from a very far apart distance, you have to initially start with a very large amount of light. Like you have to have your mean photon number higher than 1. What Alice can actually do, she can use the classical principle itself. I would I would be sitting very close to the satellite where the photon number is very high. I will break it and keep one for me and send the rest. So it's like you are breaking the photon state up and you're making a copy of it. This is the paper, the generalized beam splitting, that you can look upon to understand the photon number splitting error. But there is a way out called the decoy state protocol. I'll skip this because we're running out of time right now. But there are also true single photon sources. I think this is the last topic that I will cover. That would be best for everyone. There are something called true single photon sources. How do you describe a true single photon source? How do you test them? Well, the answer is anti-bunching. So let us understand what anti-bunching is first. See, suppose when the photons are coming very close by in time, look at the third line over here. You see the photons are coming very close by in time. They are described over here as particles, but if you consider them as like wave functions over them, you would understand that the wave functions are like superposed upon each other. So as you know that photons are bosons, and they can populate a single quantum state itself. So basically what is happening in this case, photons are bunched, which means that all the photons, their wave functions are superposed with each other, and all of them are sitting in the single quantum state, which means that you cannot isolate single photons over here. Photons are clubbed together. This is called photon bunching. Whatever light you see, light from sunlight, light from tube light, these are all emitters of bunched photons, which means that the photons are coming in like clumps. Then there is something called a random source, or a coherent source in case of laser, where the photons are sometimes clubbed to each other and sometimes they are not. As you can see, this distribution is random. But for a true single photon source, the photon would be very far apart from each other. As you can see, these two photons, they are like the distance between them is enough so that their two wave functions don't interfere with each other, which means you can essentially say that the photon wave functions do not reside in the same quantum state, even if they're bosons. This is called photon anti-bunching. Essentially, the photons are coming as single particles right now. How do you test them? The best way to test them is using a beam splitter. What does a beam splitter do? Suppose consider this stream of like these green balls. When it hits the beam splitter, for a classical beam, a beam splitter would have split the beam into two. But for a photon, it's a particle. It cannot go in two directions. It has to go only in one direction, right? It has to either hit detector 1 or hit detector 2. If you keep the two detectors at the same distance, then a photon in this stream, in this stream, whenever it hits the beam splitter, it either has to hit detector 1 or it has to hit detector 2. It cannot hit them simultaneously. So whenever you are measuring coincidence among these two detectors at equal time, this is what this delay does. At zero delay, if you can see at this zero delay, or they haven't put this zero delay because there is delay in this channel that they have to compensate for. Like whenever the distance between these two paths are equal, you can see there is a dip in the coincidence, which means that whenever your photon is a single photon source, your two detectors will never click simultaneously. On the contrary, if you look at this lower line where the photons are clubbed together, whenever they come at this beam splitter point, one of them will go here, two of them will come here, or two of them goes here, one of them come here. So at the same time, there would always be a click and they would start rising. So you won't see a dip, you would see a straight line over here. So anti-bunching is a test whether your source is a single photon source or not. Mathematically, it is described as this, that is the correlation between the photon numbers on detector 1 and 2 at two different times divided by their mean number. So you categorize your single photon source based on the value at tau is equal to 0. That is when the two detectors are sitting at an equal distance. For greater than 1, it is bunched, which means the photons are coming in clumps. For G2 is equal to 0, since there would be no correlation, they would always like spread out randomly, and this is called coherent. And where is less than 0, it is called anti-bunch. Okay, I shouldn't have placed these values zeros. These should be actually ones. It is G2 equal to 1 and G2 less than 1, not zeros. This is an offsetted value by 1. Like usually when we do an experiment, we usually offset it so that we can see positive, negative rising. But in literature, these values are all 1. G2 greater than 1 is bunched. G2 equal to 1 is coherent. And G2 less than 1 is called anti-bunch. So anti-bunch sources are true single photon sources. So I think since I'm running out of time, I'll talk about this last. Is that there was this experimental demonstration, first experimental demonstration on photon anti-bunching using stimulated emissions from sodium atoms. Let me take you through this experiment. There is a sodium atom right over here, and there is a pulsed laser that is coming over here. So whenever there is a pulsing in this laser, there is a stimulated emission, and the stimulated emission will give you a single photon. And then there is this whole like measurement setup that I showed you previously. Two detectors at equal distances divided by a beam splitter, and at zero time gap between these two detectors, you would see a dip. They have shown in terms of the counts, the coincident counts. As you can see, at tau is equal to 0, the number of coincidence counts is very small. But at larger tau, you can see that the coincidence are increasing. So this actually shows me that my source is a single photon source. Okay, so before I proceed, I would like to know how much time I have, then I can talk accordingly.
It's okay. I mean, you can talk for a couple of minutes more. Please go.
Okay, like a couple of minutes would be a very short amount for me. Okay, I'll try to like skim over as fast as I can.
Yeah.
So this is this paper right over here, like photon anti-bunching. This was shown by Kimball et al. It's a very good paper. You should look at it. In laboratory purpose, like the lab work that we do, we actually use this concept called spontaneous parametric down conversion from a nonlinear crystal to create single photon sources. Okay, this is the last part that I will talk about. The crystal that we use is called a potassium titanium phosphate. It's a Chi2 crystal or a nonlinear crystal. It's usually periodically poured. Let's skip all this part because these are not that much important. What's important is this second order these nonlinear crystals create something called a correlated pair or a time correlated pair. What happens? You have a nonlinear crystal. The feature of a nonlinear crystal is that whenever you pump it with a very high energy photon, it will break it into two low energy photons. As you can see, I'm sending a blue photon and it's breaking into two red photons. The important property of this thing is that, first of all, the energy is being conserved. That is omega s omega I will always be equal to the pump energy. And they are either of same polarization or they are of counter polarizations. But the major point of this generation is that whenever you send a pump in this crystal, this photon creates two sister photons exactly at the same time, which means that whenever these two photons are created, they are correlated in time. What does this mean? So this is the quantum state that it creates in, like whenever a pump photon comes in, it will create two photons at two separate polarization and with some spread in the wavelength. This is the experimental setup. This is like not very tough to understand. I'll show you. This is a nonlinear crystal right over here, which is being pumped by this blue light. This nonlinear crystal creates these two signal idler photons, which we are filtering this out. As you can see, the red light is coming over out. These two photons are coming in the same direction. As you can see, they are coming in different directions. There are crystals that create them in different directions, but the crystal that we're using here creates them in the same direction. These two photons are coming out, and these two photons have an important property is that their polarizations are orthogonal, which means the signal and idler photons created over here have orthogonal polarizations. So whenever we use a polarizing beam filter right over here, these two photons are separated. The horizontal goes to the straight path while the vertical goes to the reflected path. Now, as I said, since these photons are correlated in time, which means that whenever they are born together. There is no time delay between them. The only time delay that can come in between them is due to the birefringence in this crystal and the optical path. So if we try to find coincidence among these detectors, among these horizontal and vertical measured photons, we should see a coincidence among them. So what we are doing over here is whenever a photon is detected over here, we are asking when is the second photon detected. And as you can see, the second photon is always detected within, like, with a high probability in certain time window after a certain time. Like there's a mean and this variance, which means that the photons are correlated to each other. As you can from this histogram, you can see that there is a higher probability of the second photon to come within certain time window after the first photon has reached. In terms of the second order correlation that I described you in the last section about bunching, these two photons you can describe as bunched. As you can see, the value has gone way above 1. It's not even at 1, it has gone about to the value 80. So this is a very it's a highly bunched state that you're looking over here. But how do you create a single photon source out of it? So what we do is called a heralded single photon source. Since these photons are correlated in time, as you can see, these are in 1-1 state. So whenever you isolate one of the photons out, the other photon has to be very close by it, right? And this other photon that you have separated out is in a single photon state. So what you're doing right over here is that you keep one of the photons, suppose this photon, you keep it as reference, and the other on the other photon, you're doing a G2 measurement. And if you see a bunching, if you see an anti-bunching dip in this particular line, you would be sure that whenever I'm seeing this photon, the other photon is in a single photon state. This is exactly what we are going to do. Suppose this DH over here is the reference photon, and this D1 and D2 are being tagged with respect to this photon that is detected over here. Like whenever DH is tagged, D1 and D2 also clicks, since they are correlated in time, right? So as you can see, there are two peaks that are coming over here, since the photons that come either at D1 or D2 are related to DH in time. But if I concentrate only on this part, if the source coming from here is a single photon, then it will at 0 delay, they will either go at D1 or at D2, but never can go to both. That is, you are doing a conditional measurement. Given that I have measured a photon over here, what is the probability that these two detectors over here are clicking simultaneously? From this graph, as you can see, at 0 delay is showing a clear dip with a value less than 1. So this is showing that this photon, that is a source that I have obtained over here, is anti-bunched, or it is a single photon source. It's rather an engineered single photon source or a conditioned single photon source, not a true single photon source. So this is how you create a single photon source, or you engineer a single photon source, and we routinely use this source in any work that we do in our lab on quantum cryptography and whatever. So this is a paper that exactly describes this particular experiment that we had executed. These experiments are done actually to like calibrate our sources before we take them to doing quantum cryptography and all. Okay, E91 protocol I'll skip because the entanglement protocol will take some time. This was our initial trials where we did our experiment with weak coherent pulse, but we did a very simple experiment of sending just a single polarization and measuring the polarization fidelity. Like if you're sending a single photon from Alice and receiving it on Bob, is your Bob setup, like does it have the good enough fidelity to tag the photons properly? So as you can see, when we are sending the correct polarization, suppose I'm sending the 0-bit polarization over here, it is responding to only the 0-bit and the other one is float, which means Bob is only tagging the right polarization. Similarly, when the other one is sent, the other channel peaks while the other ground is float. So these were our initial trials. So finally, my conclusions on, like, there are many more protocols and methodologies that exist, like there are BBM92 and there are protocols that utilizes multi-photon entangled state to do protocols. It's an emerging field which has promising scopes, and but it requires a lot of technological developments. And in lab, there is a major boundary that we have to cross every time, like time tagging, doing efficient measurements of photons so that we don't lose and stuff. But it also allows you to look at the quantum world in a different perspective, with a practical perspective that usually you cannot come out from books. Like, there are many things which are like indirectly visible, but these experiments actually lets you do hands-on experience of how quantum theories work. Well, my acknowledgement for Professor Sushil Majumdar, my PI. He is the project instructor of these quantum cryptographic things in our lab at NOMAL, Nano Optics and Microscopy Optics. And these are my two lab mates, Vikas and Kiran, with whom I have traversed this new area of research. And thank you.
Thanks a lot, Mr. Chatterjee. I mean, for your speech. I mean, for your very detailed speech. Yeah. I hope many people working in this field will get benefited. Thank you. Thank you for. Yeah. We are very fortunate. We are very pleased to have hosted you.
Yeah, of course, of course. Like, I was also happy to share with you guys. So, if you have any questions, you can ask.
Excuse me.
Yes.
I have two questions. In the case of BB84 protocol, when Alice send standard polarization and Bob choose compatible standard basis, then he will get result. But how can Bob know that whether he is choosing right basis or not?
Yes, that is the case. Okay, that is when you need this thing. See, that is why in the whole protocol system you have two channels, the quantum channels and classical channels. It is true, Bob will never know. Bob has no a priori information of what polarization Alice is going to send, but he doesn't need to know. What he knows is that whenever he chooses a correct basis, he is choosing randomly. Suppose Alice is sending randomly, but Bob is also choosing randomly. He doesn't need to make an educated guess. He needs to make a random guess. What he knows is that after the photons have been transmitted from Alice side to Bob's side, that is when, like in this picture, if you see, that is when the classical channel comes into play. That is when Alice and Bob will discuss amongst themselves what basis of measurement they have chosen, what not photon they have measured. Like, what does a basis mean? As you can see in this picture, the basis is a cross and a plus, which means that if a photon comes in, and depending on what polarization it is, it will hit that detector. Suppose, like, see in this particular column, the second column, Alice is sending a 0-degree polarization, right? And Bob is choosing a plus basis, so the 0 will hit the 0 detector on Bob's side. So after this sequence has been passed, Alice will say to Bob that, look, I have sent you a photon in plus basis. She won't say that I have sent you a photon in the 0-degree. She would say, I have sent you a photon in the plus basis. Similarly, Bob would say, I have received a photon in plus basis. He won't say that what photon. Have I received 0-degree or 90-degree? He won't say that. You must understand that your information is being encoded in the polarization, not in the basis. So whenever you are discussing basis amongst yourself, like if you are Alice and I am Bob, and I am discussing basis amongst ourselves, then I am not revealing any information about the key. I am only revealing information of my choice of measurement. The thing that is happening over here is that I know whenever my choice of sending and your choice of measuring is same, That can happen randomly, and there is a upper, like if you do the calculation, there is like an upper threshold to it. Like in B92 protocol, whatever Alice sends, Bob can only tag 25% of that, not more. That is the ideal situation. In practical situation, you will be tagging less due to losses. But the important point is that it doesn't matter what Alice is sending. It doesn't matter in which basis Bob is measuring. They has to be random. But whenever their bases match, which they talk about it after they have sent the sequence of photons, whenever their bases match, they know that they are seeing the right, the correct polarization. Like Alice doesn't need to say, I have sent you a 0 degree polarization. If she says that I have sent you a polarization that is in plus basis, and if Bob finds out that I have received a photon that is in plus basis, he can be sure that what I have received is the same thing that Alice has said. Think about it now. Is that clear to you?
Yes, sir. But in each basis, probability will be different, na?
In each basis, probability will be different, but that's okay now. Then you have a particular threshold. Not all the photons that is sent by Alice will be tagged by Bob. Bob can only tag a particular percentage of it. Like in B92 protocol, you can tag only 25% of the total photons sent by Alice. But that doesn't matter. What matters truly is that the photons that I have tagged, okay, I know for sure that whatever Alice is sending, I am receiving only that. So the percentage of photons that I have tagged correctly based on the right choice of polarization, that becomes my new key. So yeah, it's an overwork. You're sending a lot of information, but only a small amount of it is usable. But you know for sure whatever I'm looking is the same on both sides.
Yeah. Thank you.
Yeah, of course. Okay, so any more questions?
Well, I guess we have one question in the Teams chat. So it goes on something like, nice talk. My mic is not in working good. I mean, okay. Can you comment on entanglement based protocols, and what do we expect more? Any work has been done on single photon entangled states where entanglement is between different degrees of freedom of the same photon for cryptography?
Yes, like that is the part I had to unfortunately skip for lack of time, but I was going to talk about this protocol called the E91 protocol. In this protocol, what happens is that you create a pair of photons that are entangled in polarization. It's better I refer you to this paper, Quantum Cryptography Based on Bell's Theorem. If you read this paper or any article based on this paper, you would know more about this.
If you can upload this paper, I mean your presentation, and with the references in
sure.
Teams chat, so it will be good for us.
Okay, how about I mail this presentation to you after the talk, then you can distribute among themselves. That's okay.
Yeah, absolutely. I guess that will be fine as well.
Yeah. So coming back to his question, this was the first, it's E91 because it was developed in 1991. So the entanglement based protocol is very old. It's not a very recent development. And if you talk about recent development, then there are protocols in which people have used higher dimensional entanglement. In polarization, you have two bases. You have only two states, right? Either 0 or 90 or rotated versions of that. So you are in a 2-dimension space. So the entanglement space you get is 4-dimension, right? But in photons itself, you can use other degrees of freedom like optical angular momentum or time delay between them that you can use to create higher dimensional entangled states from which you can use to do quantum protocols. Okay, let me tell you in a very simple manner how an entanglement protocol works. In the two protocols that I have described over, B92 and BB84, they are based on statistics. Like if an hacker comes in between your system and tries to hack, then your statistics change, and from that you're being hacked. But in a entanglement based protocol, it is more intuitive. What you do is that your entangled source will send photons to A and B, right? And for using few bases first, the A and B will first make sure that their photons are entangled or not. Once they make sure that their photons are entangled, doing some measurements that I won't talk about here right now, they can use a next set of measurement to create a common key among them. Okay, if you read about this protocol, you would find it's very interesting. They use three 3 different measurements on both sides to establish that both their sources entangled, as well as generate a key out of them. The fun fact is that if a hacker tries to hack, he has to come here or here, like he has to intercept these photons somewhere, right? If he intercepts this photon, he will inevitably break entanglement, and if he breaks entanglement, Alice and Bob would know. And once Alice and Bob gets to know that entanglement is broken, they would know they are being hacked. And another fact is that even if the eavesdropper is trying to hack them, the key would be useless. First of all, he would be exposed. Second of all, the key only makes sense after the entanglement measurements have been done. So if this particular protocol, E91 protocol, has been shown by the Chinese very recently in the year 2020 from their satellite. They sent this entanglement photon source over a distance of like 11,050 kilometers at 2 stations A and B, and they showed that the entanglement is preserved, as well as you can make a secret key out of it. So you can understand, right? Like the entanglement-based protocols are actually more used in the forefront of modern technology than the ones that I have shown over here. Like in year 2007, there was a project, like almost like 15 years back, but it was advanced for that time frame. They also used, like in this paper, this Canary Island experiment right over here, Varsin et al. In the year 2006, not even 7. They also use the same principle. They use entangled photon source, keep on one side, send to the other, and using this entangled protocol, they are doing the quantum key distribution. Even more recent work is being done in the Harriet-Watt by a group called Mehul Malik. They have shown entanglement-based protocol in higher dimensions of entanglement, 3-dimension, 4-dimension, using optical angular momentum and all. You can look at them if you also want. I hope that answers the question. I have more questions.
Dinesh says thanks. Okay. So yeah, thanks a lot for your very detailed and very dedicated thing. Like you actually told a lot of things, gave us a lot of information. Thanks for that.
Yes, of course. And thank you for inviting me. It was a very nice experience.
It was our pleasure. It was our pleasure. Thank you so much.
Thank you.
Okay.
Then I'll stop sharing now.
Sure. So basically, our last speaker, Mr. Ankit Dhaka had a problem, like, and I'm sorry, Mr. Rahul Shastri. I'll just call you a little later, okay? The thing is, our last speaker, Mr. Ankit Dhaka, he had a small problem, a technical issue. So he wants to, you would like to come back again, right? Hello, are you there?
Hello,
yeah, please.
So I'll share my screen. It seems I was talking to the screen only for the whole talk.
Okay.
Yeah. Can somebody tell me where was I when this issue happened?
You were there. Some slide. Yeah, this slide. Experimental studies, basic plasma experiments.
Okay.
No, the next one. The next one. No, the next one.
This one?
Next one. Yeah. No, next means not previous. The next. This one. Toroidal assemble. Yeah.
Okay. So I told you. So if I join the ends of the magnetic mirror, I hope everybody is on the same page. So we make a system called a toroidal assembly, and what happens is that the energetic electrons that were losing from these ends will stay confined because the ends are joined together. So we reach to a configuration called a toroidal assembly, and here we see that the magnetic field that we are creating is being created by these square coils that you see. And if I draw it on the right hand side figure, it will be like this. So if I make a current flow in this coil like this, the magnetic field will be along the toroidal direction, and due to this magnetic field, the electrons will be bound towards the magnetic field lines, and they'll be confined. And this is a small machine that it's been there for 40 years, I think. Sorry, 30 years, and the plasma is being produced by thermionic emission. And recently they have installed a ECR source. ECR stands for electron resonance, and it's basically we launch an electromagnetic wave with a frequency such that frequency that is equal to the cyclotron frequency of electron, and the wave actually dumps the energy inside the plasma, and the plasma will get heated up. So this machine includes the studies including transport and function fluctuations of densities and instabilities in a toroidal geometry. And basically the idea is to reach in a device called a tokamak. So tokamak basically is a toroidal plasma device, and it was invented by Russians in 1950s with an idea of achieving magnetic confinement. So in the previous slide, probably you remember me talking about increasing the density, increasing the temperature, and increasing the confinement time. So why we are doing is that there exists an criteria for fusion to happen, and basically it's called the fusion triple product. So according to a theory given by Lawson, if the product of these three parameters exceeds a certain value, we achieve a nuclear fusion. That is the whole goal of this program. And we have a tokamak that is being operated in IPR. It's named as Aditya, and we started Aditya U. U stands for an upgrade. So basically, what we are doing is that we are flowing current in these coils in this direction that produces a toroidal field, and due to the magnetic field, the plasma will be confined in this geometry. And the question arises that how do we heat this plasma? So for heating the plasma, we'll have to drive a current inside the plasma, but since it's a toroidal continuous geometry, we cannot have an electrode inside. So the idea is to have an ohmically driven current. So how the current is driven is that there is basically a solenoid in the center, and we drive a current such that there is a constant di by dt, that is the current is changing linearly with time, and due to that there is an electric field induced in the toroidal direction, and due to that electric field there will be a finite plasma current, and due to the plasma current there will be, since plasma has a resistivity, the plasma will get heated up. And in the top here you see a schematic diagram of Aditya U tokamak, and it's basically a vacuum vessel in the toroidal shape, and you see all the diagnostics that is being installed on this device, and basically each diagnostics offers one Ph.D. problem. And so we have infrared imaging, visible spectroscopy, then visible imaging, laser diagnostics, magnetic diagnostics, and we have spectroscopy, then Thomson scattering. So there are a number of diagnostic exist to measure the tokamak plasma. And why do we need this exotic diagnostic? Is that the tokamak plasma is very hot. So you see it's around 400 eV, and if I roughly transform this in Kelvin, it will be around 10 power 6 kelvins of temperature. And at such a high temperature, you cannot rely on passive diagnostics. So we cannot put any probes inside the plasma to measure this temperature. So we have to rely on a certain number of diagnostics. So here one thing we observe is that the coils of the vessel that are not visible in the figure, but in the schematic you see the blue lines. So these coils are made up of copper, and what happens is that if you drive a current in a copper, due to the finite resistivity, the copper will get heated up, and you cannot operate the machine at a long time. So because the conductors will start to melt. So this is overcome by upgrading the tokamak to a superconducting tokamak, where all the copper conductors are replaced by superconductors. So ideally, since the superconductors has a very low resistance, you can drive the current throughout the day, and it will not melt. And also you can use lower rated power supplies to achieve higher currents. So this is a machine named as a steady state tokamak 1, and it's fully superconducting machine, and basically all diagnostics that we see on Aditya tokamak was also there for the SST tokamak. And then we move to the fusion program. So I'm basically running through the slides. So if anyone has a question, they can stop me. And so then we have India is a partner in the international collaboration of ITER. That is basically a very huge tokamak. You can compare by seeing a human here. So it's a very big machine. So of this project of close to $26 billion, and which is shared by seven nations. The machine is built in France, and India is a equal partner in technology and research. So the IPR offers few students who work there for a year or so, and the machine is being built in a place called Cadars in France, and the contribution that are going to be supplied from India are the cryostat. So cryostat is basically the vessel in which the superconductors are being housed because they have to be in an inert environment, and then the involved neutron shielding. So that prevents the neutrons from coming out and stops the safety hazards. So prevents the hazards due to neutrons, and then we are supplying cryo distribution lines, then auxiliary heating system. So heating systems such as ion cyclotron resonance heating and electron cyclotron resonance heating. Then we are also supplying a diagnostic neutral beam module. So that is basically what we do is we launch a neutral beam inside the plasma. What will happen is that the neutrals will get ionized, and during the process there are a lot of radiation getting emitted, and those radiations are being used to diagnose the plasma. And if somebody is wondering how do we make a neutral beam, is that we accelerate the ions, and then we accelerate the electrons, and then we combine them together to make a beam, because you cannot accelerate the neutrals because they don't respond to electric or magnetic fields. So then few power supplies also being supplied by India in this case. And then I move to theoretical and computational studies. So all the theory people in IPR have a big computer known as high performance computing system. So we are using this to run simulations. And why it's needed is because the normal plasma densities that we deal with are 10 power 20, 10 power 19 particles per meter cube, and so the plasma has a very high degree of freedom system. So for simulations, we need large computers. So we have some in-house developed codes. So that is first one is the MPMD, multi-potential molecular dynamics codes. Then there's this code called IPR equilibrium. So IPR equilibrium is used to solve a system called Grad-Schaffernov equations that basically tells how the magnetic field will be in a tokamak for a given plasma current and given toroidal fields. And then we have a GMSD code that basically solves the generalized magnetohydrodynamics equation. And magnetohydrodynamics is basically a system having the Navier-Stokes description supplemented with the Maxwell's equations. And then we have an ACTIS, that is the neutron. It's a neutron activity code. So it is recently being accepted by ITER for their calculation. Then we have few PIC codes. We also work on a few international collaboration on codes such as EMC3 iron, DKS2. All these are the codes to study the tokamaks, and we use them to corroborate the experimental results that we see in the tokamaks and various other plasma experiments. Then a few commercial codes for engineering perspective are also being run on this project. And the theory group is extensively using this platform to study nonlinear structures in plasma, such as solitary waves and laser plasma interactions and all sort of waves and instabilities in the plasma. And quickly I go through what I do in IPR. Is basically I'm involved in a collaborative project between theory and experiment, and I'm studying the nature of spontaneous fluctuations of strongly coupled Yukawa fluids. In the first slide, I told you about the dusty plasma. So this is a more model we used to model, we used to study the dusty plasma. So basically, we say that the particles are interacting by a screened Coulomb potential, where screening is provided by the second term, and Q is the particle charge. And if I define a parameter gamma such that it's a ratio of kinetic energy, potential energy to kinetic energy. So it can be used to characterize the length of correlations in the system, and then I can define a kappa, which is basically the strength of screening, how soon the potential is going to die, and I can use, by varying the gamma as in kappa in the experiments, I can achieve different phases of the system. And in the study, what I did is how, by using a model called a generalized hadronic model, how the fluctuations can be characterized. So I used the particle balance and energy balance along with the generalized hadronic model. So if one is wondering what is GH model, is that it's basically a Navier-Stokes model supplemented with Maxwell's theory of viscosity, and it's basically a modified momentum equation with the extra time kernel in the starting. And if one transform these equations in the Fourier Laplace space, you get a hydrodynamic matrix, and by inverting this matrix and solving for roots in using the power series, we achieved how the fluctuations is going to decay analytically, and then the results are being verified by using molecular dynamics simulations. And I invite you to read this paper we recently published in this work. And with this, I quickly conclude my talk. And I want to say that we in IPR are open for any collaborations, any ideas in plasma physics. If you want to do experiments on tokamaks, any system that you might be of interested in, we are open to that. And also we have a PhD program and postdoc program that is currently running. And if you have any question, any query, my email is here. I'm happy to redirect you to the concerned group, or if it's related to my work, I'm happy to collaborate or discuss the ideas. And with this, I conclude my talk, and I apologize for the interruption in the last talk.
No, we completely understand. It happens to all of us, and we are sorry to have, to have kept you waiting for such a long time. I understand you are also very busy, and thank you for the invitation for the collaborations and all. So
I forgot to ask if anybody has a question. I'm happy to answer I'll try to answer with my knowledge.
Sir, I just wanted to ask one thing, that is, these are plasma particles. In this plasma, like you said that the electrons are, they are electrons. So like, what is the, average range of velocity that the electrons get?
So basically, you can here in the tokamak, for example, the temperature is of the range of 400 electron volt. So if I assume a Maxwellian distribution, so the width is around 400 electron volt, and from there one can easily find out the speeds. It's of a few thousands of kilometers per second, but again it has a distribution, so you can.
So it's mostly non-relativistic, right?
Yeah, it can be relativistic also. Okay. In the tokamak, in the core, the speeds are very high.
So at that areas, that means relativistic calculations come into take place, at least in the theoretical studies.
Yes. So we recently, one of my colleagues, she defended her thesis, and she was working on the wave breaking in plasmas in the relativistic regime. So if your wave has an electric field amplitude that cannot be sustained in the plasma, so what will happen is that the wave will break and it will dump its energy into the plasma. So she has done extensive work on the relativistic effects in the plasma.
Okay. Thank you so much.
Okay.
Thank you, sir. Okay. Thank you. We are very honored to have you here. For your thank you
Yeah,
for your
it was
talk.
a great experience for me also. Thank you very much for inviting me.
Yeah. Thank you so much.
Okay. Welcome.
Okay. So we'll move on to our next speaker. He is a student at IIT Gandhinagar. His name is Rahul Shastri and he works in the field of quantum thermodynamics and quantum optics. Today, he'll be delivering a talk on quantum heat engines. So, Mr. Shastri, you are welcome.
Okay, so should I share the screen now?
Yes, sure. And sorry to have kept you waiting again. We are running a little late. Yeah.
So can you see the screen? Can you see my screen now?
No, it's not visible yet.
Now is it visible? Because I have shared the screen. I think do you need to allow something or some?
No. It's not like that. I guess it's not only for me. Nobody is able to see the screen, right? I'm just asking the others present.
Cannot see the screen.
Cannot see now. It's again. I don't know. There are too many technical glitches happening today. You can just maybe try it again. I don't know.
Okay. Let me do that.
We request our viewers to kindly wait again. Today is not exactly a good day, I guess. Oh, yeah. Mr. Rahul Shastri, are you there? He's not there.
So I'm trying to share the screen, but I don't know what is the issue.
Like you did like leave the meeting and join again, right?
Yeah.
Do you have another device? Maybe some people have had a problem with the
Okay, let
device
me
as well.
Okay.
Or maybe change the network connection or whatever.
Okay, give me 2 minutes.
Okay, sure.
Yeah, there is a question that about PPT slides and recorded videos. Yeah, we'll deliver the PPT slides, all the PPT slides what we got from the speakers. And for the recorded videos, you always can watch it on YouTube. For the drive files, we will send you as soon as possible.
Okay.
Hello.
Hello.
Yes, you're audible.
Now can you see my screen?
It's black. I mean,
now?
there's a screen, but it can be seen now. It can be seen.
Okay.
Okay. Please go.
So is it okay to like turn off my video so that I?
Yeah, absolutely. Why not?
Okay. Now it's visible, right?
Yes, sir, it's visible.
Okay. Okay, so good evening, everyone, and it is a very nice initiative. It seems so. I thank the organizer to like allowing me to like present my work here. So I'm going to present about quantum heat engine. So before first, let me give you a brief introduction about my field of interest, which is quantum thermodynamics. And this is very emerging and new field with very fascinating and new open ideas and questions. And here is very nice short review about open questions in this field. Can you see my pointer or cursor or something?
Yes, it can be seen.
Okay. So this is the very nice review about the open questions in this field of quantum thermodynamics. Broadly speaking, this is the field is about understanding and study the interplay between quantum effects like quantum coherence, entanglement, quantum information, and non-equilibrium statistical physics ideas. So here is another very nice review on the experimental side of this field. Very recent, so you can look at this. Okay, so this is going to be the plan of the talk. So I'll start by introducing the idea of quantum heat engine and why studying this kind of systems are useful in order to understand the concepts of quantum thermodynamics. And then I'll talk about my recent work on asymmetric Otto cycle, and then I'll conclude. Okay, so what is quantum heat engines? So these are nothing but engines with quantum systems as working substance, and which uses flow of heat in order to perform useful work. And the first idea of quantum heat engine goes back to 1950s, and this is very nice paper in which the author showed that the three-level maser as a quantum heat engine, working as a quantum heat engine, and using the ideas of equilibrium statistical mechanics, they have derived bounds on the efficiency of such kinds of engine. And yeah, so basically we all know that quantum systems have discrete energy levels. This is one of the characteristics. And here is an example of a quantum thermodynamical process in which system is going from one equilibrium state to another state. And here in this schematic, you see that this red lines are the discrete energy levels of the system, which is described by the underlying Hamiltonian of the system, along with the population. Because now the system is maybe connected with the bath or / environment or reservoir. Now using that we can define useful variables like internal energy, heat exchange, work exchange in the following way. So the internal energy is nothing but the average energy of the system. And during the process, the average energy can change in two ways. Either the populations are due to the change in population, or due to the change in the spectrum, the energy spectrum that we can control. So the internal energy change due to change in the Hamiltonian or the energy spectrum, we attribute that as a work done or work exchange. And the energy change due to change in the populations, we attribute as heat exchange. So this is very nice way to think about the thermodynamical variables heat and work. Okay, so this is very nice familiar example of a quantum Otto cycle. It consists of two work strokes. One is a compression stroke and one is an expansion stroke, and two heat strokes. One in which system absorbs heat from the hot bath, and one in which system dumps heat to the cold bath. The only difference here is that now the classical system is replaced by the quantum system. Okay. So why study this quantum heat engines? Because these are like very nice framework to study the concepts of quantum thermodynamics. And also there are various experimental platforms available to perform or to study this kind of engine. And yeah. So these are few examples where clearly people have shown that quantum heat engines or this kind of devices can outperform their classical counterparts. Yeah. So there is an advantage of going to quantum regime in some sense. Okay, so now I'm going to present our recent work, which is on the optimization side of this quantum Otto engine. So what we have done is we have considered finite time quantum Otto heat engine with compression and expansion strokes with unequal duration. So hence it is called asymmetric Otto engine. And I will define all of these terms little later, but roughly what the question is that by using this asymmetry parameter, can we optimize such this engine in terms of work output and reliability? And it turns out that there is a trade-off between work output and reliability, and for some parameter regime it is possible to co-optimize work output and reliability. I'll define this term in a moment. Okay, so this is the basic setup. So as we have seen, it consists of 4 strokes, 2 work strokes, compression and expansion, and 2 heat strokes. The difference is that the time spent in compression and expansion strokes are different, and this asymmetry is characterized by this parameter Ru, which is between 0 and 1, and Ru equals to 0.5, which is the standard symmetric Otto engine. Okay, so now also in thermodynamics we always talk, we care about only the average quantities like average heat and average work, and we don't have to worry about fluctuations because of the large system size. But as you go down to a small system scale, the fluctuations become important, and then in addition to efficiency and power output, you have to also ask the question that is the engine reliable, in the sense that is the signal to noise ratio good enough. So one way to define a measure of this reliability is through the ratio of average work output to the standard deviation, which is very nicely introduced in this following article. Okay, so it turns out that it is possible to exactly construct work and heat probability distribution, not just the averages, by using this 2-point measurement scheme. And the expression of work and heat distribution is given by this following form in terms of the parameters of the engine and the temperatures of 2 baths. And by using this distribution, we can calculate various moments of work and heat in the following way. Okay, so the central question or aim of our work is to ask the following question. So can we optimize work output and reliability, these two quantities, as a function of this asymmetry parameter Ru? And we have considered these 2 specific examples of quantum systems. Okay, so this is the first set of results. So on the left hand side you see plot of optimum value R corresponding to the work output, which is denoted by R star, and optimum value of R corresponding to the reliability, denoted by R circle, as a function of total cycle time, which is the time of compression stroke plus the time spent in the expansion stroke. And immediately you can see that the functions are discontinuous, but another more interesting thing is that the optimum value corresponding to work do not coincide with the optimum value corresponding to reliability, which means that we cannot co-optimize except at some isolated point. So if the engine is running at this particular total time, then only we can co-optimize these two quantities. This is one of the central results, and on the right hand side we have plotted the actual optimum values of work output and reliability. Okay, so this is the same plot for different parameter values, and we see similar patterns, except that here these co-optimum points are different from the 0.5. Okay. Now similar, it turns out that it is also same for the two-level system, which points to the fact that these results are more general, system independent, and yeah. Now in all the previous cases we have restricted to the scenario in which we allow the system to thermalize perfectly with the hot bath and cold bath, but now we remove this constraint and allow for imperfect thermalization, and we see the same results in this case, both for two-level system and harmonic oscillator. We have also looked at power output in the finite time regime, the optimum power output and the power output corresponding to the standard symmetric Otto cycle, and it is very remarkable that we can see that the optimum value, the power output is for the asymmetric quantum Otto cycle is always greater than the symmetric Otto cycle case, both for these two examples of systems. We have also looked at efficiency and the efficiency fluctuations, which is introduced in this recent article, and this quantities also shows similar behavior. And yeah, this is for the oscillator case, and this is for the two-level system. So basically, we have this is the conclusion. What we have done is we have considered finite time Otto cycle, and we have introduced an extra parameter which characterizes the unequal time spent into work strokes, and we have optimized with respect to that parameter, and we have seen that there is a trade-off between these two quantities, work output and reliability. And we also extended this result for the finite thermalization case. Yeah, and we have also looked at power output. And one interesting follow-up of this work can be to see that what happens if we allow unequal time, the asymmetry in the thermalization stroke as well. Yeah, thanks. So if you have any questions, you can ask.
Thank you very much for your talk. I don't think there are any questions.
Okay.
Just
so
if there are questions, so I guess they can reach out to you via mail or something.
Yeah. Sure.
Okay. So thank you. It was a pleasure having you here. It was a great pleasure having you here. I hope we can interact furthermore in the future. So
yeah. Sure.
Thank you very much.
Thank you for allowing me to present the work.
Absolutely, it was our pleasure. Thank you so much. Okay. So we'll move on to our next speaker. I'll just ask the speaker first before introducing him whether he is available. I mean, Mr. Ratul Das, will you be able to speak right now?
Yeah.
Okay. So basically, here's Ratul Das for you. He's from NISA. He works in the field of astrophysics. And today's talk shall be on irregularity and memory in the hemispherical asymmetry of the sunspot cycle. Mr. Ratul Das, please take the stage.
Yeah. All right. I should share my screen, right? Yeah. Hello, everyone. Can you see my screen?
Yes, your screen is visible.
Yeah. Okay. So yeah, I just realized that I had actually entered a different title for my talk, and yeah, this is actually the title of the paper that we had published after finishing our work. So basically, I had worked on this during my summer vacation in 2020. I had begun my work on this with Dr. Vidya Vinayak Tarak. He's a professor at IIT BHU. And later on, we also started working with Aparup Ghosh, who is a fifth year from IISA Kolkata. After this semester, he's going to be finishing up his BSMS degree. And I think he's going to go towards high energy physics. But yeah, this is something that is not exactly astrophysics. I would call this more directed toward nonlinear dynamics. But yeah, it seemed like this is something that people in astrophysics would identify more with. So I went ahead with astrophysics. So yeah, without further ado, I'll begin now. Okay, what's happening? Right. So yeah, I'll go through a short overview of the talk. Essentially, I'll explain what is the hemispherical asymmetry of the solar activity, how does it arise, what data I had picked for the analysis I had done in this work. And then I'll go through each of the methods that we use for analysis. There's something called correlation dimension analysis. There is something called fractal analysis. And finally, there is first exponent analysis. So all of these are basically time series analysis methods that are commonly used in nonlinear dynamics. And yeah, after that, I'll conclude. So I'll begin by explaining exactly how we started talking about the asymmetry of this solar cycle. So essentially, when we observe sunspots, we see that they are not equally distributed about the equator of the sun. As in, you can get more sunspots in either the northern hemisphere or the southern hemisphere. And it's not something that remains consistent from solar cycle to cycle, as in the 11-year period that is commonly seen. Many people have studied this in the last 20 years. And before this, people had studied sunspot numbers, sunspot areas. But this is something that has gained more traction in terms of attention this side of the century. So yeah, this is not very well understood in terms of how it occurs, in terms of the underlying process that causes this. And we know for a fact that this is not something which is just a result of inaccurate or noisy observations. Yeah, so sunspots are essentially a proxy for solar activity. As in the magnetic field fluctuations that are seen on the surface of the sun, they become visible to us in the form of sunspots. Because you may know that whenever there is a strong magnetic field, you get sunspot formation in that area of the sun's photosphere. So yeah, here are some pictures of the sun taken by SDO. In the top row, you will see 4 frames in different parts of the solar cycle. And in the bottom row, you will see essentially the magnetograms for those exact frames. And yeah, the middle row is something that is generated by an AI program by looking at the visible spectrum images of the sun, the top row. So yeah, this is something which is understood pretty well. And essentially, I added this picture because I wanted to show you all this. But yeah, essentially, when we talk about the sunspot areas, we are interested in what the last frame has to offer. Those exact areas where we see a dip in the temperature, basically. So, okay, yes, another thing, the top image, I think, is inverted. So, yeah, I should have found more on that. But anyway, yeah, this is something I picked up from one of Professor Karak's papers. In this, he had studied the temporal variation from 1874 to 2016. This is the same data set that we had used for our work. And in this, you can see that the north and south sunspot areas, they don't vary in the same way. In some years, you will see that. Can you see the mouse, everyone?
Yeah.
Yeah. In some of the solar cycles, the south sunspot area dominates. In some, in like 4 consecutive cycles between 1900 and 1930ish, the north, 1944, yeah. The northern sunspot areas had dominated, and so on. So, yeah, this is something that has been studied, and now we wish to understand why this happens. So, in that regards, a lot of theoretical attempts have been made, right from the 1990s, I think. Paper I mentioned earlier with Ballester and Carbonell. Yeah, those 2 people are responsible for doing a lot of work in this field. And yeah, so the sun is essentially a hydromagnetic dynamo. Or rather, the sun contains a hydromagnetic dynamo in its convection zone, which is responsible for large-scale magnetic field and the solar cycle itself. So this is something that Parker had established in 1955. So, and in the current dynamo model, a toroidal component of the magnetic field. So a toroidal component means basically a magnetic field that travels along the equator of the sun. So essentially, during the sun's cycle, it switches between the poloidal and the toroidal configurations of the magnetic field. So the poloidal magnetic field is something that is stable. It looks like what you would see for a bar magnet. And the toroidal magnetic field is something like a torus. So it's highly unstable, and it usually occurs during the solar maximum, when the polarity of the sun's magnetic field makes a 180-degree flip, essentially. That's also something that happens for the Earth every 100,000 years or so. But for sun, it happens much quicker. It happens every 11 years. So yeah, I should have explained some of these terms better. But for example, meridional circulation. But anyway, the point is that due to the turbulent behavior of plasma in the sun, this sort of hemispherical asymmetry is inevitable. And this is what we see when we look at pictures of the sun, basically. I'll go back to this once again. Yeah, here, for example, if you divide the sun right in the middle in each of these pictures by a horizontal line, you will see that, yeah, the area of these sunspots is not the same across that line. Yeah, both the AI generated and the actual images taken by the magnetogram instrument of the STO telescope. So, yeah, the actual data, the actual time series that we used for our work were this and this, the asymmetry and the normalized asymmetry. So we worked on both of these because in some papers it was seen that these two time series actually have different periodograms, basically. So if you take the Fourier transform of the asymmetry in the frequency domain, then you essentially get different distributions. So because of that, it makes sense to, form the same analysis for both AS and the normalized asymmetry. So yeah, okay, I should mention what AN and AS is. AN is the area of sunspots above the equator, and AS is the area of sunspot below the equator. And yeah, AS is simply the difference between these two. And yeah, this is not the modulus of the difference. This is this has a sign, so it can be negative if the area of sunspot is greater in the southern hemisphere. And AS norm is simply the same thing divided by the total sunspot area at any given time. So yeah, this is how we get these two time series. So yeah, I'll talk about the first method that we use to look for basically any deterministic behavior in the system. So essentially in nonlinear dynamics, you're interested in behavior that looks random. I'm using this word in a euphemistic way. It looks random, but it's not actually random. It's something which can be predicted. Stochastic systems cannot be predicted. They're random, actually random in the mathematical sense. But chaotic systems can actually be predicted despite their name. So essentially, we use something called a box counting method. In this case, we use the correlation dimension to see if the trajectory that is taken by a process, essentially we look at how a variable changes and essentially look at the number of points that are within a distance r from a given point. And using the Heaviside function, this theta, we obtain basically this quantity, CMR. For small r, we can actually estimate this T2 quantity by taking the asymptotic logarithm of CMR. But in our case, we actually do this numerically. So yeah, we wrote some code for that. And using that, we managed to produce the following plot. For a chaotic attractor, the D2 should actually saturate after a certain M. For something like M equals to 4 or 5, you will see this curve sort of flattening out. But in this case, it sort of keeps increasing. It sticks close to the slope line for the tan 45-degree slope line, basically. The slope is 1 here for this dotted line. So that is a characteristic of a stochastic system. There is a degree of basically stochasticity that can be mistaken for a deterministic system if we take m only up to 8. But if you go higher, it's seen that for larger radiuses, basically the radius that I'm talking about here, it actually increases again. So yeah, you actually have to decide by yourself until what m you want to examine to find that sudden jump. And if a jump like that happens, your process is definitely not a stochastic process. So yeah, this is one method we used. The other method was basically finding the fractal dimension for our time series. So we take our time series, out of which we produce subseries for each given time size, or rather step size tau. And we calculate for that step size basically a length scale, which is given as this summation. So if you plot the log of that length against the log of tau itself, basically the log of that length at a step size against the log of the step size itself, you get basically a line with the slope of 1.91 roughly. If you do the same method for basically an actual chaotic attractor solution, you will get something that is closer to 1.5 or 1.6. In this case, it's closer to 2, because this is a process that that is more ergodic in nature. If you remember the ergodic principle, it will make more sense. So yeah, as per this as well, this is more or less a process that is stochastic in nature. Now we come to the Hurst exponent method. This can be obtained using multiple different sorts of methods. We only focused on the RS method, and in the appendix for our work, we also discussed DFA and GPH, detrended fluctuation analysis, and Gewecki-Porter-Hudak method. So the RS method, it's kind of a handful to explain, but essentially, again, we take a step size and we make several subseries, and we calculate the standard deviations of these subsets, and we also calculate the ranges of these sets of cumulative deviations. And this allows us to find a rescaled range measure for each pair of T0 and tau. But T0 is the first basically time index for a discrete signal, and tau is the step size. For a yeah, we find the rescale range for that T0 and tau. And for each temporal window, by moving from T0 to n minus tau plus 1, which is the number of windows that is possible for a given size tau, we find the rescale range for tau as the average of those values. So the rescale range becomes a function of just tau if you find that average. So it is seen that this rescale range for each tau is proportional to tau to the power h, where h is the first exponent that we are looking for, and k is some proportionality constant. Yeah, right here. So this plot we obtain, we actually get two different regimes for different step sizes. So in this case, we actually use the natural log. So if you have a calculator at hand, you can actually see that e to the power roughly 2.2 is actually equal to 11. So that's roughly where we have this sort of change in the slope of this plot for both the asymmetry and the normalized asymmetry. So this is actually significant, as this suggests that there is a stronger persistence for these two regimes before that 11-year mark and after that 11-year mark for the asymmetry of the sunspot cycle. So it can simply mean that, yeah, there is a lot more noise if you look at the data series less at time periods, at step sizes less than 11 years. And for greater than 11 years, it's simply more persistent. But it could also mean that there is a fundamental change in the dynamics of the system when we observe it for different, for larger than 11-year timescales. Some people have said that there are various periodicities to the solar cycle. Some people, some are as large as a few thousands of years, and some are something smaller, like 70, 80 years. But it's difficult to say because we only have good data for the solar cycle for only about 200 to 300 years, which is still one of the longest time series that has been recorded in the history of humanity when it comes to natural processes. But yeah, that is something that has been theorized. So yeah, this is so basically the DFA method is sort of similar to the RS method. It's kind of trivial to discuss how it's different, but
excuse me,
yeah.
So yeah, I hope you know that we are running short of time. So like, if you could complete this within 5 to 7 minutes, it'll be good for us.
Oh yeah. It'll be finished in 2 minutes. Yeah.
Okay, sure.
Yeah. So essentially, the GPH method is based on taking the Fourier transform of the signal. In the DFA and RS methods, you don't actually take the Fourier transform. It's something that you purely work on in the real space. And yeah, it's something you can actually look up by yourself. But that's the general idea. So yeah, I'm going to summarize now basically. Yeah, from the D2 method, we found that it does not actually saturate for higher values of M. This means that there is no underlying presence of a low-dimensional chaotic attractor that could govern the asymmetry of the sunspot area data. And that agrees with the conclusion that Carbonell et al. Found in 1993 in their paper. That is, this is an irregular process. Through the fractal analysis that we did, we found that fractal dimension is closer to 2, which implies that a stochastic process, or possibly a high-dimensional chaotic process, is the cause of the asymmetry. High dimensional chaotic process is basically anything that is essentially indistinguishable from a random process. It's kind of a joke in the nonlinear dynamics community, but yeah. In all three methods that we did for the Hurst exponent calculation, we found that the Hurst exponent indicates that the Hurst exponent is above 0.7, which is basically an indication that if it's above 0.5, then it's a persistent time series. That is, if the variable in question is going in one direction, it will keep going in one direction. If it's less than 0.5, then it will do the opposite. It will prefer to go in the opposite direction. So yeah, our values were above 0.7. So that indicates a rather high degree of persistence. So, and for periods greater than 11 years, sorry, it says 22 here, this is wrong. We get a higher degree of persistence. So our ultimate conclusion here is that the monthly asymmetry of sunspot area is actually the result of a stochastic process. But it turns out that this stochastic process has a long-term memory. That is, it shows a strong periodicity even for large timescales that we found from an analysis. So yeah, thank you. If you have any questions, please feel free to ask. I'm sorry for going over time. Yeah.
No, it's actually okay. I mean, we have kind of got back on our lost time. It was okay. Okay, let's see if we have questions. Do you have any questions here from the audience? I don't think there's any. There's just 20 minutes. Okay, I don't think there's any questions in the YouTube section as well. People can, I guess, get back to you if they have questions. So
yeah, of course.
Yeah.
And if you want me to share the slides, I can share them as well.
Yeah, you share them. Either you email Shanshan or anybody like that, or you might just put this in this chat section as well. It's your choice.
Okay.
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 Yeah, if anyone asks for them, yeah, of course.
Please go on. What were you saying?
Yeah, if anyone needs them, please feel free to mail. I think that's probably the easiest way to go about it.
Sure. I guess people have heard this. So thank you for that. Thank you for the thing. Really good work going on. I wish you all the best in the future. And I'm looking forward to more such interactions as well. So
yeah, thank you.
Thank you so much. We are pleased to have you here. So okay. So with this, we can get to our next speaker. I hope he's there. I'll just ask for once, Mr. Tanmay Pati. I mean, are you ready to give a speech? I mean, give your talk.
Yeah.
Tanmay Pati, right? You're ready. Okay. Okay. So the next speaker we have on our list is Mr. Tanmay Pati. He is from NISA. He's working right now in the field of quantum cosmology, and he'll be delivering a talk on FG correspondence. Tanmay, it's your stage.
Yeah, thank you. Is the slide visible?
Yeah, we can see your slides.
Okay, thank you. Sorry for a background noise. Yeah, I will just start the talk right now. And my talk, the content of my talk is the fluid gravity duality. Okay, so in this talk, the plan is first I will give some overview in the sense like how the duality works, and basically the fluid gravity duality was formulated in the context of gauge gravity duality, which is sort of the area safety correspondence, which some lectures I believe some lectures have been done here, so you are a little bit familiar with this. And after that, I will tell why the fluid gravity and why it is important, the formulation, and what we can learn from there. Obviously, everything. I mean, when there is some dual system, you will see later in this talk. When there will be some dual system, some notorious calculations can be extremely simplified. And after that, I will go to the formulation of the problem, how I will formulate the entire thing. And here I need two components. One is the fluid dynamics and another is the gravity, which is basically the Einstein's theory. And I will go a little bit beyond the Einstein's theory because because the Einstein's theory is simply the static solution of the any problem. For example, the Schwarzschild black hole, if you see there is some static solution, and which we call it as the event horizon. But and whatever the metric we get, that is the static. And here that metric we will go beyond that, and that will be more generalized thing. And this will allow us to go to the derivative expansion of the Einstein's theory, and we will not go back to the derivative expansion of the main Einstein's action, Einstein-Hilbert action. But this talk would be essentially a simple short portion of the entire fluid gravity duality, which has been worked since the I believe the past 15 years. And here the two components are relativistic fluid dynamics and the gravity. After that, we will go to the conclusion and the future in future what we can see from this theory. So let's start with the overview. What is a duality? Duality is a if you see a system from the two different point of view. Okay, that means if the system can be different from two different point of view. Essentially, I mean, apparently may be different, but they are the same. So to make sure the systems are same, from every point, I mean, in every frame of reference, for example, if you see as a frame, from every frame you can get some different independent informations, and some informations can essentially be the same. Okay, and some informations you can get extra from one frame to another frame, and these extra informations can be derived from the other frame as well, but it may be extremely complicated. But in that case, duality comes into picture. So if you know one system is dual to another system, and if the second system is easy to deal with, so why we cannot start with the second system? Okay, so and we can get some complete some good information which can be useful to study the first system. For example, here we will see that transport coefficients of fluid dynamics would be used to construct the to construct the metric solution of the Einstein's theory in more general way. Okay, so and the essential idea is the horizon of a black hole. Here, horizon is important. Horizon, we will discuss what horizon we want to say. Now, just assume the horizon of a black hole behaves like a viscous fluid if you give a slight perturbation from the outside. Okay, so here what is the horizon? That means there is some ambiguity and some problematic. So that's why the membrane paradigm comes into picture. So horizon means here it's not the event horizon. The reason is if you take the event horizon, it's just a null surface. Okay, so the problem is we may have some causality issue, and if you take the horizon, which essentially the fluid would be there, if it is inside the black hole, there's another problem is it would be a space-like, because inside the black hole the horizon is space-like. So there is also the problem in manifestation of the causality. And so the most popular idea is the horizon is a stretched horizon. Okay, so whatever the horizon we will discuss in this talk is based on the stretched horizon, which is outside of the black hole event horizon. Okay, so that we call an exterior membrane. now let's now the fluid gravity duality, when it was worked out, it was based on the gauge gravity correspondence, which is the ADS safety correspondence. Okay, so what is the fundamental idea is in ADS safety correspondence is you have a d plus one dimensional gravity system with the gravity, or the gravity system can be one-to-one mapped with some d-dimensional fluid system. Okay, not necessarily fluid system, a d-dimensional gauge system in that case. It's a non-abelian gauge theory. And what happens, I showed here, it's a gravitational theory which we call bulk of the system. Okay, and it's essentially the string theory, which will be which will be reduced to d plus one dimensional supergravity, and the outside the membrane conformal field theory lives. It's a non-abelian gauge theory, and the gravity theory determines the conformal field theory, and similarly conformal field theory, from the conformal field theory you can get the extra information of the gravitational theory. So they are one is the correspondence of another. So that is the important, because this correspondent will allow us to find out the dynamics of the stretched horizon. If we give some slight perturbation from the outside, and what is the dynamics of the event horizon, we can find out from the boundary, if we use the boundary, the conformal field theory also, or if we incorporate the fluid dynamics there. But fluid dynamics is, I believe, it's simpler in that sense, but obviously you will get less information than the non-abelian gauge theory. So just 1 second. Yes, this is the holography, because in gravity system you have one extra dimension which can be described by one less dimensional system. Here it's the gauge theory, and this is the due to this different dimension, you can see, for example, if you see the Bekenstein-Hawking entropy formula, it's proportional to A, the area of the black hole. But in any system, if you see it's dependent on the volume. So in that sense, the gravity in any gravity system can be described by one less dimensional other system. That's simply the idea of the holography. So here we will use the d-dimensional Einstein equation, d plus one dimensional Einstein equation, which is one greater dimension, which determines the gravity and the essential, the geometry associated with it with a d-dimensional fluid. Okay, now the idea is why fluid gravity. First of all, one system can be the studying of one system can be easier than another. So using this gravity, fluid gravity duality, we can use the fluid dynamics, which is in some sense it's easier to determine some sort of dynamics, or you can say, we'll see what information we can get. But fluid dynamics is easier than to deal with than the black hole dynamics. Okay, and even if you here in this talk, mainly I will discuss about the Schwarzschild black hole, which is in particular planar ADS Schwarzschild ADS5 black hole. But you can use even the Kerr black hole or Dresden-Ostrom black hole if you incorporate the charge. In that sense, in that case, you have to use charged fluid. Okay, and this is this is also not very difficult to deal with than the black hole dynamics. And another thing is the converse is also true. If you have for a different type of fluid, for example, you have QGP. Okay, so in that case, that determination of the transport coefficients may not be easier, may not be easy to calculate from your first principles. So in that case, you can use the dual gravity system, which means the gravity determines the fluid. So these information you can get from the dual gravity system, and that is another important consequence. The converse also you can use, and another important result is the viscosity and entropy density ratio. This result tells for any system, if you have a system, there should be a boundary. For example, if your system is viscous, obviously, if it is not viscous, that's not a problem. If it is a viscous system, that means your entropy and there will be an inequality sign greater than equal to entropy, viscosity and entropy density ratio should be greater than 1/4 pi in natural unit. So in fluid gravity duality, we can derive this result, and we will in fact derive here, which will match also with the more rigorous treatments on this subject. Now how will formulate this problem? We will proceed in the analogous way, how the gauge gravity duality was formulated. Okay. Now in gauge gravity duality, what happened? We have two part of the same system. Okay. One is the gravity which determines the bulk and the geometry associated with the bulk, and another is the boundary, and the boundary we use as the gauge theory. Gauge theory, we just place the gauge theory as the boundary. Now depending on the bulk geometry, we use whether the gauge theory is in the ground state or the excited state. For example, if you have the maximal symmetric ADS geometry, for example, that means there is no outside perturbation or the outside influence from some outside object. In that sense, we say the gauge theory is in ground state. Ground state means if you take the expectation value of the energy momentum tensor, okay, so it would you can renormalize it to go to 0. Okay, so that's the that corresponds to the maximal symmetric ADS geometry. Now, and here one thing we are considering here, the ADS spacetime, which is a negative curvature spacetime geometry. Okay, so if you perturb or deviate from the maximally symmetric ADS geometry, that corresponds to the excited state of the gauge theory. Okay, so that means then in that case, expectation value of the T mu will be non-zero, and it depends. The value depends how you perturb it. If your perturbation is too much, in that sense your it would be and the expectation value greater would be very large. Larger than another. That means if your perturbation is large and your expectation value of T mu will also be larger. In that that is, we call it higher and higher excited state, and we associate some states also. We will not discuss in here because that is the different part. And here what will happen? Here the same way we will associate gravity as the bulk, and here we will associate fluid at the boundary. Fluid, when for example when here the maximal symmetric ADS geometry, in that sense for this case we will associate the ideal fluid at the boundary. Okay, ideal fluid means we will talk to that. And here if outside, if you perturb some fluid and it deviates from its maximal symmetric behavior, that corresponds to the the higher order gravity, the higher order derivative of the fluid. So that means if it is if it is a dissipative or non-dissipative, the higher order derivatives will remain in the fluid solution. Now, first I will discuss the fluid dynamics, and in this talk we will only discuss up to the first order of the fluid dynamics. And here the fluid will live in 3+1 dimension, and the gravity, gravity object is 4+1 dimension. That's why we call it ADS5. And yeah, if you see some papers and references, what I also gave there, they considered D dimension. So more general way, but the calculations are quite difficult. Okay. Now, fluid dynamics is obviously an effective description of a thermodynamic large system, and we consider its we consider the domain where the system is described by an effective theory. So the time scale is much less than the macroscopic time scale, where if you deviate the system from or drive the system outside the equilibrium, the time requires to come to the equilibrium again. That I am calling it's a macroscopic time scale, and it should be less than macroscopic time scale. Without this, if you perturb a little bit, if you're dissipative fluid, that means the modes what you will get is a quasi-normal modes, where there will be some imaginary parts, and the modes will decay with time. So my time scale will be much smaller than this, and the length scale is also effective domain. The length scale is important in the sense if you go to the molecular regime, there you will not get this thermodynamic property or the what's called the statistical behavior of T and mainly the temperature, because our parameters are two. One is the temperature, another is the velocity field. Okay, velocity field is sort of think of a vector field now in that sense. Okay, now we have two symmetry. Sorry, in our talk I will consider only one symmetry, which is the global space-time translation symmetry, which will correspond to the energy momentum tensor, is a conserved current, and the corresponding equation of motion is del mu t mu nu equal to 0. And if we have a charged fluid, in that sense we can associate another j mu for charge vector, which is your rho and the charge flux. There also we would get some equation of motion del mu j mu equal to 0. So our parameters are two. One is the temperature and another is the velocity field. Now, first consider the zeroth order T mu nu of an uncharged fluid. We have to consider, since it's a zeroth order, we are in equilibrium. So since we are in equilibrium, there will be no fluctuation. There will be no deviation of the temperature and the velocity field in every space-time point. That means there will be no derivative with respect to temperature and velocity. So we have to construct a T mu nu out of, we have two parameters, u and t, because t is not explicitly doing. So we have two parameters because t is constant in that sense, because it's a zeroth order and everything is in thermodynamical equilibrium and the system is thermodynamically large. So we would get e plus p u mu u nu plus p multiplied by eta mu nu. It can be done using, for example, if you say a plus b and so on, and the right side will be energy density if you take mu equal to nu equal to 0, and momenta, it will be momenta when these all are spatial indices. So, and yeah, obviously this constant equation is always satisfied because we are also considering the global spacetime translation symmetry. Now at the first order, so what would be if the fluid, and this in particular a viscous fluid, is deviated from the equilibrium? So what will happen if our time scale is not much greater, which is comparable with the macroscopic time scale? We would get the deviation was the del mu u mu and del mu t, which are non-zero, and this will allow us to construct the T mu nu, which is just a 2-0 tensor, out of, we have three parameters now: a velocity field, temperature field, and your force gradient. Now the generic form would be your just a constant c u mu nu d p mu nu. P mu nu is a projector operator. I will come to that. And et v mu u nu plus u mu p mu nu plus f into tau mu nu. This construction is just like any matrix can be written in terms of just antisymmetric matrix and a symmetric matrix without trace and a trace part. So our constraints are, one is the p mu nu tau mu equal to 0 and u mu tau mu equal to 0. So I will not go into the details of this fluid dynamics because this is it's sort of the prerequisite of this talk anyway. So it does not require, only the required part is the results, and we will quote it. So p mu nu is the projector operator which projects your velocity in the perpendicular space. For example, it's defined at eta mu nu plus u mu nu. If you take u nu, you will get 0. So if projector operator projects everything in the perpendicular space of the velocity, and that is the satisfying p mu nu equal to 0. Now this condition tells this last part is a traceless part. The last matrix component is a traceless component, and it's also perpendicular with the u mu.
Excuse me, Norman.
Yeah. Go ahead.
Yeah, I'm really sorry to interrupt you, but then can you please wrap this up within 5 to 7 minutes because we have other speakers as well.
Oh, okay, sorry.
Okay, it's not an issue. Like, just cover it up, okay?
So I'm trying. So the generic form you will get CTS. You should have a derivative in that sense, and here also a derivative is with the temperature. So the generic form would be this T1. Now and the conservatism equation is always valid, and from the conservatism equation we will see these and these coefficients are linearly dependent. Okay, so that means our these are C1, C2, these are called transport coefficients, and this we can be determined from the gravity. Now from this equation, if you see the momenta part, you will get the Navier-Stokes equation. That means we are in the right track. Now let's define the gravity as a bulk. So gravity is determined by the Einstein tensor, and the geometry is basically the Einstein tensor, and the and the boundary dynamics. And if you have Einstein tensor, if you have a geometry, you can set a boundary, and this boundary, which is the essentially the right side of the Einstein's equation, is just the T mu nu. Okay, and T mu nu, this T mu nu we can compare with the T mu nu of the fluid. That's the idea. Okay, so what it means, whatever the gravity, whatever if you have a gravity system, in the boundary, whatever its influence, you can compare the influence with the fluid dynamics. You'll get almost the same form. For example, if you have a T mu nu, this is the essential the description of T mu nu. It's called the Brown-York procedure, and this is the extrinsic curvature tensor. For example, in Ricci or Riemann curvature tensor, you use the tangent vector to parallel transport in the direction of the hypersurface of the manifold. But here we will use the normal vector, and the rate of change of the normal vector, it's just a simple commutator of two vector fields. So and it's the extrinsic curvature scalar, and it's the Einstein tensor. Okay, where the Ricci tensor and Ricci scalars are present. So the zeroth order Schwarzschild metric for radius 5 black hole can be determined in this paper. It's determined. So it's easy, and we get this. And from our previous procedure, and here we have used Eddington-Bickerstone coordinate, and his R is the scale parameter. Think about it as a scale parameter, not like radius. Obviously, it's a radius, but the problem is inside it's space-like, outside it's a time-like. So that's why I'm telling it's a scale parameter. Now, the T mu nu from our prescription will come to be this. Okay, from here, from the metric. Because we have a metric solution, and from there you can find out the geometry. From the geometry, you will induce some energy moment of tensor from the Brown-York procedure, and which we can compare with the fluid. We have this fluid T mu nu, and if we compare it, we will get the pressure is this, and entropy density is the derivative with the temperature. We'll come to this. Now let's part up everything first order. After the first order, if you part up everything, then the temperature field and velocity field will have a there are four what's called these four gradients will be non-zero. There should be a fluctuation, which since the system is outside the equilibrium, and they will vibrate with some sort of quasi-normal modes, which I have already discussed. In that case, in the right hand side, your T mu nu will have a first order and second order correction and so forth, whatever you can go up to the infinite order correction, but depends on the contribution. For example, if you are near the equilibrium, the contribution would be very small of the higher order term, the contribution will be very small. But if you are away from the equilibrium, depending on the how much away from the equilibrium, that much amount of term you have to include to get a good amount of estimate. Okay, so if your left hand side, the right hand side is the higher order terms, which includes the four gradient of U and T. The left hand side of the metric of the Einstein solution should have the higher order corrections as well. So T mu nu is 0 and x0. These are x0 mu is the four vectors. So this should this should not be a solution of the Einstein equation, and I have to find out the general solution of the Einstein equation, which has a kth order correction where k equal to 0 to infinity. Okay, so in the presence of perturbation, I have to solve the solution of the Einstein equation order by order. For example, here we will consider that up to the linear order. You can go to the quadratic order. The prescription is essentially the same. Okay, so here let's go to the first order. In the up to the first order, this is the solution of the Einstein's equation, and this is the related expressions. Due to lack of time, I will not go into details. So from here, the similar prescription, you can find out the boundary energy momentum tensor, which would be induced from the Einstein's equation. This solution, which would be like this. Okay, I'm not here. I have dot because this will include this del mu t and del mu u mu and so forth. So I'm not discussing to this. So the important thing is this, and sigma mu nu is the shear tensor, which I defined as the tau mu nu. The reason is it is traceless antisymmetric. Sorry, traceless symmetric. Traceless symmetric in the sense it will have a non-zero what's called the non-zero spatial parts. That means your one fluid will have a non-zero spatial part when its viscosity is non-zero. So that means it's a viscous fluid I'm considering. So that's why that will correspond to some entropy, some what's called the viscosity. Now with this, we can compare this with this generic form of T1 mu nu with the negative of 2 eta t sigma mu nu. We can get the viscosity will be 2 pi cube t cube. Now, so up to the first order correction, we can find out the viscosity and entropy density ratio is 1 by 4 pi. What we try to prove, and that is the proof that we are in the correct direction. Now, this exact result can be derived from some other part also. For example, this I don't understand this super angles theory, and they also got the same result. And now the another thing we will discuss what would be the event. I mean, how the event behavior of the event horizon with time. If you perturbed a little bit, and it's basically the when the outside of the event horizon also we let's I mean, and here also we can determine the event horizon. We will determine the event horizon, unlike the general relativity, not globally but locally at every point in the space time. So we would get a generalized solution where the event horizon at any point in x is with equilibrium plus some constant by pi t. T is the Hawking temperature, and sigma mu sigma nu sigma mu sigma nu in dot dot. So if you can see, when after after waiting for some certain amount of time, this term will have contributes, some which has a viscosity term. So for example, the shear tensor, this is come to be at equilibrium, and at the equilibrium there's a zero contribution. That means Rx equal to Rx0 plus some constant will be there, and it should be there because of the second law of thermodynamics. For example, the perturbation can be from the outside the external mass falling into the black hole. In that sense, your entropy will increase, and entropy means the area will be increased. So that is the that is the evolution of the evolution of the event horizon with time. So we have a one scale parameter, that means one radius, and that is the x mu. And if you see the initial time, there's a lot of perturbation. After that, the perturbation goes to be when the system comes to an equilibrium, that perturbation just simply fades away. So that's the perturbation with time. That is the event horizon locally, the dynamics of the event horizon. Now, since the fluid is dissipative, that's why this comes to an equilibrium. Now the conclusion. What is the importance of studying this fluid gravity duality? Now, first of all, in the non-linear regime, because in this talk we have considered up to the linear order. In the non-linear regime, the other transport coefficient can also be determined, and from there some interesting behavior of the fluid can also be calculated. And another thing is, which I have already discussed, for example, the quark-gluon plasma or the conformal fluids, then in that case the transport coefficients or these coefficients can maybe notoriously difficult to solve, to find out from the first principle. So in that sense, in that case, we can use the dual gravity system to determine them. And the third thing is, it is the some sort of work in progress. So it can be used to use in some sort of like cosmological singularity problems and so on. Some I don't understand this, so it has some sort of future in the fluid gravity duality because of the two things. One is it is easier to determine, easier to use, and it can lead to some part of the quantum gravity. And this is the 3 papers I have just used to write this talk. And yeah, I forgot to thank you, Chad. Thank you. If you have any question, let me know.
Thank you so much, Tanmay. Does any one of you have any questions from him? I don't think anybody has. So thank you, Tanmay, for your speech. It was it was quite mathematical. It shows that you have worked really hard on this. So thanks a lot. All the best for your future endeavors. All the best for whatever you are going to do. And I look forward to keep interacting. We all look forward to keep interacting with you in the future. Okay. Thanks a lot.
Yes.
It's been an honor for us to host you. Okay.
Thank you.
Okay. So then we move to the penultimate talk of our 2-day long conference. So the next speaker shall be another classmate we had at RKM Narendrapur. He is Sharthuk De. He is presently an M.Sc student at IIT Bombay. He's working in the realm of experimental condensed matter, more specifically nanotechnology, and he'll be giving out a talk on understanding indirect exciton in 2D semiconductors. Sharthuk, are you there? Okay, yeah. Please go on.
Let me share my screen. Okay, can you see the PowerPoint interface? Hello?
Yes, we can.
Okay, sorry. So let's start. First of all, good evening, everyone, and thanks to the organizers of the Young Physicist Meet for giving me the opportunity to present my talk here. I am Sharthuk De, an M.Sc final year student. Currently, I am working under the supervision of Professor Shubhobroto Dhar, Optomac Lab, Department of Physics. Now, my work is based on understanding the indirect exciton in 2D semiconductor. Okay, here I am giving a quick overview of my today's talk. First of all, I will start with the basic introduction and usefulness of 2D semiconductors. Then I will show the properties of molybdenum disulfide material. Actually, my work is mainly based on this material. And then I will show the results obtained from some theoretical formalisms and computational simulations, which are the eigenfunctions and binding energies of excitonic bound state in TMDC, HB, and TMDC heterostructure. Now, what is this heterostructure? It is a heterostructure where the hexagonal boron nitride material is sandwiched between two TMDC semiconducting monolayers. Now, hexagonal boron nitride is a dielectric material or insulating material. And hello?
Excuse me, Sharthuk?
Yes, you can say.
Yeah, what you can do is now you can put on a slideshow or something. Also, this isn't full screen. So maybe what we are able to see is very less. So
can you say the problem again? What is the problem you are facing? I can't understand.
Actually, the picture that we are able to see here is in full screen. Okay. So maybe you can maximize your screen and then put on a slideshow, so it will be easier for us.
No, I am actually in slideshow mode. So
okay, then your thing is not working. I mean, it's probably you just share again. You changed the slide right now, isn't it?
I just quit from the presentation mode.
Okay, so you start the slideshow again.
Okay. Can you see the whole screen? Only
yeah,
the slide
I can see. No, I can see the whole screen.
Okay, so
go for the slideshow, please.
Check again. Okay, I think in Teams there is some problems.
Many people are facing problems today.
So I am stop sharing. I will share again. Okay. So, the entire screen sharing option is not working, that's the main problem. I will have to select a particular window, and the window is showing my PowerPoint.
Okay, fine. If that doesn't work, whatever works for you, you go on.
So now, how much can you see?
Normal PowerPoint screen. I mean, like not the slideshow. You just tried putting on the slideshow.
Now what are you saying?
No, slideshow is not happening. You just quit. Okay, you quit the slideshow. Just show the slides one by one.
Okay. Please try to adjust with that. I don't know how to resolve the problem. Okay.
You just show the slides one by one. No need of slideshow.
Okay. So then I will show the eigenfunctions and binding energies of excitonic bound state. Oh, I have already talked about the heterostructure. So here the HBN or hexagonal boron nitride is the dielectric material, and TMDC is a special type of semiconductor material which is a full form of transition metal dichalcogenides. After that, I will show the oscillator state due to optical absorption by indirect excitant, and then the experimental approach to observe the indirect excitants. Then I will describe the growth procedure to actually produce the molybdenum disulfide monolayers by using chemical vapor diffusion method. At last, I will show the analysis of photoluminescence, Raman spectroscopy, and atomic force microscopy. These are the different characterization techniques for for any kind of material for as-grown and transferred MO2 samples. Now, what are the as-grown and transferred MO2 samples? The as-grown sample is the material or MO2 material grown on directly on the sapphire substrate by using CVD method. But transferred sample is the sample transferred from sapphire substrate to silicon dioxide coated silicon substrate by using some transfer procedure. I will describe that later. Now the two-dimensional semiconductor is a natural 2D semiconductor which is a thickness of almost few nanometers. Now, since its discovery, the 2D semiconductors have attracted a strong attention and scientific focus in research because of its remarkable and physical and chemical properties, which are tunable bandgap, very high charge carrier mobility, Cleving flexibility, etc. Now, because of these useful properties, 2D materials have used applications in electronic and optoelectronic industries. Now, transition and metal chalcogenides is one type of graphene-like 2D materials. This material is basically have the formula of Mx2, where M is the transition metal atom and X is the dichalcogenide atoms. The main categories of these materials are MOS2, WS2, MOSE2, WSE2. Now, among these four materials, the molybdenum disulfide is the most studied layer TMDC materials because of its core molybdenite is widespread in nature. Actually, it can be produced very easily by mechanical exfoliation from the molybdenite core. Then I will going to describe the structure of this material, where basically a hexagonal monolayer of molybdenum atoms is sandwiched between two hexagonal monolayers of sulfur atoms by strong sulfur molybdenum sulfur covalence bonds, and these sulfur molybdenum sulfur monolayers are attracted to each other by weak van der Waals force of attraction. Now, the semiconducting MOS2 material has a structure of 2H trigonal prismatic structure, where where we can see two different layers in every repeat unit. Now, from literature review, I have found that the MOS2 monolayers have a thickness of almost 0.65 nanometer, and here I am going to show the electronic and optical properties of this material. So, this MOS2 material in bulk form, it is an indirect semiconducting material with a band gap value of almost 1.2 electron volt. But if we reduce the number of layers from the bulk MOS2 and then we reach to the MOS2 monolayer, then it becomes a direct semiconductor with a band gap value of 1.9 electron volt. So the gapless or zero gap problem of graphene can be overcome by monolayer molybdenum disulfide material. That's why this material is very useful for optoelectronic and switching nano devices. This is the first Bellua zone of MOS2 in the material, and the Bellua zone mainly consists of two sets of points which are K and K prime. These points are degenerate in energy, but they are non-equivalent, and K1, K2 are the reciprocal lattice vectors. Okay. Now, I have mentioned earlier the charge carrier mobility of this material can reach to a very high value. Scientists have shown that this mobility of this material can reach up to 200 centimeters per volt second at room temperature with current on-off ratio of 10 to the power 8 in a MOS2 based transistor with hafnium dioxide at the gate dielectric. And another useful property of this material as photoresponsivity of this material can also reach up to a very high value, which is 7.5 milliampere per watt at a gate voltage of almost 50 volt. Now, the different procedures to grow MOS2 monolayers are mechanical exfoliation, solvent exfoliation, intercalation, and chemical vapor diffusion. Among these procedures, chemical vapor diffusion is the most useful one because the large area coverage by the material can be obtained through this procedure. And if we will be able to produce large area molybdenum disulfide flakes, then it has huge applications in integrated electronics. Now I am going to start the description of optical and collective properties of excitons. Now, exciton is basically the bound state of negatively charged electron and positively charged hole. Now, at first we will have to know what are direct and indirect excitons. In case of direct excitons, the electron and hole basically occupy the same semiconducting monolayer. But in the case of indirect exciton, as you can see here, the electron and hole occupy two different semiconducting monolayer with a insulating gap between them. Here we can see the indirect excitons. The electron and hole are situated at two different semiconducting quantum wells, which are separated by a insulating gap. So these are the A and B type of excitons present in the MOS2 material, and the indirect excitons can be formed in the TMTC, HB and TMTC heterostructure by optical excitation such as laser pulse. Now, the other types of bound states which are possible in 2D semiconductors are trion, which is basically a bound state of electron and the exciton, and it is basically negatively charged. Another one is bi-exciton, which is basically the bound state of two different excitons. And then move on to the next. So what is the motivation of doing this work? So the aim is to experimentally observe the indirect excitons in 2D monolar molybdenum disulfide in the heterostructure I have already mentioned. So what is the advantages of indirect excitons over the direct excitons? We have seen that in case of indirect excitons, the electron and hole are separated by an insulating material. So the recombination rate is very much less in case of indirect excitons than that of the case of direct excitons. So as a result, the indirect excitons also have higher survival time, that is in the order of nanosecond. So in the higher survival time, the indirect excitons can be processed with laser pulse. And we can also think about other excitonic devices and exciton-based logic circuits. So if we will be able to fabricate the excitonic devices, then the excitonic devices can produce so many advantages, which are high interconnection speed and high operational speed. And it will be also very useful for optoelectronic integrated circuits because of very small dimensions of the excitonic devices. And then I am going to describe the theoretical formalism here, and I will try to describe the excitonic bound state. The description is basically the binding energy of the excitonic state and the graphical representations of the wave functions of the excitonic state. Now, to describe the excitonic bound state, the excitonic bound state is basically a bound state of positively and negatively charged particles. So it is very analogous to the hydrogen atom problem. And the 2D Schrodinger equation to describe the bound state, so excitonic bound state, is this one. Here V is the interaction potential between the electron and the hole, RE and RH as the position vectors of electron and holes respectively. So the last Schrodinger equation was a standard quantum two-body problem. We need to solve the Schrodinger equation by using a separation of variables into relative mass coordinates and center of mass coordinates. And I have used the cylindrical polar coordinate system to describe the excitonic bound state. And this is the Schrodinger equation in relative coordinates format. Here V are the interaction potential between the electron and hole. Psi r is the wave function, and E is the eigenenergy. Okay. So to solve the previous equation, at first we will have to know the actual form of the potential, interaction potential. So I will start, keeping analogy with the hydrogen atom problem, I will start with the Coulomb potential. But in case of indirect exciton, the dielectric environment surrounding the excitonic bound state is inhomogeneous, and Coulomb potential is not able to handle this inhomogeneous dielectric case. So some modifications in Coulomb potential is required, and the modified Coulomb potential has the rate of Rickenbach-Redis potential, which is a form of this. Here kappa is the average dielectric constant of the dielectric environment of the excitonic bound state. Rho naught is the dielectric spinning length. Chi 2d is the 2D polarizability of the semiconducting material. Now from here we can see both the Coulomb and RK potential has central symmetry, and keeping analogy with the 2D hydrogen atom problem, we can say that here we also have two main quantum numbers, which are principal quantum number and angular momentum quantum number. So now I have done the simulations in the software Wolfram Mathematica, and these are the parameter values that I have used to do my calculations. So here I have used the dielectric constant value for hexagonal boron nitride as 4.89, and the thickness of each boron nitride layer is 0.333 nanometer. We actually do the calculations for different thickness and of the boron nitride layer. So N basically stands for the number of boron nitride layers used between the two semiconducting monolayers. So the other parameters used are the reduced mass of electron and hole and the 2D polarizability of the MOS2 material. Now I have collected all these values from literature review, and the values comes under the EB low column actually minimizes the binding energy of the excitonic bound state, and the values comes under the column EB high actually maximizes the value of the binding energy value of the excitonic bound state. So the actual binding energy value somehow lie in between these two maximum and minimum values. Okay. So now we will see in some graphical representations of the wave functions of excitonic bound states. So the graphs in this column represents the radial part of the excitonic bound state, and this is and these figures I have plotted mod psi square along z-axis, and xy plane represents the polar coordinates, which is basically rho phi. So these are the graphical representations of one state. So, I need to mention one thing: all the graphical representations have been obtained for keeping number of H mel layer is equal to 1. Okay, so these are the graphical representations for one state. These are for two state. These are the graphical representations of 3 state, and these are for 2p state. 2p state, and this is for 3p state. Sorry. So we can see the graphical representations of the wave functions of excitonic bound states is very similar to the hydrogen atom problem. Now I am going to present the binding and energy and values of this excitonic bound state. So here along I have shown the variation of binding energy values of excitonic bound state in milli electron volt with the number of hexagonal boron nitride monolayers between the two semiconducting MOS2 monolayers. So the red dots basically represents the maximum binding energy values, and blue dots basically represents the minimum binding energy values. So the actual value I have mentioned earlier, the actual value somehow lie in between these two, between the maximum and minimum values. And in case of Coulomb potential, we can see the binding energy is somehow higher between the higher than the RK potential. And we can also observe the binding energy of the excitonic bound state is sufficiently high. It is some hundreds of milli electron volt. So these are the binding energy for one state, and these are the binding energy for 2p state. And to observe the dielectric effects properly, I have done the calculations both for the Coulomb and RK potentials. Now here I have shown the transition energy. This is basically the difference of energies between 2p and 1s states in both of the case of Coulomb and RK potential. We have also show the variation of the transition energy with the number of hexagonal boron nitride monolayers. So here we can see, and here you can also see the binding transition energy is also higher in case of Coulomb potential than that of the RK potential case. Okay. So now I am going to show the oscillator strength and the computationally calculated values. So what is oscillator strength? Oscillator strength is a quantity which can express the probability of optical absorption or emission, which means from the oscillator strength we can get an idea about the probability when an excitonic bound state make a transition from an initial state I to final state F by optical absorption or emission of electromagnetic radiation. Now this is basically the mathematical expression for the oscillator strength, where I and F are the initials and final states respectively. Omega I to F basically the frequency equivalence of energy difference between the two states, and X is the direction of polarization of the incident electromagnetic radiation. So here we can see for the Coulomb, both for the Coulomb and RK potentials, the oscillator and the strength gets saturated. So here I have calculated the oscillator and the strength for the transition from 1s to 2p state. So the oscillator strength values we can see gets saturated with the increment in number of hexagonal boron nitride monolayers. And here for this case we can see the values of oscillator strength is very similar for both of the case of Coulomb and RK potentials. Now I will move on to the experimental section. Now first I will describe what should be the experimental approach to observe the indirect excitance. First we will have to grow the MOS2 monolayer using microcavity based CVD method using sapphire substrate, and then we will have to transfer the MOS2 monolayer from sapphire to silicon dioxide coated silicon substrate using surface energy assisted approach. Now why this transfer is necessary? Because if we use silicon as substrate, then the tensile strength from the material is getting reduced by a significant amount. So the band structure of the material becomes more uniform, and also the sapphire substrate is very useful in case of device fabrications. And after that we will have to coat that semiconducting monolayer with hexagonal boron nitride. This is a dielectric material. So after that we will have to form the TMDC, HB and TMDC heterostructure by growing another layer of molybdenum disulfide on the top of the HB and hexagonal boron nitride layers. So after that, we need the proper characterization of this heterostructure using photoillumination technique, and if we will be able to observe a low intensity peak which is very close to the direct excitonic peak, then we can conclude that the indirect excitons are present inside the TMDC HB and TMDC heterostructure. So for to get the actual position of the direct excitonic peak, we need to do the characterization for the monolayer case, for the monolayer MOS2 material at first. So here I will describe the growth, how the growth is being carried on. So here I have used basically the microcavity based CVD technique, where I have used the sulfur powder and molybdenum trioxide as precursors, which is basically based on the sulfurization of molybdenum trioxide material. I have used argon as carrier gas, and I have used two types of substrate, which are sapphire and dioxide coated silicon. So this picture basically shows the positions of the boats inside the CVD furnace, and argon is the carrier gas. You can show the direction of flow of argon. These boats basically contains the sulfur powder, and these boats basically contain the MOO3 powder and the microcavity produced by the substrate pieces. And here in this portion of this microcavity, MOS2 is generally formed. Okay. And this is the temperature profile maintained inside the CVD furnace. We can also see the change of flow rate of carrier gas argon and during each phase of the growth process. And the formation of microcavity can be understood in better way by this picture. This is basically the microcavity, the gap formed between the sapphire and these two substrate pieces, and we can see the sulfur, basically the argon carrier gas argon carries the sulfur powder, and the sulfur atoms are reacting with the MOO3 molecules to produce the molybdenum disulfide material. Okay, this is the reaction. So what are the results that I have obtained from the growth of MOS2 monolayers? Now the growth quality for sapphire substrate in case of MOS2 monolayer was very good, but we can also observe some continuous regions in the sapphire substrate covered with MOS2 monolayer by optical microscopy. But the film quality grown on silicon dioxide coated silicon substrate was very poor. But so right now I am trying to optimize the growth procedure by changing the growth parameters such as the amount of precursors taken, the flow rate of the carrier gas, and the temperature of the temperature in the CVD furnace to improve the film quality on the silicon dioxide coated silicon substrate. Because if we will be able to get good quality film in silicon substrate, then we can skip the transfer procedure. So it will be very useful for the whole experimental work as well. Okay, here I will describe the transfer procedure. At first, we first have this MOS2 monolayer on sapphire substrate. We need to spin coat. We need to coat this MOS2 monolayer with a polymer named polystyrene using the spin coating method. After that, we generally bake this whole structure. This is polystyrene MOS2 sapphire at 80 to 90 degrees Celsius for 15 minutes, and then we utilize the water penetration technique to detach the sapphire and MOS2 layer. So the water penetration can be started by itself. We need to poke, we need to scratch the edges of the sample by a sharp object to initiate the water penetration. Here, basically, sapphire is a hydrophilic material and MOS2 is a hydrophobic material. So water penetrates. So when water penetrates between the MOS2 and sapphire, is basically detach these two materials, and after when the water penetration is complete, we can just pick up the MOS2 PSA, MOS2 polystyrene layer and with a tweezer, and we can just place it on the target substrate, which is silicon dioxide coated silicon, and then we will have to again bake it at a temperature of 120 degrees Celsius at for almost 15 minutes, and then finally we need to dissolve another whole sample and into toluene solution to finally we need to dip the whole structure or whole sample into toluene solution to dissolve the polystyrene material from the top of the MOS2 monolayer. Okay, now here I am going to show the analysis of photoluminescence spectroscopic data that I have done for the monolayer MOS2 materials. Now, So for the photoluminescence and a method, all the photoluminescence and measurements have been taken with the incident laser radiation of 532 nanometer. This spectrum is basically the photoluminescence spectrum of MOS2 material grown on sapphire substrate at room temperature. So here we can see the exciton or trine peak is appearing at 1.87 electron volt. This is the photoluminescence measurement of MOS2 material grown on for as-grown samples grown on sapphire substrate at a very low temperature, which is 100 Kelvin. So here we can see a what the luminescence and a feature appearing due to defects, and these defects are basically coming because of the sulfur vacancies present inside the MS2 material. So we can see this defect peak is basically consists of two different consists of a high energy defect peak and a low energy defect peak, and the exciton time peak is appearing at 1.93694 or 93 electron volt. Here basically I have done a mistake because through experiment or by the use of instruments, we can reach up to the 4th digit after the decimal. We can reach up to almost 2nd digit up to the decimal. Basically, I got this value by simulating in a computational software. Okay. So here we can observe the exciton or trine peak is suffering a blue shift due to reduction in temperature. So then this is the photoluminescence measurements of transferred MOS2 sample from sapphire to silicon dioxide coated silicon substrate at room temperature. This is the exciton or excitonic trine peak, which is basically for the A exciton, which is appearing at 1.88 electron volt, and this is the peak for the B exciton, which is appearing at 2.1 electron volt. And then this is the photoluminescence measurement of MOS2 sample transferred from sapphire to silicon dioxide coated silicon substrate at 90 Kelvin temperature, which is low temperature. So here we can again we can see the broad luminescence feature is appearing at before the exciton and trine peaks. But here we can see a different thing, that the trine peak is separated from the exciton peak, and the trine peak also has a higher intensity than the excitonic peak, and so the trine peak is appearing at 1.92 electron volt and the excitonic peak is appearing at 1.96 electron volt. So here we can see again that the exciton and trine peaks are suffering the blue shift due to the reduction in temperature. Now I am going to show the Raman spectroscopy data. Now Raman spectroscopy is the study of vibration of molecules present inside the materials. Now basically you do the Raman spectroscopy and atomic force microscopy to prove that the grown MOS2 material is monolayer in nature. So there are two types of characteristic peaks are present in the Raman spectroscopic measurements, which are E2G1 peak and A1G peak. Now E2G1 peak corresponds to the in-plane vibrations of molecules, and A1G peak corresponds to the out-of-plane vibrations of the molecules. Now the difference between the difference of Raman shifts, this is the Raman shift plotted in x-axis, between those two peaks lies between 18 to 22 centimeter inverse for monolayer MOS2 material. Here we can see the difference is 19.95 centimeter inverse, which is an evidence of monolar molybdenum disulfide material grown from the chemical vapor deposition technique. So in the case of transferred material, transferred from sapphire to silicon dioxide coated silicon material, we can again see the difference of Raman shifts between E2G1 and A1G peak is 20.14 centimeter inverse, which again proves the transferred MOS2 film is monolayer in nature. After that, I will show the.
Yes. I'm really sorry to interrupt, but just I had one question before. Just go to the 28th slide number 28. So in the transferred monolayer of MOS2, do these E2G and E1G peaks suffer a blue shift or a phase shift? I mean, sorry, a red shift. Just check.
No. See, the Raman spectroscopy data have been taken at room temperature solely. I have not done the experiments at low temperature, and I can say comment on the blue shift before doing the experiments at different temperatures. Okay.
No, like you have done both at the same temperature, right? The transferred and this thing.
Yes. Transferred and this
just check like if there's a shift, like here E2G was happening at 385.98. We'll go to the next.
The change or amount of blue shift is very negligible. Okay, so
there is a blue shift, right?
There is a blue
Energy
shift.
is reducing means blue shift. Okay. Okay. Blue shift should happen because of strain release. Okay, please go.
But it is not significant in amount. Okay. So here results obtained from the atomic analysis of atomic force microscopy data. This is the vertical image profile of AFM image. AFM is a short form of atomic force microscopy for Ashburn MOS2 sample obtained from the nanoscope software. This triangular flex actually represents the MOS2 layer. So for determining the thickness of the MOS2 layer, I basically drawn random lines across the circumference and of this triangular flex. Took the thickness at each point, and then I have plotted a histogram of the different thickness using MATLAB. Where you can see the histogram here, and the maximum and the number of counts is coming between 0.6 to 0.7 nanometer. And from the literature review, we are seeing the monolayer molybdenum disulfide has a thickness of almost 0.65 nanometer. So somehow we can say that the MOS2 film grown from CVD technique is monolayer in nature. And the last one is the analysis of AFM data for the transferred MOS2 sample. Here the light colored region and represents the MOS2 portions, and here I have used the same technique to determine the thickness. So here you can see the maximum number of counts for thicknesses is coming between 2.5 to 3 nanometer. But so here you can conclude one thing, that a thin layer of the carrier material polystyrene is present over the MOS2 monolayer. So after the transfer procedure, we basically dip the sample inside the toluene solution, but this dipping does not completely dissolve the polystyrene material. Okay. This is the conclusion of the analysis of AFM data of transferred sample. Now the future plan of my work is, till now I have done all the theoretical calculation. Till now I have done all the experiments and analysis of data for the monolayer samples only. Now currently I am working to prepare another TMDC HB and TMDC heterostructure, and next I will try to experimentally observe the existence of indirect excitons inside this heterostructure using different characterization techniques. Okay, these are the references that I have used during my work, or currently I am using these things. And thank you everyone for giving me the opportunity for presenting my work here. I think this initiative will help me a lot in my future to carry on my work. Thank you.
Okay, Sharthok.
Yes.
I mean, I actually have a lot of questions. I don't think I'll just take some time, and I hope you, first I'll say that you have done a lot of work. I don't know how you have done so much in such a short time, but then I'll ask you a few things just to, just for my understanding. That is, you said that MOS2 is used, can be used, MOS2 monolayers can be obtained via intercalation also, right?
Yes.
Yes, so if it can be obtained by intercalation, in your lab has there been any application in electrochemical systems, like batteries or something like that?
No, I don't think so. In my lab, people only use the chemical vapor deposition technique, because
that is how you manufacture it. I mean, if intercalation, when intercalation method is used, it's usually used in supercapacitors, batteries and stuff, right? So there has been okay, fine. Okay, you talked about indirect exciton, right? Now you said that indirect exciton is obtained when there are multiple layers, isn't it?
Multiple layers are basically two semiconducting monolayers.
So exactly. So if you have multiple, at least a bilayer, then that doesn't remain a monolayer, right? That becomes a bilayer.
No. Sorry. You are mixing up things. Two semiconducting monolayers are separated by a insulating material, which is hexagonal boron nitride. I want to say first you have a semiconducting MOS2 layer, then after that you are basically coat that semiconducting monolayer with hexagonal boron nitride, and then again you are coating that hexagonal boron nitride layer with another semiconducting monolayer.
Okay, fine. Also, there's one thing, I saw in one of your graphs that when the number of monolayers increase, your binding energy of the exciton reduces, some kind of renormalization probably. Do you know why this happens?
No. I didn't increase the number of monolayers. Number of monolayers is fixed. this is the number of hexagonal layers present between the two semiconducting monolayers. So basically, you are changing the thickness of the insulating layer present between the two semiconducting monolayers. Okay. So
like, why is the exciton binding energy reducing with the number of HBN monolayers?
This is very natural now, because the dielectric strength is increasing in that case, and also physically you can see the distance between the electron and the hole is getting increased.
Okay. So its energy is reducing, binding energy. Okay, fine. Also, like in the experiment, you have used like the growth process is happening at 8 SCCM. Okay.
8 SCCM basically the operational flow rate of argon.
I mean, for example, when we grow WS2, we use 100 SCCM here. So, I mean, your like this flow rate is required for the vapors to go and deposit on the oxide powder, right? So, like in 8 SCCM, the things happen, and like you come down from 200 to 8. Like this, there's a rapid shift here. I mean, can you tell me the reason why this happens? Like.
Basically, my senior told me that we use the 200 SCCM because before going to the 8 SCCM to first remove all the residual molecules such as water vapors and oxygen molecules present inside that CVD furnace. And then 8 SCCM is the operational, because if you use the argon flow at very high flow rate, then it will basically the reaction cross section between the molybdenum traction material and the sulfur molecules will be very less. So I want to say the sulfur molecules will not get enough time to react with the MO3 materials.
Okay, that means you must be getting I mean quite wide things. No? I mean your monolayers area should be wide. Like, what is your I mean dimension of the, like in the optical images you must have, what is the dimension you are getting?
It covers during using this microcavity based CVD technique, the most monolayers covers almost centimeter square area coverage.
Centimeter square? Oh my
yes,
God. That's huge. Okay. And last question, like it's you had somewhere told that whenever the temperature reduces, there was a blue shift. I mean, I saw somewhere in your Raman or PL something like that.
This one and this is PL.
Okay, so you said that when the temperature reduces, there is a blue shift. Can you explain why?
I can. This is you can understand that the band structure and the band structure basically has some dependence on temperature, and this should have the empirical expressions also between the band energy gap and the temperature. But I don't know what is the actual expression. So
okay, fine.
I can't explain.
Okay, fine. Thank you, Sharthak. I mean, extremely good. I mean, as I'm working on a very similar field, I can actually say that you have done really good work. Thank you. Okay. And please keep helping me.
Seniors also helped me a lot to increase my work.
Okay, so you go and enjoy your mood indigo.
Okay,
thanks for coming in here. Okay. So we'll go on for our last speaker of the show. The last speaker for our conference, for our 2-day conference. So we welcome Mr. Purvesh Garg from NISER. He's working in the field of cosmology, and the topic that he'll be delivering talk on will be orbit construction for Indian lunar orbiter for observing epoch of reionization. Purvesh, the stage is yours.
Yes. Am I audible?
Yes, you are.
Yeah. Let me share the screen. Okay. Yeah. So is it visible? Like my screen is visible?
Yeah.
Yes.
Yeah. Okay. So in this talk, like I will be telling you, like talking about some like how the orbit of any satellite could be constructed using some software which is constructed, like maintained and managed by the NASA. So in this topic, then in this entire talk, I would not be using any mathematics here, just so you can just sit back and relax. So let's start with our talk. So first thing is like, what is the epoch of reionization? Let's go in a backward direction. Like, so what is the epoch of reionization? So we know that the universe was formed about 14 billion years ago,
and after around 370,000 years ago, the universe, which was actually opaque after the Big Bang, got transparent, like due to the recombination of the particles like protons and electrons. They got recombined and they formed the atoms. So as soon as the atoms were formed, the gas was free, the entire universe was transparent. So that is what we call as the recombination epoch, or the epoch of recombination. Okay. So now what happens is, like, as the universe was expanding, our gas in the hydrogen gas, which was inside the universe, was cooling down as it was expanding. So as the gas cooled down enough, so that even the atoms could, like, the enough means, what I want to say is, like, when the gas were cooled down enough so that now stars could form, like there could be that gravitational collapse of those particles, so that you can start forming the stars. So as the period at which the first stars were formed, what happened is, like, those stars, they are very bright and they're really huge and very bright, and they are expected to emit in UV. So what is now happening here is, like, you have a star which is formed, is emitting in UV, and around that star you can see there's this interstellar hydrogen, neutral hydrogen atoms around that star. So what will happen is, like, as soon as the UV ray will go out, it will knock out that electron inside that hydrogen atom. So what will happen is, like, as soon as the electron get knocked out, we have this again the ionization of that hydrogen atom. So let's say there are, like, multiple stars which just formed. Now they start emitting in UV. What will happen is, like, entire interstellar medium in between those stars is now ionized. As soon as it's ionized, now you have a similar problem which it was before the epoch of recombination. That is, now you again have an opaque interstellar medium. So what will now happen is, like, now the light cannot travel. As soon as the light tries to travel, it will get absorbed by some atom or some particle, and it will again re-emit. So this will happen, and the photons from those first stars cannot reach us. So this is a problem. Like, you cannot see the first stars which are formed because there is this ionization of the interstellar medium. So that is what we call as the start of epoch of reionization. And as the entire interstellar medium was ionized again, this is known as the dark ages. As you can see here, dark ages. It is in marked here. So now, so the problem here is, like, you cannot observe the first stars. So in order to observe that, what you need is some method. Like, how can I see within, like, I cannot see the dark ages. It is not possible for me because there is no light coming from it. So either I can just look at this boundary, or I can look at this boundary. So even if I'm able to get this, I will be able to, like, extrapolate, like, what would have happened to the first stars. So the question is, like, how will you detect those atoms, that emissions? So the one way to detect, a standard method in cosmology, is to look at the 21 centimeter line. So 21 centimeter line is a very specific line, so that it is created when there is a spin flip transition of a neutral hydrogen atom. So what is happening is, like, there is a triplet state. Whenever the triplet state goes into the singlet state, what you have is a emission, because there is there's this emission of 21 centimeter line. The energy of it is 5.87 micro electron volt. If you convert it into wavelength, it is 21 centimeter. If you convert it to frequency, it's 1420 megahertz. So now the problem with this transition is, like, it is very highly unlikely. You can see that the probability of this happening is 2 × 10 to the power minus 15 per second. So from this, you can easily interpret that the strength of the signal would be weak. Yeah, there are more atoms there. You will still see the signal, but strength of the signal will be weak. So now I have to look at the signal, which is very weak. Okay. So in order to, like, any signal, if I have to observe, I have to use some telescope. So, and 1420, and the thing here is, like, since the epoch of reionization was the dark ages period, it is being calculated that the redshift, because as the universe is expanding, you will have a redshift. The redshift of that period is about 20. So if I calculate it, do some math, and I would get it, the signal should be around 100 to 200 megahertz. It is that the frequency. So now we have a thing is like we have a signal which is 100 megahertz. Yes.
Why you are considering, I mean, only one frequency? There could be some multiple frequency, right? I mean, the transition is not confined.
This is the only, because this is only one transition, because there could be multiple frequencies, but I want to look at a one frequency. That is that because I'm only considering one frequency because it is standard to that atom. I only want to look at hydrogen because when this epoch of ionization started, there was only hydrogen. There was no helium. Later, I could have any frequencies. But I would specifically want to look at the 21 centimeter because I know that it's the only atom which will, it is only standard frequency for neutral hydrogen atom.
Okay, so it's just a standard. That means we could use some other frequency also.
You could use, but the thing is like that frequency could come anywhere.
Yeah.
It's like just some kind of a standard candle. Like I have that.
Yes.
Because it will always be 21 centimeter. No other frequency from that.
Okay.
So that's what I'm looking at. So now once I see that, okay, I have a signal. Now I have to observe it. So in observe, I have to use telescope. So the problem is that at 100 megahertz we have a problem of our atmosphere, because as you go down the frequency, the problem is that your atmosphere starts becoming opaque because of water vapor. Because if you see the precipitable water vapor, it has a tendency, and many other atmospheric components, they tend to absorb those frequencies. Now I have a signal which is weak and also getting absorbed. So it has become very difficult for me to construct a telescope which could observe it. The problem is like, first thing is it is absorbed. Second thing is like, if I have to construct it and observe it, I need to have it a very sensitive telescope. It has to be very sensitive. Now I can construct a very sensitive telescope. It is not a problem, but the problem comes from background. So again, if I construct a very sensitive telescope, it is prone to more of noise. It will pick up in even the smallest of noises which is around you. Even a stone. Let's say even anything, any man-made devices could emit in that frequency range, and it will even catch very far away noises. So that is a problem. And the biggest problem that we have, if we want to observe it from the ground, is FM. Because what we know that it is around 100 megahertz. So as we know, our FM that works in 80 megahertz to 110 megahertz, and FM is a very, very strong noise. Like it is so big that it becomes very difficult for you to eliminate that. So I cannot use, like it is possible, but it is not feasible to use a very sensitive telescope to observe this. So the other option that comes into picture is like, let's take that telescope into space. So I have an option that I could put it in a Earth's orbit. So if I put in the Earth's orbit, the thing is like, these are radio frequencies, and radio frequencies, like they travel a lot, and according to like that, the strength that we have here on the Earth is strong enough that it could go in our outer space as well. So getting into space, I can get rid of the atmosphere, I can get rid of the some surrounding noises, but I cannot still get rid of all the frequencies that come as a noise in that range. The problem will be sun. You can consider sun as almost a black body. So if you have a sun we consider almost a black body, it will emit in all frequencies. So again, there will be a noise from sun as well now. So we have a problem again if you put it in a Earth's orbit. So the second thing that you can do is put it in a moon's orbit. So why moon's orbit? Because let me go here. Yeah. So this is the moon's orbit. So what will happen whenever I will come here? If you say, whenever I'm on the far side of the moon, I automatically block the emissions coming from the Earth. I automatically block them. Now what I have to do only take care of is what is the position of the sun, because the actual quiet zone, the radio quiet zone, we call it radio quiet zone because there is no radio emissions there. It is very quiet for observations. So in order to calculate the radio quiet zone, I just have to look for the sun now. Whenever my satellite will be in this far side region, so whenever it is on the far side region, I will have a radio quiet zone for the Earth. And once I know what is the position of the sun with respect to the moon, I can calculate like what will be the total radio quiet zone. That is the intersection of radio quiet zone for sun and radio quiet zone for the Earth. So this is what you call as a total radio quiet zone. Okay, so this is what is the thinking that okay, how should we get the most quietest zone? Because the another reason for choosing the moon is like the moon surface is a very good what we say very good obstruction that could block, like it could block it is a very good object, so that it could absorb all the frequencies. It will absorb and reflect all the almost radio frequencies. So this is one of the good this is why we are choosing the moon. So now this is the plan that we are doing. So actually the actual telescope which would be probably flying is named as Pratyush. So Pratyush stands for probing reionization of the universe using signal from hydrogen. That is the full form of this Pratyush mission. And this is majorly worked by Raman Research Institute. They are working really hard on this. And this will be a space-based probe for looking for epoch of reionization using a spin flip transition of again the same thing. And the baseline frequency range of the Pratyush will be 55 to 110 megahertz, which is the most probable, which we have calculated that okay, this will be the frequency range at which we can observe that epoch of reionization period. Also, this you can see that the baseline period is the baseline range frequency is 55 to 110 megahertz. That means again the FM we have comes within this range. So it is better to put it in the space on the lunar orbit to have the maximum obstruction from the radio frequencies. So now if we have to construct the orbit, the first thing that we need to have is a coordinate systems. So in order to calculate anything, I need a coordinate system. So this is the first there are two coordinate systems which we'll be using. One is a body fixed coordinate system.
That means to stay in a continuous radio quiet zone, your satellite need to rotate in a very complicated manner, right?
What do you mean by complicated manner? Like what?
It had to block the Earth's.
Yes, but it did not. Yeah. See, if you see here, my orbit will be like this, rotating. Now, if you see the radio quiet zone for the Earth will be this only, all the time, because we can only the only one face of the moon is there. We can observe only one side of the moon, but the moon is revolving around Earth and Earth is revolving around moon. Earth is revolving around sun. So what is happening is like this cone will shift. This radio quiet cone of sun will shift. So you need not have every time you will not have like in 1 month, let's say you will not have all the 30 days of observation period. No, because what will happen is like one day, like this cone will be like this, and this radio quiet cone will be literally perpendicular to it. Now there will be no intersection of the cones. You cannot observe. Fine, like I would buy it still, because if I put it in a, let's say, let us assume that I put it in a some like what we say some stationary orbit, let's say, because like it will be always be, let's say, at this point, it will be of no use to me, because I can never have a like I would have either the first thing is that I will have less time in the radio quiet zone. Second, I will never be able to transmit my data. So I'm fine with like even if I get some few thousand hours in few minutes in every orbit, I'm fine with it. So that is the thing. Like it will be very simple orbit, no magical things happening out there. It will be very simple orbit. It will observe for like 10-14 days, and for 14 days it will not observe. Fine. That's the idea here. Because you cannot block out everything because of the configurations.
Yeah, but they could use the umbrella-like structure what James Webb Space Telescope is using to block the sun and Earth both.
Yeah, but still, what will you do for the Earth?
Yeah, that is a problem. Okay.
Yeah. So what we will be looking at the two coordinate system. One is the body fixed coordinate and another will be object reference coordinate system. So what is a body fixed coordinate? Simple. Like I will take a moon. Okay. I will put my origin at the moon. I will extend my x-axis to be the line joining the Earth and the moon. That will be my x-axis. My z-axis would be the zenith, like literally north pole of the moon. I don't care about z-axis although, but fine. And y-axis is of no use to us. The only axis that we want is x-axis, because this will define our 0 degree mark. So this is the body fixed system. So next will be the object reference coordinate system. So what object reference coordinate system is like, I place origin and one object and I put another point on the second object, and I look at the relative motion of both the bodies with respect to each other. So the line or my x-axis would be this r. This will be my x-axis, you could say. And the relative motion, I will just look at the relative motion, and I would put the like r to be my x-axis, which will mark my 0 degree mark, because I have to calculate the angle. What is the angle of my satellite with respect to the other body, with respect to both the bodies rather. That's why. So this is my x-axis. Velocity I don't care, and my z-axis would be again the normal to the point joining the two bodies and the velocity component of it. So these are my two systems. So like, is there any doubt regarding this object reference, because this is a bit complicated thing? Okay, so let's go. Like, so the first thing is like how we determine those cones. Like we've seen that there are two cones: radio quiet cone for Earth, radio quiet cone for Sun. So thing is like how do you know what is the size of the cone for anything? So the first thing is like, we will see that the radio quiet cone. What is the size of the radio quiet cone? So we calculated this by extrapolating the data of a simulation which was done by the Neil Bassett during their mission of 2017, and then they postponed the mission and eventually cancelled it. So the calculation was done by the electromagnetic simulation using the finite time difference simulation by the Neil Bassett, and they simulated each and every parameter, like at this frequency range, how is the frequency bulge which is coming out from the Earth. They calculated everything. They've done a very big simulation on the supercomputers, and they have written a code from which you can calculate according to your the frequency ranges. You just have to give your frequency ranges and what is the altitude of the satellite, and it will calculate accordingly, like what will be the size of the cone that you will get, like what is the range of the cone, like how many degrees you could get of the cone. For the sun, since you know the sun is very far from us, it is a very good approximation to take a plane wave. Now you have a plane wave, you have a object blocking, you can easily calculate like what will be the quiet cone, radio quiet cone that you will get. Like I know that the only thing that you need to find from some literature is what is the size of the like what is the frequency emissions, like what is the strength of the emission of the sun in that frequency range. That's the only thing that you need to find, and we found that from the literature and accordingly calculated it. So we found that once the satellite in that object reference frame, because my origin will be here in the object reference frame, if my satellite goes past the 110-degree mark from the 0 degree, from like 0. If I take my orbit to be like 0 to 360 degree, if it goes past 110 from each side, like from even left or right, my I assume that my satellite is in radio quiet zone of the sun. That's how we have seen. So now in order to calculate, now we have calculated everything, but now we have to simulate, like how do we do the simulation of the satellite, like how to construct the orbit. So for constructing the orbit, we use a software known as the General Mission Analysis Tool, or GMAT. So GMAT is the software which is maintained and it was constructed and maintained by NASA, and it is a very high fidelity software from which you can like literally launch a satellite. Like it has a very high precision of almost of 10 to the power minus 12 kilometers of like you can create, and if you put it in a satellite, and that if as the satellite will execute, it could have a precision of 10 to the power minus 12 kilometers. Like it is that precise in creating those creating that orbits and inserting it. So now we have used the software, we know, but there are some things that which we require to give the inputs. Like what would be the inputs? So in order to create any orbit, we need 6 parameters. Any orbit requires 6 parameters that distinguish each other, like two. So these 6 parameters are like semi-major axis. We know everyone like what is semi-major axis. Eccentricity. Eccentricity is like how much your orbit is deviating from a circle. That's just eccentricity. Then inclination, how much inclined your orbit is from the equator of that body. Like if I expand my equator to be the very big, if I this is my plane of reference, or let's say the equator of the body, and how much tilted my orbit is, will give me that what is the inclination of the orbit. Then comes the RAN, that is right ascension of ascending node. So what right ascension of ascending node is like, at let's say this is my reference axis. Okay, this is my reference axis. It could be anything. Let's say it is my 0 mark. At what point the ascending node? What is the ascending node? Is like at what point the orbit, the satellite will going up in the at the positive inclination rate. That is going from down to up. Like where the actual orbit, the actual plane of the orbit cuts the reference axis, reference plane is the point. There, like it will cut at 2 points, like this point and this point. This point is ascending node because the satellite will go down here and go up. At what point it goes up is known as the ascending node. And what is the angle of that ascending node with respect to the reference axis is called as the right ascension of ascending node. Then there is the argument of perigee. What is the argument of perigee? Like at what is the angle of your perigee? Perigee is periapsis. Like argument of perigee or argument of periapsis. So at what is the angle of the periapsis with respect to the right ascension of ascending node? With what is the AOP is the angle of your perigee with respect to RAN. And true anomaly is like what is the angle? What is the angle of your satellite, your satellite with respect to the argument of periapsis, AOP. Or you could, like, in order to understand, you can take TA as also as the point of his insertion as well. It doesn't matter. Like this is not that of a big deal, but rest of them are a very big deal with respect to constructing an orbit. So this is the layout that we have in the GMAT. You can see I have give it a epoch. What is the format of the epoch? What is the epoch? Because the positions of planets and all the celestial body change with every day. So epoch is very, very important for constructing anything, because every day the location, the positions of the celestial body would change. They would change the gravity that the satellite would experience. Then there is this, I've fixed this. There is known as the moon fixed. That this is the body fixed coordinate system in which my origin is on the moon. My origin is the moon, and it is fixed to the as we discussed in previous, like what is a body fix? It is just a body fix with the origin at the moon. And this is a state that how I will give the parameters. These elements, how will you? I will giving Keplerian form. So I have SMA here, that is 1850 kilometers, which is around 100 kilometers. Like because the size, the radius of the moon is 11737 kilometers. So it is around roughly 100 kilometers. Eccentricity 0.018. This is very near to circle because eccentricity, as you can see, it is 100 kilometers. So it's a very low lunar orbit. In low lunar or in any low orbits, eccentricity plays a huge role. Like even if I change it by slightest of amount, my satellite could go haywire. Like it could go into it could crash. It could easily crash because this parameter is very, very important. Even inclination is very, very important. Like these two parameters are very, very important. They are very sensitive. The orbit is very sensitive to this. Then RAN. This, as we know, we have given 0 degree, AOP being on 180 and TAS 360. Like TA and RAN overlap, that means it doesn't matter. So now,
I mean, why the inclination has a like 10 digit after the 287? Is it manually given?
What?
If you see the inclination angle after 10 or 15, there is 287.
Yeah, what I gave is 1.5. Then what I run the simulation. Okay. I run the simulation. What happens is like it will change those parameters slightly in order to maintain the accuracy of the differential solver. Like if I go ahead, let me go ahead. I will show you. You have here Rangekutta 89, which is your integrator, and you have this accuracy. So in order to, it just changes your parameter very slightly, or at 8 or 9th decimal, just to maintain this. Just to maintain the accuracy at very first step, because as you go integrator, this is your differential equation solver. As you iterate, it will go one by one. So just to maintain its accuracy at very first and last steps, it just changes your inputs very slightly. That's how you could see. Even if I give like this, I have given here 1850, but it came 1.849.9999992.
Yeah.
It just changes very slightly in order to incorporate that accuracy at the very first and the last steps.
Okay.
So now I have created the orbit, but in order to hold that satellite in the orbit, I need the gravity. The gravity is the only force which will be acting on it. So now we don't know how the gravity of the moon is. So there was this mission known as the Grail mission. Okay, the gravity recovery and interior laboratory, the Grail mission. There were two missions which were flown by the NASA to map the gravity. So the data that came from that Grail mission, they used to create the models, different gravity models. Okay, there's this Grail 50, Grail 180, Grail 420, 660, 900, 100, and 1200. Okay, so the Grail is fine. What 50 shows is like, because gravity, the gravity of the moon is not symmetric. It changes, it fluctuates a lot. So you consider the numbers which are here, they are just the degrees and orders of spherical harmonics that the model can solve. That's the only thing, that it could sound like 50 degree and 50 orders of spherical harmonics, and 180 can solve 180 degree and 180 order of different that spherical harmonics. So this is the latest one, Grail 1200. In this simulation that we have done, we are using this Grail 1200, which is the latest, and I think it was launched 2020 maybe. Yeah, it was launched in 2020. So this is very recent and very high precision. This has a what we say. This has the resolution of 5 kilometers. Like each patch that they have mapped, like they have taken as you know that there are pixels. When you take a photo, there are pixels. There are number of pixels, and the pixel has this size. So each pixel that they have taken, they have a resolution of 5 kilometers. That is the they have made a 5 kilometer block, and they have averaged the gravity over the 5 kilometer block on the moon. So entire they have mapped the 3D model of it, and they have constructed this lunar gravity model. So this is the propagator, or whether where you give the, as you can see here, here's this GRGM 1200A. We have degree 100, we have over 100 degrees, and order also 100. These are error correction steps which are inbuilt or inbuilt. Okay, sorry, inbuilt features of the GMAT software, and we are taking gravity of all the other celestial bodies, prime celestial bodies, I'm saying, which are inside our solar system, like sun, all the planets, that is, as point mass. That they are taken as point mass, and their influence is to consider using this. We are also considering a solar radiation pressure. Okay, so there would be like, the satellite would have its own solar panels, and which will experience those forces, so radiation pressures. So we are considering it as well, and we are taking for now this, because this is a first order calculation for that satellite. This is the solar radiation pressure is we are considered to be spherical radiation pressure. Okay. So now, after putting everything into the software, we run the simulation. So we run the simulation. So our y-axis shows the semi-major axis. Y-axis is semi-major axis. X-axis is the time. Like we want, because this mission is planned to be of around 2 years. So we have to look that whether our satellite is stable over the course of the 2 years without any external boosts, because without any orbit correction maneuvers. Okay, so here we are seeing that, okay, this is falling slightly around. If you see, this is the apogee, this is the apogee, and this is the perigee. Okay, so if you see here, it is very going down to some around 17, maybe, like it is falling just around 30 kilometers above the surface. So it is not coming into the atmosphere that is there of the moon, because we don't know how high the atmosphere goes. So we have to maintain some altitude, some margin for that as well. So that so we have put a threshold of around maybe 25-30 kilometers. So if the orbit goes below that, we consider it to be crash, because it will then experience more and more drag from the moon's atmosphere, and eventually it will result in the it will, as you know, it will lose its velocity, and more orbit correction maneuvers would require, and eventually it would run out of its life. So as you can see, you can see the influence of all the bodies as well as the moon. You can see that how much it is fluctuating. That shows that how asymmetric the moon's gravity is. So this is what we found in our result, like how this is our orbit looks, and then we did the calculation for how much time it will spend in that radio quiet zone, and we found that the maximum time the satellite will spend in one single orbit, that is what is the what we say in lunar eclipse configuration. Let's say you have a lunar eclipse, that is the period, that is the configuration of the sun, moon, and earth, that would give us the maximum time for observation. We found it to be around 42.05 minutes for over the orbit of 2 hours. That we have the orbital period can be given by you, like you can configure it on your own. It does not need any other things. You can just give it an orbit to be 2 hours. It will have the simulation will have a 2 hour orbit, and we found that the cumulative time spent by the satellite in radio quiet zone will be around 2,200 hours. This is slightly at a higher end. We don't expect our satellite to have this many hours. So being this first order calculation, we take it as a okay, but still it needs to be lesser, because it is way too high for it is predicted way too high than the predicted one. So we expect that this happens due to the coordinate system that we are taking, because the object reference coordinate system is a non-inertial frame of reference. It is, so that could be, we predict that, okay, that could be the one which would be the troubling part, like giving us the higher number. So I think I end my talk here. Maybe if someone have any questions.
So over the course of 2 years, I have to, I mean, the satellite have to stay in the radio quiet zone for a very small amount of time.
Yeah, it will, and yes. But the thing is, like, your orbit is only 2 hours. That is, if the orbit is 2 hours, that is in one day it will have 12 orbits. I could use that. It will have 12 orbits every day. If I multiplied by, let's say, 730, calculatedly, you will have around maybe 8,500 orbits. I would take it.
Okay.
And you could, and the minimum would be 0. Like, it would, because there will be a configuration here. Let me go back. There will also be a configuration that my Earth is on this side, my Sun is on this side. Absolutely no. All the sides will be affected by the radio interferences, radio frequency interference, RFIs. So the most is like when both of them overlap completely. You will get the most time, and when they are, and this is when they will have most time, will be the point where when more Sun and Earth both will be on the same side, and that is the lunar eclipse configuration, which will have a most time, because at that time you have both of them going, both of them aligning very well. So you will have a most amount of time in the radio quiet zone. Any other questions?
Hello.
Yes.
I'm in my first sem of engineering.
Yeah.
And my branch is CSC.
Yes.
I'm also interested in physics. So is there some way in which I could contribute to this?
Like, actually, I don't have idea. Like, I was just visit. It was my internship project. This was, so actually I don't know, like, whether you could be, maybe.
I mean, since my BTech is in CSC, my program is in computer science. So how could I use my?
You could, like, since you are computer science, it will be much more help for them as well. But actually, I don't know, like, because I did not select the project. I just
you could try one thing. You could try some internship in your spare time. For example, after one year, and try some internship, and after that, if you like, you can pursue PhD in these things.
Where can I try for internship related to this?
I mean, that you have to. I mean, you can mail some individual professors also, or you can use some official. I mean, in summer internship, they will have a lot of official. Applications. You can apply it. I think there is some engineering and science both can apply in some applications. So you can try. That is one way. What I know.
And which institutes work on this project?
This project is mostly ISRO and RRI. No other institute.
Okay. Thank you.
Yeah.
Okay, so I guess we are done with the questions. Any more questions from anybody? I guess not. Thank you so much, Purvesh. It was a fascinating talk. I mean, it invited so many questions, so you can understand for yourself that it really engaged the people. So thank you. It was a pleasure to have you here.
Yeah.
And yeah, I hope we have some interactions in the future as well.
Yeah. Sure.
Thank you for coming up here. And by this, we end Young Physicists Meet 2022. It's been a memorable 2 days. I'll not be able to forget it in a long time. and I really didn't know that this would scale out to such a large magnitude. I won't say large, but in terms of the number of speakers who came and the number of talks that were presented, it was indeed large. So I did not imagine that this would happen. Shanshan, me some days back, maybe 2 weeks back, came up with such a proposal. And I must say, I mean, Shanshan hates this. I know to if I take his name too much, but then he deserves all the credit. He did the entire thing, and to be doing such a thing, like at being a student, is a huge thing. Also, I would extend my thanks to the other people who were instrumental in doing everything, like from setting up the teams, everything, the technical work, the streaming, and everything that went, the invitation and all. I'd like to take some names: Shomrat Ash from IIT Bombay, Ritik Dhara from IISER Kolkata, Shamobroto Paria, IIT Kharagpur, Hilachal, IIT Gandhinagar, Dr. Ritik Acharya from IIT Kharagpur, Orijit, IIT Kharagpur again. And so that was the thing. Thanks to all the viewers who were patient enough through all our technical glitches, and technical glitches which were rampant throughout the 2 days. And thank you to all the speakers for turning up, first of all, and second, when we could not stage all the things according to schedule, you guys actually cooperated with us. So thanks a lot. I hope that we'll have such interactions, more and more such interactions in the future. And it was a pleasure to have you all. And in advance, I'll wish all of you a happy new year. I wish that all of you prosper a lot in the fields in the years to come. And I hope your research in whatever field you are pursuing goes on very strong, and we get prouder and prouder of you in the upcoming years. With this is the host, me, Alekho Shah, signing off. Thank you very much.
Thanks a lot, Alekho. You carried the whole session on your shoulder. Without you, it would probably it would probably down.
Okay, fine. I mean, I'm very grateful to you for all the praise that you heaped on me. But you must understand that nothing would have happened without you. So yeah.
I'm probably nothing, and our team.
No. I did not mean that. Come on.
Yeah, those are probably the most genius people in our team.
I mean, how did you bring such people? I don't even have an idea. Like, you have amazing connections, I must say. Amazing connections. So, okay. I mean, the viewers are not here, I guess, to listen to our jibber jabber like that. It's getting cold. People must go and have their dinner. I don't know why Shomrat is still here. You must go to Mood Indigo now. Why are you here? Come on.
Not here, but I also want to thank all the speakers who attended actively with just in a reply of just single mail. It's not my credit; it's their credit. They help really us.
Actually, this is something I've realized. When you get up now, when you like move up, when you see actually good people around, they tend to be more modest and humble and tend to help a little more. This has been my observation.
Yeah, exactly. Thank you all.
Thank you so much. Okay, then good night.
Try to arrange this type of meeting in once a year at least. It's really helpful.
I mean, I really don't know, because given the fast nature in which our lives are progressing, I don't know where the people will be next year. So, but I hope, this has been really good. So I hope we can do it again. I hope so. Sure. And I really expect your active cooperation and participation if it's held again. So.
Yeah.
Okay then. Bye. See you. Happy New Year in advance.